Are you frustrated with the limitations of your organization's measurement systems? Knowing that the measurement systems you rely on to do your job aren't accurate or precise enough can be frustrating, and any incompatibility between systems just makes things worse. Data and analysis are only as good as the measurements you base them on. So the measurements you take from your measurement systems must be correct. Otherwise, actions taken to improve the process being examined may be inadequate or even damaging because they will be based on faulty data. Incompatibility between measurement systems can also negatively impact your organization's process improvement efforts. First, administrative costs increase because you have to maintain and operate different systems. Second, exchanging data between different systems may cause a loss of accuracy and precision. Finally, the time it takes to exchange data between systems can result in time-to-market delays, which can mean a loss in competitiveness. What you need is a way to make the most of your organization's measurement systems and maximize your process improvement efforts. Metrology, the science of measurement, provides you with a way to measure and control processes, which is critical to improvement efforts. There are three key elements of metrology. First, the establishment of internationally accepted and definable measurement standards. Second, the use of measuring equipment to compare process data to specifications. And finally, the regular calibration of measuring equipment, traceable to international standards. The three predominant international systems of measurement are the English system, the metric system, and the international system of units, commonly referred to as the SI system. Both the English and SI systems are used in the U.S. Of the three, it is the SI system that has the final authority for setting measurement standards. The SI system is founded on 7 fundamental units. Each fundamental unit corresponds to one of 7 distinct categories of measurement. In a Six Sigma project, products and processes will be measured for one or more of the 7 SI system categories. First, there's amount of substance, which is measured in mole. Next, electric current, with the unit of measure being the ampere. There's also length, measured in meter, light, measured in candela, and mass, measured in kilogram. The final 2 categories are temperature and time. The unit of measure for temperature is the Kelvin, and the unit of measure for time is the second. Access the job aid SI system units after the video to review the SI system units. Measurements are used in a Six Sigma project to determine whether products or services are delivering on customer requirements. When you are basing your improvement efforts on these measurements, you want to make sure they're correct. Correct measurements are both accurate and precise. Precision describes how close the measurements are to each other. Accuracy describes how close the measured values are to the reference value. Accuracy and precision are critical in the sport of archery. When archers practice their sport, they use a target, with their objective being to hit the bullseye. Why? The ability to repeatedly hit the bullseye, which represents the measurement standard, demonstrates how accurate and precise their shooting is. Just like in archery, the goal of measurement is to achieve both accurate and precise values. When the arrows are randomly spread across the target, or even misses the target altogether, the archer's shot are neither accurate nor precise. The arrows are not close to the target, nor are they centered. If the arrows are clustered closely together in the top right corner, for instance, the archer's aim is precise, but the fact that they are off-center indicates that his shot is not accurate. When the arrows are loosely centered around the bullseye, then the shots are accurate. However, because they are not tightly clustered, the shots aren't precise. If the arrows are centered and tightly clustered around the bullseye, then the archer's shot are both accurate and precise. It's accurate because the shots are centered, and precise because they are close together. A lack of precision or accuracy, or both, leads to measurement system error, which is the difference between measurements and the reference values for a measurement system. You need to understand the elements of accuracy and precision to understand measurement system error. Accuracy and precision are made up of different elements. Accuracy has 2: stability, which is accuracy over time and usage, and linearity, which is change in accuracy over lower and higher ranges of measurement. The elements of precision are discrimination, repeatability, and reproducibility. Discrimination, which may also be referred to as sensitivity or resolution, is the smallest readable unit of measurement, whereas repeatability refers to the precision or closeness of measurements of the same units by the same measurer using the same equipment. Repeatability can be further broken down into consistency and uniformity. Consistency is repeatability over time, and uniformly is repeatability over different values. Finally, reproducibility describes the precision of measurements of the same units by different measurers using different equipment. So now you know that a lack of accuracy and precision can lead to measurement system error. But what are the sources of error in a measurement system? Typical sources of measurement error include machine, methods, man, materials, Mother Nature, and management. Machine or measurement equipment error is error inherent to the machine. Machine error may be caused by a lack of accuracy or precision or gauge instability over time. Methods error can be caused in 4 ways: when there is more than one way to obtain a measurement and results vary, when the wrong method or procedure is designated for use, when the proper procedure or method is not used, or when variation exists in software formulas. Measurement error attributed to man includes operator error and operator-to-operator error. Operator error occurs when the same person using the same measuring instrument on the same product gets different measurements. Operator-to-operator error is caused by differences in measuring techniques and occurs when 2 people use the same measurement instrument on the same product but get different results. The underlying causes may include lack of training, physical ability, or motivation. Materials or parts-related measurement error may occur when, during the process of testing a product, the sample being measured is destroyed or changed in a way that makes subsequent measurements impossible. This type of measurement error may also be caused by the instability of the materials over time and a lack of homogeneity. Mother Nature is a category of error used to describe error that occurs due to variability in the natural environment. Causes of this type of error include differences in temperature, humidity, atmospheric pressure, lighting, noise levels, vibration, and electronic emission. If environmental conditions are not constant between labs testing the same products, Mother Nature error can arise. Management issues can also be a source of measurement error. Causes of management error include procedures that differ from laboratory to laboratory, inconsistent goals and objectives, or reward systems that are contrary to the stated goals and objectives of the measuring system. An atmosphere of mistrust or fear can also contribute to management error. Measurement systems consist of diverse components including people, instruments, equipment, and methods. And each and every one of them can be a source of error. Follow along with the examples to learn about sources of error. Weight measurement of the parts coming out of a lathe machine shows excessive variation. On further analysis, it was found that the inbuilt scale in the lathe machine has not been calibrated for a long time and is the prime cause of the variation measured. Measurement analysis of a sawmill's output indicated unusual variation. An investigation determined that the wrong method was used and was the source of the measurement error. This is an example of methods error. It's Philip's job to observe the temperature reading for the furnace, flashed every 5 seconds on the display monitor. Lately, significant measurement variation was evident in the furnace temperature. An investigation reveals that Philip failed to observe measurement correctly due to his weakening eyesight and needed glasses. At a plastic goods manufacturer, the viscosity of the liquid plastic changes in a short time as it flows to the next processing stage, and the measurement gives a different value each time. This is an example of measurement error caused by materials instability over time. Space scientists have designed a test to help them understand the effects of weightlessness on the cardiovascular system of astronauts. They need to make sure the test conditions in the lab are exactly the same each time the tests are conducted. Otherwise, variations in humidity and temperature will introduce error and make the results unusable. The potential impact of environmental factors makes this a clear example of Mother Nature error. It's Jill's job to check the output of a process. Her bonus is determined by how often the process is within specification, even though she has no authority for measurement quality. Sometimes Jill reports measurements that indicate the process is within specification when it's not. Jill's motivation for falsifying measurements is directly related to a management issue, making this an example of management error. Six Sigma focuses on process improvement, but you should know that process error, including part or product error, doesn't account for all the variation observed. If, during the measure phase, you focus only on process error, your improvement efforts may not be as effective as you expect. Why? Because measurement error is also a source of variation, and your improvement efforts will be misguided if you mistake excessive error in the measurement system as excessive process error. So if you want to reduce total variation, improve your measurements first. So before even thinking about how to achieve process improvement, you need to determine how much of the total variability is measurement error. A high measurement error value that goes unnoticed could lead you to make bad decisions about how to reduce variation and improve processes. High error values diminish your data's usefulness. The higher the measurement error value, the more likely it is that a product will be deemed acceptable when, in reality, it doesn't meet customer requirements. Similarly, a high measurement error value could cause you to reject perfectly acceptable products. When you incorrectly approve a product because of a high measurement error, the customer will end up discovering the problems. Customer requirements won't be met, and they'll be extremely dissatisfied. And if perfectly acceptable products are unnecessarily rejected, you'll end up wasting time and resources trying to fix non-existent problems. Before you can reduce the variation caused by measurement error, you need to identify what part of total variability is attributed to measurement error. Measurement error is the same thing as measurement variation and indicates how much of the total variability is attributable to the measurement system. Measurement systems consist of diverse elements, including people, standards, devices, environments, instruments, and methods that together make up the process used to obtain measurements. Total variability is the sum of process variability and measurement system variability. Measurement error is the difference between the measured value and the true value, represented by the accepted reference standard. Metrology helps Six Sigma practitioners ensure the measurement data collected for analysis is correct. Metrology relies on the SI system as an international guide to measurements. The SI system classifies measurements into 7 distinct categories, and the measurement units of which make up its fundamental units. Sources of measurement system error are categorized as machine, methods, man, materials, Mother Nature, and management. Measurement error contributes to total variability and must be identified before process improvement decisions are made. Improving measures and the measurement system before making process improvements leads to changes that are necessary, effective, and efficient. Each element in a measurement system is a potential source of error, and while elimination of error from all sources is important, this video will focus on the error introduced by measuring devices. Calibration is the process of comparing a measurement device to a standard of known accuracy. The primary goal of calibration is to eliminate the measurement error introduced by measurement devices. Calibration maintains accuracy. It doesn't increase precision. Typically, the precision of a device remains constant. Over time and with use, the measurement devices you rely on to keep your processes under control tend to lose accuracy. Regular calibration can help maintain accuracy. But how often should you calibrate devices? Considering the attributes of your device will help you set appropriate calibration intervals. These attributes are stability and adjustment history, purpose, and usage. First, stability. A measuring device's ability to maintain accuracy over time will impact the calibration interval set for a device. The device's adjustment history is a valuable resource when considering stability. Second, purpose refers to how the measuring device's measurements will be used. When considering purpose, consider how important it is that the measurements are accurate, or how critical of an application they're being used to judge. And finally, usage considerations are related to how often a device is used and under what environmental conditions. Calibration intervals can be impacted by things like temperature, potential for contamination, and treatment. Once the attributes of the device have been considered, its calibration interval may be set, if new, or adjusted. You adjust the calibration interval depending on how stable a device is. Lengthening the interval may be appropriate if recent calibrations haven't required any adjustment. If the device's history shows that each time it's calibrated it needs adjustment, you should probably shorten the interval. Setting a short calibration interval for a new device will help maintain its accuracy until its stability can be determined. The biggest issue when considering the measuring device's purpose is the criticality of the application it's being used to control. The more important it is that the measurements are right, the shorter your interval will be. For example, the calibration interval set for the device used to calculate Space Shuttle re-entry trajectory should be shorter than that used to calculate the number of red candies that are put in a bag of multicolored candy. When considering usage, you should consider all the things a device is exposed to where it's used. A shorter interval may be appropriate if the device is used outdoors rather than indoors, operates in an extreme environment rather than a moderate one, or is used under rough conditions rather than safe conditions. A good example is the difference between the usage of two navigation devices. While the purpose of both is critical, the usage of a handheld device on a Coast Guard rescue boat will warrant a shorter calibration interval than one used inside a climate-controlled air traffic control tower. Effective calibration systems depend on documentation of all calibration activities. The dates of scheduled and completed calibrations, the results of calibrations, and the actions taken in response to them must all be documented. These details form the basis of the adjustment history used to consider a device's stability. Calibration systems typically require that a method is in place to inform users of upcoming calibration activities. Clearly labeling devices with the date of the next calibration can achieve this. Today, many organizations seek ISO 10012-2003 certification. This is a measurement management system based on international standards and applies to measuring equipment and processes. It's used to ensure that the physical characteristics of products conform to specifications. Organizations looking to achieve certification must prove that their measurement systems are calibrated to the standards set by ISO 10012-2003. Written procedures and work instructions are emphasized by the ISO standard. To put it simply, ISO requires companies to write what they do and do what they write. ISO 10012-2003 is the governing standard. It fulfills earlier ISO standards and replaces both ISO 10012-1-1992 and ISO 10012-2-1997. Achieving the ISO standard requires organizations to have a measurement system that meets some basic criteria. To meet this criteria, the following activities must be performed. Organizations are required to document procedures for defining the system and evaluate equipment, as well as review and evaluate the calibration system regularly. They should also establish calibration intervals according to the type of equipment, usage conditions, and calibration standards traceable to national standards. And finally, they're required to recalibrate devices regularly. Imagine how hard it would be to do business in today's global marketplace if standard measurements weren't available to prove the accuracy of measuring systems. Traceability is the ability to prove that your measuring system gives measurements that are calibrated to reference standards. Traceability is a requirement of ISO and the cornerstone of any measurement system. Unchangeable standards, like those of ISO, are used to make sure industries and businesses around the world are operating according to the same standard measurements. So a kilogram in Hanoi is equivalent to a kilogram in New Hampshire. For measurements and measurement devices to be traceable, they must be able to be compared to unchangeable standards, like those established and maintained by ISO or the International System of Units, commonly referred to as the SI system. Take the SI system, for example. SI units are defined by absolute physical measurements. This is what makes the system worth tracing to. The meter is the standard unit of length. A meter is defined as the length of the path traveled by light in a vacuum during a time interval of 1/299,792,458th of a second. The kilogram, the standard unit of mass, is equal to the mass of the International Prototype, a cylinder of platinum iridium alloy kept by the International Bureau of Weights and Measures at Sèvres, France. A traceability hierarchy of standards is used to guide metrological applications. When things are measured, these are the various standards, such as SI system or ISO standards, they are compared to check their accuracy. As the level of authority for maintaining accuracy increases, so does the level of accuracy. From the top down, the traceability hierarchy of standards starts with national and international standards, moves through reference, functional, and calibration standards, and ends with working level standards. At the highest level of accuracy, the national and international standards are the final authority on measurements. All standards must be traceable to this level. Most industrialized nations have a national reference, which is used instead of national standards. The National Institute of Standards and Technology, or NIST for short, is the reference standard used in the U.S. Reference standards are traceable to international standards. The next level down, the metrology labs of organizations use functional standards to measure precision work and to calibrate other standards. This is followed by calibration standards, which are simply the standards to which the working level standards are calibrated. At the lowest level of accuracy are working level standards. Working level standards include the devices used during work activities. Why is the traceability hierarchy important? Suppose you produce plumbing washers, plastic or metal rings used in plumbing applications, to supply a national market. Incorporating the traceability hierarchy into your measurement system will help make sure the washer is produced according to national standards. This means your washer will be compatible with national standards and meet customer needs. A gauge traceability document is used to document traceability. It has 7 essential elements. First, an unbroken chain of comparisons. It's a documented system of comparisons traceable to a national or international standard. Next, measurement uncertainty must be calculated and stated for each step in the chain. The measurement uncertainty of each step is calculated using defined methods and is used to determine the overall uncertainty for the entire chain. Documentation is essential on 2 points as well. First, each step in the unbroken chain of comparisons must be performed according to known, documented procedures. Second, as each step is performed, its results must be documented. Parties responsible for performing the steps in the chain must be competent to do the work. So, competence is the next essential element. Training records and accreditation by a recognized body are examples of how competence can be proved. Next, the standards used must be primary standards for the realization of the SI units, meaning the ability to achieve calibration traceable to the SI system standards. Periodic recalibration of standards and equipment is another element. It must be performed according to established intervals. This is essential to maintain traceability of the standard over time and with use. And finally, a measurement assurance program must be established to make sure the measurement process is valid and the standard being used is accurate. Josie, Brad, and Rick are responsible for making sure their company's gas meters are traceable to SI system standards. Follow along as they create a gauge traceability document. First, Josie documents a procedure that will allow them to support an unbroken chain of comparisons. The procedure begins with the SI system standard, the cubic meter, and works on down through functional, calibration, and our own working level standards. Next, Brad works with Josie's traceability hierarchy to calculate the measurement uncertainty for each step of the chain. He then established the overall measurement uncertainty for the chain to be plus or minus 0.5%. Rick works on the procedures that will guide the traceability procedure to achieve an unbroken chain of comparisons step by step. And he creates guidelines for documenting the results of each step. The SI system is used as the highest level of standard, and thus the realization of SI units will be achieved. Brad also collects and documents proof of the team's competence, including its collective skill sets, training, and its good standing with the National Accreditation Authority. All that's left is to establish calibration intervals. Based on recent consideration of the gas meters, they decide to shorten the calibration interval because winter is approaching. Finally, they make sure their measurement assurance program is appropriate. Calibration is used to maintain the accuracy of measurement devices. Comparing a measuring device or standard to a device of known accuracy or another standard allows you to identify measurement error, which can be eliminated by recalibrating the device. 3 attributes must be considered when setting or changing a device's calibration interval: stability and adjustment history, purpose, and usage. Traceability is used to ensure that measurements are accurate within the overall uncertainty of measurement. Essential elements of traceability include an unbroken chain of comparisons, measurement uncertainty, documentation, competence, realization of SI units, periodic recalibration, and measurement assurance. A gauge traceability document outlines the system in place to achieve traceability to standard. Process improvement decisions are based on the measurements gathered using your organization's measurement system. Can your measurements be trusted? The answer to this question is critical to Six Sigma project success, and measurement systems analysis, sometimes called MSA, can help you to answer it. You should be familiar with measurement systems analysis from your background in Greenbelt concepts. Measurement systems analysis simply means taking measure of the measures. It provides a way for organizations to determine how much error or variability is introduced by their measurement systems. Measurement systems are made up of measurement devices, such as equipment, instruments, and tools, as well as measurement process elements, such as people, standards, operating environments, and methods. In other words, the measurement system comprises all components that combine to generate the measurements. Organizations commonly break their analysis into error caused by the measurement process and error caused by the devices, which focuses effort and reduces error more effectively. Access the content measurement systems after the video if you wish to further review measurement systems analysis. Performing a measurement systems analysis should be the first thing you do to reduce total variability. If there is error in your measurement system, there will be error in your measurements, and your data won't truly reflect the characteristics of the things you measure. Basing improvement efforts on incorrect measures can be ineffective or even counterproductive. Reducing measurement system error can be the most cost-effective way to improve your processes. You can be certain your decisions are based on reality, and you won't spend time trying to improve your process when it's your measurements that are the problem. Measurement systems analysis involves measurement correlation. Measurement correlation is the comparison, or correlation, of the values from different measurement systems or components of measurement systems. Typically, the comparison is made between systems or components that you would expect to be strongly correlated. Measurement correlation can be assessed within various types of comparisons, including values against a known standard, measurement device against measurement device, and measurer against measurer. Comparing values against a known standard, the established reference standard, can be done using a component of a measurement system or the system as a whole. For instance, using a device to measure a series of items that has known dimensions will tell the team whether or not measurement error is being introduced by the device. Calibration is an example of measurement correlation, where values are compared to a known standard. Device against device comparison is where similar devices measuring the same or similar artifacts are compared. This is also known as round-robin or proficiency testing. This type of comparison may be done when national reference standards aren't available for the specific range of values or conditions being measured. It provides a way to separate the error attributed to the thing being measured and the device used to measure it. Measurer against measurer comparison is when data measurers are compared to one another or the same measurer's results are compared on repeated inspections. This technique is used to assess the human element in the measurement system by measuring the degree of agreement between persons gathering the same data or rating the same set of observations. This will indicate whether or not data gatherers are contributing to the error or variability observed in a process. You may compare values against a known standard when you want to verify the accuracy of your measuring device. For example, a scale used to measure gold coins may be calibrated against a standard coin whose weight has been verified. You may compare one device against another device if you use equipment to gather your measurements. For example, perhaps a cosmetic company uses automated product analysis tests to determine if products have been made according to specification. Different machines are used to test the same characteristics throughout the production line, and the organization assumes perfect correlation between machines. This correlation can and should be verified. You may compare measurer against measurer or measurers against themselves on repeated inspections when you want to know if the measurers are introducing error. For instance, maybe you regularly collect data about your output as part of your quality efforts. If you observe unexplained variation, you might first compare the data collected by each gatherer to determine whether variability among the measurer's values is the source of variation. How can you determine measurement correlation? You can use percent agreement to determine the correlation between different measurement systems or components of measurement systems. While there are a number of methods, the focus of this section will be on percent agreement. Percent agreement is the ratio of observed agreements in two or more data sets. It deals with the proportion of identical results obtained by the tested components or systems. For example, if two devices are used to measure 4 items, and the resulting data sets show 2 identical measurements out of 4, the devices could be said to have 50% agreement. Percent agreement can be used to compare a measurement system or component with a standard, or with other systems or components. It can also be used to compare different measurers, or the same measurer on repeated inspections. You can use percent agreement with categorical data. With this type of data, percent agreement typically compares the number of pass-fail attributions by one system, component, or measurer with the number of pass-fail attributions made by another system, component, or measurer. For example, one measurer determines that 90 out of 100 items pass inspection, while another measurer determines that only 85 out of 100 items pass. A total of 75 of the objects passed were passed by both measurers. Agreement between measurers is therefore 75%. Percentage agreement also describes the proportion of measurements that exactly agree with a reference standard. For example, a team uses its measuring device to measure an object of known standard weight of 5.98 grams. It obtains a value of 5.98 grams in 85 out of 100 measurements, so its agreement with a reference standard is 85%. Percent agreement can also be used with continuous data. You can estimate percent agreement for two systems or components measuring continuous data by calculating Pearson's correlation coefficient, R. When you use Pearson's coefficient to estimate percent agreement, the R value is expressed as a percentage. So if the R value is positive 0.3, it's expressed as a percent agreement of 30%. Percent agreement helps you determine how measurements are increasing or decreasing together in the same direction. A negative R value indicates that the measurements are inversely related or moving in opposite directions. And an R value of 0 indicates that the datasets have no measurements in common. While both are possible, they are unlikely. If you calculate Pearson's correlation coefficient and get an R value of 0 or less, it indicates that something is drastically wrong with the measurement components or systems being compared. Suppose you want to know the correlation between the measurements obtained by two people measuring the same series of items. Using an XY chart, you can plot measurer A's values on the y-axis and measurer B's values on the x-axis. If the two measurers have obtained identical values for all measurements, the R value will be 1.0. The data points will form an upward sloping line making an angle of 45 degrees with the x-axis, and the percent agreement value will be 100%. A more likely outcome is that as the number of data points in agreement decreases, the plotted points will spread further across the chart. The points will generally still fall in a pattern when expressing percent agreement. There is no fixed value for a percent agreement to be identified as good or bad, and it depends entirely on the nature of business and organization's own standards for measurement quality. However, just based on the R value, The percent agreement can be described as being high, moderate, or low. Each term describes the measurement correlation of the systems or components being compared. A high percent agreement indicates a high measurement correlation. When the R value is 1, it indicates a percent agreement of 100% and tells you that all the measurements are identical between systems or components, which is the desired condition. Values of R that are nearer to 1 than 0.5 return a high percent agreement. A moderate percent agreement indicates a moderate measurement correlation. When the R value is 0.5, it indicates a percent agreement of 50% and tells you that between the two sets of data, half of them are identical. Values of R that are nearer to 0.5 than to 1 or 0 return a moderate percent agreement. A low percent agreement indicates a low measurement correlation. Any R values that fall nearer to 0 than 0.5 indicate a low percent agreement. Consider this example. A team responsible for assuring the quality of light bulbs wants to determine measurement correlation for 2 of its light meters. Light intensity measurements are taken for 100 bulbs using each light meter. A percent agreement of 90% between the 2 meters is calculated. This means that 90% of the measurements being compared are identical. The team concludes that the measurement devices are highly correlated with each other. If you want to understand why you get a particular value for measurement correlation, you'll need to consider the several categories of measurement system error that influence correlation. Bias, repeatability, reproducibility, stability, and linearity are all categories of error that combine to explain measurement correlation. First, bias is the difference between the measured values and reference values. Next, repeatability is precision or closeness between repeated measurements of the same item by the same measurer. Reproducibility is also the precision or closeness between measurements of the same items, but this time it's measurements by different measurers. Fourth, stability represents the change in accuracy or bias of a measurement system over time and usage. And finally, linearity is the change in measurement accuracy or bias over the entire range, low to high, of measurement. Regularly tracking these sources of measurement error will help you understand your measurement system. This is done using various analysis approaches, including bias studies, linearity studies, stability assessments, and gauge repeatability and reproducibility studies. Measurement systems analysis is used to determine how good your measurements are. Determining measurement correlation for part or all of your measurement system can help you find out if your measurements can be trusted. Calculating percent agreement is one way to determine measurement correlation. Perfectly correlated systems and components will have a percent agreement of 100%, meaning that all values are identical between the systems, components, or reference standards being compared. Highly correlated measurement systems will have a percent agreement value closer to 100% than 50%. A less than perfect correlation indicates that measurement error accounts for some of the variation you observe in your process. When bias is present in your measurement system, measurement results can be misleading, inaccurate, or off-kilter. Bias is one of the categories of measurement error that contributes to measurement correlation. If you want to understand measurement correlation, you need to know the effect bias is having on your measurement system. Bias is the systematic difference between the average measured value of an item and the actual or reference value. Determining bias helps you understand how far off the reference value your measurements are. Bias can be caused by unobserved differences in systems, by human factors, or by unassignable causes. Bias is directly related to accuracy. Accuracy describes how close the average measured values are to the true value and is one of the key components of measurement error. So the larger the bias, the less accurate your measurements. While bias does exert an effect on accuracy, it's not likely to exert an effect on precision, the other major component of measurement system error. Measurements can be precise and still be affected by bias. Performing a bias study will tell you how close your measurement system or devices come to providing accurate measurements. Conducting a bias study is something you are likely to be familiar with from your background in Greenbelt concepts. Access the content Conducting a Bias Study after the video to review the procedure for conducting a bias study. When you conduct a bias study, it is essential that you are familiar with the bias formula. How do you complete the bias formula? First, you need to know the average of the repeated measurements and the reference value. There are two components to the bias formula, the average measurement and the reference value. The first part of the formula is the calculation used to get the average of the measurements taken. Find the average as you normally would by adding all the measurements to find their sum and dividing by the number of measurements. The second part of the formula represents the reference value, expressed in the formula by the uppercase letter T. You will have to select a standard to represent the reference value. It will likely be a master part or a standard traceable to a national or international standard, like the National Institute of Standards and Technology. Once you calculate the average, you are ready to calculate bias. Bias equals the average measurement minus the reference value. For example, say you have a standard, a screw, with a known value of 10.00 millimeters that is checked 10 times by an inspector using a dial caliper. The measured values are 10.02 millimeters, 9.98 millimeters, 10.00 millimeters, 10.00 millimeters, 10.02 millimeters, 10.00 millimeters, 10.00 millimeters, 10.02 millimeters, 10.02 millimeters, and 9.98 millimeters. If you wanted to find the bias, you would first add the 10 measurements to find their sum, which is 100.04 millimeters. Next, you would find the average by dividing the sum of the measurements, 100.04 millimeters, by the number of measurements taken, 10, resulting in an average measurement of 10.004 millimeters. Finally, you complete the calculation by subtracting the reference value, 10 millimeters, from the average measurement, 10.004 millimeters, to get a bias of 0.004 millimeters. After you calculate bias, you may find that it's positive or negative. Both are possible. A negative bias tells you that the measuring system or device is underestimating the true or reference value. This means that, on average, the measurements obtained are smaller than the reference value. A positive bias tells you that the device or system is overestimating the true or reference value. This means that, on average, the measurements obtained are larger than the reference value. In the screw manufacturing example, your average measurement, 10.004 millimeters, was larger than the reference value, 10 millimeters. Hence, the measuring device in this example has a positive bias. Once you have calculated bias, it can be expressed or reported in two different ways. First, as a percentage of total process variation, or second, as a percentage of the tolerance set for the process. When expressing bias as a percentage of total process variation, percent bias equals the absolute value of bias divided by total process variation, all multiplied by 100 to give a percentage. When expressing bias as a percentage of the tolerance set for the process, percent bias equals the absolute value of bias divided by the tolerance range, all multiplied by 100 to give a percentage. Recall the example of the inspector measuring screws, who found the bias was 0.004 millimeters. Suppose the process variation is 0.50 millimeters. What would bias expressed as a percentage of process variation be? Using the percent bias formula, you would divide bias, 0.004 millimeters, by process variation, 0.50 millimeters, and multiply the result by 100. Bias expressed as a percentage of process variation equals 0.8%. This means that the device will, on average, produce measurements that are 0.004 millimeters larger than the reference value, bias. This measurement bias accounts for 0.8% of the process variation. If you want to determine the statistical significance of the value of bias you find in your study, you can do so using a t-test for significance. This t-test is something you will recall from your Greenbelt level work. Bias is one of the categories of measurement error that contributes to measurement correlation. You can find bias by finding the average of the measured values and subtracting the reference value. If the bias value is positive, the system device is overestimating. A negative bias value indicates the opposite. Bias is commonly expressed as a percentage of process tolerance or variation. Calculate bias as a percentage of process tolerance or variation by dividing the bias by process tolerance or variation, then multiplying by 100. The resulting value will tell you what percent of process tolerance or variation is attributable to bias. Along with bias, another category of error that helps to explain measurement correlation is linearity. Linearity describes the variation between the measurement and the known standard, in other words, the bias, over the entire range of the measurement instrument. Studying linearity helps you determine whether the bias associated with a measurement system is constant throughout the operating range of its measuring devices. From your background in Greenbelt concepts, you'll recall that linearity studies typically take place during the measure stage of the DMAIC process. Linearity studies allow you to evaluate the accuracy of the measurement system throughout the range of measurements required for your improvement project. When conducting a linearity study, the rule of thumb is to measure 10 parts 5 times each. This will provide sufficient data to determine linearity. Access the content Conducting a Linearity Study after the video if you wish to review the procedure for conducting a linearity study. When you finish measuring each part 5 times, you calculate the bias operating on each part by subtracting the true value of the part from the average measured values. Then plot bias on the y-axis against reference values on the x-axis. To interpret linearity, you need to assess the slope and the y-intercept of the resulting regression line. Several patterns are possible. The first pattern is a slope of 0 as well as a y-intercept of 0. If a measurement system or component is described as being linear, it means any bias in the system is constant across its operating range. In this best-case situation, the bias is constant at 0, meaning that linearity is optimal. The y-intercept is also 0, meaning there is no bias in any of the measurements. This is apparently a perfect system. A slope other than 0 is also possible. If the line is straight but has a slope other than 0, the measurement system or component is nonlinear, not accurate across the operating range, and may require calibration or repair. The larger the slope, the less linear the gauge. It indicates that the degree of bias influencing a measurement changes with the size or characteristic of the item being measured. For example, bias may increase as a team uses a gauge to measure the largest items in a series, even though bias was minimal when measuring moderately sized items. The larger the slope of the line, the more extreme the difference in bias across the operating range. Another possible pattern is a slope of 0 and a y-intercept other than 0. If the line is straight but has a y-intercept other than 0, the system or component has a constant bias, but an optimum linearity. This means that the level of bias will be the same no matter what the value of the measurement. The final pattern is a curved line. If the line is curved, it indicates extremely problematic nonlinearity with bias that changes exponentially as the measurement value changes. This measurement system is in urgent need of recalibration, repair, or replacement, and it cannot be trusted. You can use the formula L equals B multiplied by V subscript P to calculate a value for linearity. In the formula, L equals linearity, B equals slope, and V subscript P equals process variation. The smaller the value of linearity, the better. Graphically, the smaller the slope, the better. Guidelines for what constitutes acceptable linearity differ depending on the organization, the item being measured, and other circumstances. Suppose you work for a machine tools manufacturer. As part of a Six Sigma project, you want to know if the measurement system responsible for weighing the various parts is linear. Electronic weighing machines are used to measure the weights of the parts in grams. So you take 5 readings of 7 components spanning the entire operating range of the weighing machine. the exact weights of the parts are known. Your reference values are 5.00, 10.00, 15.00, 20.00, 25.00, 30.00, and 35.00 grams. For each reference value, the reference parts are measured 5 times, and average readings are determined for each component from which bias is found. Suppose the readings found for the reference value of 25 are 24.98, 25.02, 25.13, 24.99, and 25.11. The average reading is 25.05. To find the bias, you subtract the reference value from the average reading, giving a bias of 0.05. You then plot the bias on the y-axis in 5-point increments from negative 0.15 to 0.10, and the reference values on the x-axis, also at 5-point increments from 5 through to 35. Once this is done, draw a best fit line representing linearity on the scatter plot. You need the slope of the plotted line to calculate linearity. In this case, the slope is 0.0094. A software application was used to derive the values for this calculation. Assume that the process variation is 0.05 and the equation of the fitted line is y equals negative 0.2004 plus 0.0094x. The software you use to plot your data points will calculate this equation. Using these values, you can determine the linearity of the measurement instrument. A slope of 0.0094 multiplied by a process variation of 0.05 produces a linearity value of 0.00047. Linearity values other than 0 generally indicate that the measurement system requires calibration, replacement, or repair. They could be an indication that a measurement instrument is not properly calibrated at the lower and upper ends of the operating range, or that there's an error in the value of x, the reference standard, at the maximum or minimum range. They could also indicate that an inappropriate or worn measurement instrument is being used, or that there's internal design problems with the measurement instrument. Like linearity, stability is a category of measurement error. Stability is understood as accuracy over time. It refers to a measurement system's capability to produce consistent results at different points in time on the same sample. Your biggest challenge may be proving stability in your measurement system. Developing appropriate procedures can help overcome this challenge. Examples of threats to stability include continuously revised data collection forms that make it impossible to evaluate process changes against a historical standard, and degradation in measurement systems. You can assess your measurement system's stability using control charts, typically X-bar and R charts. Measurement means are plotted on the X-bar chart and measurement ranges on the R chart. When your measurement system is in control, data points fall within the upper and lower control limits. The data points plot randomly around the center or average line, and there are no discernible patterns of variation. The process for assessing stability requires you to complete 4 steps: collect measurements, calculate the means and ranges, plot the means and ranges on a control chart, and analyze the X-bar and R chart. Over a minimum of 20 short periods, typically days or weeks, collect 3 to 5 measurements in each period. Each period will represent one subgroup in control charts. Be careful to take your measurements at different times to help you capture measurement variation caused by natural environmental factors. Then, using the collected measurements, calculate the mean and range for each period. The third step is to plot the mean and range values on the X-bar and R chart respectively. You will have already determined the UCL, LCL, and centerline values for your data. The last step is to analyze the X-bar and R chart for statistical control. This can be done by checking for patterns. Patterns on the X-bar and R chart can highlight a trend, cycle, or out-of-control variation in your control chart that should be investigated. When analyzing X-bar and R charts, there may be a number of patterns of interest. However, 3 basic patterns provide clues about your measurement system's stability. The first is when points are beyond the UCL and LCL. When plotted points extend beyond the upper and lower specification limits, it is an indication that the measurement system or device is out of control. This may be due to a miscalculated or misplotted data point, a special cause of variation from a material, equipment, method, or measurement system change, or a mismeasurement. Out-of-control points should be investigated. The second pattern consists of points trending up or down. Several points moving dramatically up or down can indicate a trend. Trends may include drift in the measurement instrument, worker fatigue, or an improvement or deterioration in measuring technique. And finally, cyclical or repeating patterns in the data points can indicate various cyclical changes. These may include changes in temperature, instrument wear, differences in operators and shifts, or differences in measuring devices. Understanding linearity helps you determine how bias is affecting your measurement system. This is important if the measuring system or devices are used to measure a range of values. If linearity isn't constant over the range of measures, bias is inconsistently affecting your measurements. Stability is another important factor affecting measurements. You can use an X-bar and R chart to assess your measurement system's stability. The pattern created by plotting the mean and range of measurements from each time period can visually depict the type of variation present. Patterns may indicate that an out-of-control condition exists, or that a trend or a cyclical change is affecting. Measurement system capability can be analyzed and interpreted using various analytical methods, including gauge repeatability and reproducibility, or GR&R studies, and the precision-to-tolerance ratio calculation. Recall that total variance is made up of both process variance and measurement variance, or error. Now, if you break down measurement variance, you find that it's made up of repeatability and reproducibility. When exploring repeatability and reproducibility, the focus is on measurement error, not process error. If you want to know how much variance, or error, is attributable to your measurement system, determining repeatability and reproducibility is one way to find out. Gauge R&R studies are performed to determine the amount of variation in a measurement system and to determine how much variation is a factor of repeatability and how much is a factor of reproducibility. You should be thoroughly acquainted with GR&R studies from your Greenbelt training. Access the content Gauge Repeatability and Reproducibility Studies after the video if you wish to review this method of measurement systems analysis. Suppose you are conducting a GR&R study to determine the amount of variation in a measurement system used to weigh steel pins. You will first need to find out what data was collected during the study. The weights of 10 steel pins are measured 3 times each by 3 different operators, each using the same measurement device. The results, in centimeters, are recorded in a table. For each operator or measurer, the table provides room to record values for each part being measured in each of the trials. The average measure per part per trial is calculated and recorded, as is the mean of the averages, X double bar, of the parts per trial. The range per part and the average range per trial, R bar, is also calculated and recorded. Now that you've studied the data, you can move on to determine repeatability. From your background in Greenbelt procedures, you'll recall that this involves 3 steps: calculating R double bar, determining D subscript 2, and finally using the repeatability formula to calculate repeatability. The R double bar value is the mean of the range averages. In the steel pins study, the range averages per trial are 1.49, 1.31, and 1.33 respectively. The mean of these averages is 1.38. The D subscript 2 value is found using the D value table. Choose the value that corresponds with the number of readings taken by each operator as the sample size, n. In this case, the D subscript 2 value that corresponds with the sample size of 3, 1.693, is the right one to use. Now that you know the values for R double bar and D subscript 2, you can perform the final step of calculating repeatability using the repeatability formula. The standard deviation for repeatability is equal to the mean of the range averages, 1.38, divided by the D subscript 2 value of 1.693. Completing the calculation, you get a standard deviation for repeatability of 0.82. Because repeatability reflects variation in the measurement equipment, differences here indicate that your measurement device itself is contributing to overall variation. The next step in conducting the GR&R study is to calculate reproducibility. Calculating reproducibility, also known as appraiser variation, tells you how much variation is caused by the person taking the measurements. Like the repeatability calculations, calculating reproducibility is a three-step process. Now that you've calculated repeatability in the steel pins GR&R study, you're ready to move on and calculate the reproducibility value. To determine reproducibility, you need to first calculate Rx bar, the difference between the largest and smallest operator averages. For example, the largest operator average is 6.07 and the smallest is 5.94. When you complete the calculation, you get a value of 0.13. After calculating Rx bar, you go on to determine the value for D subscript 2 using the table. The sample size for the steel pin study is 3, so the value of D subscript 2 is again 1.693. Now you can determine reproducibility. This step involves the reproducibility formula itself. Using the Rx bar value and D subscript 2 value, you calculate reproducibility. The Rx bar value of 0.13 divided by the D subscript 2 value of 1.693 returns a reproducibility value of 0.077. Different X-bar values for different operators is an indication that appraisers or operators are introducing bias. In the example, the X-bar value generated from the readings of each operator is unique. Based on these results, it is clear that reproducibility variation exists. With the values of repeatability and reproducibility determined, you can compare them to find out which is contributing the most to measurement variation. Comparing the two values allows you to determine which is larger and, consequently, which is the larger source of variance. This will help you to focus your improvement efforts. In the steel pin GR&R study example, repeatability with a value of 0.82 is larger than reproducibility with a value of 0.077. Since repeatability contributes more variation, it should receive priority. High levels of both repeatability and reproducibility are desirable for a measurement system. A high level of repeatability indicates low within-system variability given that conditions of measurement, measuring instrument, operator, method, and environment, are stable and defined. A high level of reproducibility may indicate low measurement variation caused by operators, given other conditions of measurement are constant. However, reproducibility can also refer to any changes in other conditions. The final step in calculating the GR&R value is to determine the overall amount of measurement system variation. You do this by combining the values for repeatability and reproducibility. But first, you must convert the values found for them from standard deviations to variances. This is done by squaring the standard deviations and adding them together. Referring once again to the steel pin example, the calculation would be measurement variation equals 0.82 squared plus 0.077 squared, or 0.6724 plus 0.0059, which equals a measurement variation of 0.6783. Taking the square root of this variance value yields the measurement system's standard deviation of 0.824. Next, you will want to evaluate what you have learned. Two analytical methods allow you to analyze and interpret measurement system capability, and both rely on the overall standard deviation. Both methods express measurement system variation as ratios. They are the precision to total ratio and the precision to tolerance ratio. Precision to total ratio describes the total standard deviation that is accounted for by measurement standard deviation. It's expressed as a percentage and is found by dividing measurement standard deviation by total standard deviation and multiplying by 100. Generally, this value should not exceed 10%. A value between 10% and 30% could be considered marginal, but a value exceeding 30% is unacceptable. Precision to tolerance ratio describes the measurement standard deviation as a percentage of the tolerance. and allows you to describe how your measurement error is contributing to the variation you observe between specification limits. This method requires you to know what the processes USL and LSL are. The precision to tolerance ratio is found by dividing 6 times the measurement variation by the total tolerance. The resulting value is multiplied by 100 to express it as a percentage. If the resulting value is less than 10% of the tolerance interval, the system is considered capable. A value between 10% and 25% is considered marginally acceptable. A system that returns a value greater than 25%, however, is considered not capable. You should be familiar with these methods from your Greenbelt work, but if you wish to review the precision to tolerance ratio, access the content Precision to Tolerance Ratio after the video. Suppose you now want to assess the measurement system used to measure the steel pins. Beginning with the precision to total ratio, you would find that measurement variance of 0.824 divided by a total variance of 0.6783 yields an unacceptable precision to total ratio of 1.215, or 121.5%. Suppose you want to back this up with another analysis method and calculate the precision to tolerance ratio. Factoring in the USL and LSL for the process of plus or minus 3, you find that 6 times the standard deviation of 0.824 divided by 6 yields a value of 0.824, or 82.4%, which exceeds the recommended maximum of 25%. The system is therefore not considered capable. Conducting a gauge repeatability and reproducibility study can help you determine how much variation there is in a measurement system. Determining how much variance is related to repeatability and how much is related to reproducibility will help you focus your improvement efforts. Measurement system variation can be expressed as a percentage of the total variance using the precision to total ratio. Another informative expression of measurement variation is the precision to tolerance ratio. This is found using the measurement system's standard deviation and the control limits set for the process. The data needed to complete this calculation is collected during the GR&R study. As a general rule, a precision to tolerance ratio of less than 10% is preferred and indicates the measurement system is capable. A value between 10% and 25% may be considered capable, while a value exceeding 25% indicates the system is not. Six Sigma project success is often a reflection of the information on which project decisions were based. Essentially, the more that is known about the processes being improved, the better. Using your measurement system, you can improve the chance that your Six Sigma projects will be successful. The mention of measurement systems often brings to mind production processes and the gauges used to measure their performance. But measurement systems are used to measure performance throughout an enterprise's functional areas in a variety of ways. In addition to production and operations, there are at least 5 other functional areas whose performance is measured in one way or other: research and development, engineering, marketing and sales, both internal and external customer satisfaction, and supply chain management. Measuring key performance indicators in various functional areas will expand your understanding of your enterprise's performance. Measures of performance in functional areas are usually expressed in percentages or through visual formats such as timelines or graphs. Possible ways to measure enterprise performance include using automatic counters, computer-generated reports, internal and external audits, supplier assessments, management reports, internal and external surveys, as well as various feedback reports. Even within a production context, you can measure a wide variety of items as indicators of performance. For instance, you may choose to measure the capabilities of key machines and processes, machine downtime, average cycle times of key product lines, production control, and the adequacy of operator training. Research and development, commonly referred to as R&D, is one functional area in which performance can and should be measured. R&D is primarily concerned with developing new products or services, improving existing product or service features, and also the performance of the processes that produce products and services. There are a number of ways an organization can measure the performance of the R&D functional area. Are new product development projects justifying their investments? To find out, Return on investment, ROI, can be calculated for these projects. A viable ROI in development projects is one potential indicator that the R&D department is performing well. What proportion of the R&D department's projects have remained on budget in the last year? How many of its in-progress projects are currently on schedule? Calculating the percentage of within-budget or on-schedule projects can provide one indicator of the department's performance. R&D expenditure as percentage of total sales revenue is also a measure of performance. Many organizations set a certain percentage of their annual sales revenue toward meeting the R&D requirements of the organization. Executive leaders view this percentage metric as a measure of the cost efficiency of the R&D function. Moving through the functional areas of the enterprise, engineering is next. The engineering department is mostly concerned with the creation of products and processes. Some of the examples of engineering tasks include project controls and designing tolerance and capability specifications. You can use several measures to assess the performance of the engineering department. One of the key engineering tasks is setting up the production process that will generate the product. Good engineering will result in products that are defect-free and meet technical specifications. Therefore, product performance can be a good measure of engineering performance. Frequent requests for correction to a process or product result in delay, wastes, and unplanned overhead costs. So, the number of requests for corrective action is measure of performance. The fewer the requests, the better, generally reflecting good performance on the part of the engineering department. While it's preferable to have no need for corrective actions, mistakes and defects are bound to happen. The efficiency of responses to requests for corrective action, both in terms of the speed and the quality, can provide a good measure of the engineering team's performance. Measurement of various product and process characteristics is an essential activity in production, and one role of engineering is to ensure that measurement systems are working fine and are free from any inaccuracy or defect. Measurement system performance is another indicator of the engineering team's performance. Continuing through the enterprise, marketing and sales is another functional area whose performance you should measure. The marketing and sales area focuses on identifying markets, targeting and branding, advertising and PR, prospecting, making sales, and supporting customers. Some of the more direct measures of marketing and sales effectiveness include the following: finding sales growth per time period and calculating the ratio of sales dollars generated to marketing dollars spent. Comparing your market share to that of your competition, measuring how much time customers spend exploring pages of your website, and determining the quantity and quality of your leads are also measures. Determining the quality and quantity of your leads is an activity that requires special consideration. Many companies focus on the end result, successful sales, when measuring the performance of their marketing and sales departments, often neglecting opportunities to examine the performance of the sales process itself. When measuring a sales process, you need to measure all the key activities as well as the results of those activities that lead ultimately to sales. Best practices derived from this study can be shared or become sales guidelines to manage and improve your overall sales process. For instance, suppose a custom software provider wants to measure its sales process and creates a flow diagram of the sales process for custom software solutions. The activities are broken down, and the relationships between them are indicated with lines and arrows. As sales activities are performed, the number of customers involved in the process falls. While some of this is inevitable, each decrease in count represents the potential for improvement. For instance, a considerable number of leads are lost between the number of customers who recognize the need for custom software, 440, and the number who attend the web conference, 110. Having identified this, the company can focus on improving that part of the process. At each point in the flowchart, it is helpful to consider both the quality and the quantity of potential leads, and to identify factors that make a customer more likely to stay with the sales process until the sale is finalized. Some of these factors are within the organization's power to improve. Now consider customer satisfaction, another functional area where performance can be measured. In any organization, the customers to satisfy include both internal and external customers, and their satisfaction has both an objective and subjective component. Both components are measurable, and have a significant impact on the overall performance of the organization. The objective component of customer satisfaction refers to customer requirements that are clearly and objectively communicated by the customer. These are the things your customers expect from your products or services, and without them, they'll go elsewhere. The subjective component of customer satisfaction refers to things the customer would like but does not expect. Often referred to as customer delights, subjective components help you exceed objectively stated requirements and achieve not only customer satisfaction, but also customer loyalty. Achieving customer satisfaction requires a knowledge of what your external customers expect and desire. It begins with an understanding of current satisfaction levels. You can measure external customer satisfaction in several ways. You can determine customer retention statistics or survey levels of customer satisfaction with your products or services. You can also compare customers' perception of your products with their perception of competitors' products in terms of fulfilling customer needs. Knowing what your internal customers expect and desire and measuring their satisfaction is also important. Perhaps one of the biggest influences on overall performance is employee satisfaction. You can measure internal customer satisfaction in various ways as well. First, you can survey your employees' level of satisfaction with the company and job. Evaluating the fairness of your company's advancement policies and techniques is another measure. And you can collect feedback on company policies and procedures as well. Finally, the last of the 5 key functional areas whose performance you should measure is supply chain management. All the components of your supply chain are interrelated, and problems with any one of them can impact total supply chain performance. This interrelated nature means that in order to effectively manage your supply chain, you need to be able to measure each component and know how each component affects the others. You must also be able to accurately measure cycle times and inventory. You can measure supply chain performance in a number of ways. The delivery performance of the supply chain can be enhanced by reducing the lead time. A lead time comparable with the best in the industry enhances the probability of on-time delivery to the customers at the other end of the supply chain, and is therefore a good measure of supply chain performance. An efficient and cost-effective supply chain drives down the waste and inefficiencies and ramps up the inventory flow. Your analysis of the current cost structure can reveal that certain components of the supply chain either negatively or positively contribute to the overall product or service costs. Analyzing the ratio of various component costs to total costs is therefore one way to measure supply chain performance. Capacity utilization at the various steps in a supply chain directly affects the cost, speed of response to customer demand, and deliverability. Capacity utilization data at various levels of activity can reveal the potential for reducing or utilizing the unused capacity in the supply chain, and thus serves as a measure of supply chain performance. Even though it's common to think of measuring performance in a production context, performance can be measured for many other functional areas of an enterprise as well. Measurement systems can be developed and used in research and development, engineering, marketing and sales, customer satisfaction, and supply chain management. Measuring performance in all these areas can help you achieve Six Sigma products. In contrast to manufacturing, measuring performance in a service context requires some special considerations. Your ability to improve performance will be greater if you establish operational definitions, analyze your process and measurement systems holistically, and investigate all signals of unusual process behavior to determine their significance. Establishing clear operational definitions, the first special consideration, is crucial to your measurement success. Because many service industry terms such as responsive, knowledgeable, or professional can be subjective, it's hard to be sure what they really mean. Operational definitions provide a standard against which terms can be defined and measured. This has several advantages. It provides a common understanding, sets the expectation for actions and outcomes, and provides a way to measure progress or performance. The need to analyze your measurement systems holistically, the second consideration, is necessary because unlike manufacturing, where parts or units can be measured independently, service processes are made up of many interrelated inputs and outputs that impact one another. And measurement problems in any one of these can have impacts throughout the process. In a service context, you must consider the process, not just the output. Consider the example of booking a service call. Factors that might impact the call's outcome could be the knowledge and experience of the agent, the availability of appointments, or the suitability of available appointments to the customer's liking. If the booking system is not up to date, it could be providing inaccurate information about availability. Or perhaps a technical problem prevents the customer from even getting through. All of these inputs and outputs have a combined impact on the call and can affect the outcome. Measuring upstream events and isolating root causes of measurement variation will help improve your measurements and are activities that should be built into your measurement system. They will help you to holistically analyze not only your service process, but also your measurement system. If you measure all upstream events, not just outcomes, you will be better equipped to assess your system holistically. If you only measure the outcomes, you can't improve measurement system or process performance because you have no clear understanding of what is impacting outcome measurements. A holistic measurement approach will help you to isolate the root causes of both measurement and process problems, which you can then take action to reduce or eliminate. Effectively measuring process improvement requires a reliable process performance baseline to compare future measures against. Just as in manufacturing, it is vital that teams and service organizations analyze their measurement systems. In a service industry context, measurement error may take many forms, including defect judgment error, poor agreement between measurements, service quality categorization error, incorrect output data or faulty results, inaccurate cycle counts, and inaccurate forecasting. Cause and effect diagrams can help isolate the root causes or sources of measurement errors. Factors that can cause measurement problems in a service context include inadequate training, too much subjectivity or lack of standardization in the measurement system, inadequate measurement granularity or resolution, ambiguous measurement goals, dependence on manual rather than automated measurement, and measurement mistakes due to human fallibility, and due to emotional or physical factors causing poor observation. Just as in manufacturing contexts, service providers can analyze their measurement systems too. Measurement systems analysis in the service industry involves assessing the familiar suite of measurement correlation factors, including discrimination or resolution, repeatability, reproducibility, stability, linearity, and bias. Because the system must be capable of providing the details the improvement team needs, the discrimination, or the level of resolution of the system is an important consideration. For example, if a process improvement goal is set to reduce dropped calls per hour by 20%, but the measurement system is based on date-stamped data and therefore only capable of measuring dropped calls per day, the system's resolution level may have to be increased so that improvement can be detected on a per-hour basis. When two people make different decisions and take different actions based on the same data, it may be due to different results drawn by these people from the same data, a reproducibility error. When one person measures the same thing twice yielding two different results, it's a repeatability error. Operational definitions, well-defined criteria, and uniform data collecting procedures help to standardize the judgments and interpretations made by various evaluators measuring aspects of a service process, and thus enhance repeatability and reproducibility. Because human beings almost invariably introduce some variation when repeating or reproducing an activity, it is also good to support manual methods with automated data collection where possible. A measurement system that is unstable over time will give measurements that cannot be compared over time. For example, the frequent revision of data collection forms can make it impossible to measure process performance against a historical baseline. Similarly, too frequent changes in evaluation criteria, performance, and quality metrics can negatively impact stability. Measuring devices should have the ability to measure consistently over their entire range. An example of a threat to linearity might be a customer satisfaction evaluation form in which moderate responses are well defined and categorized, but the procedure for evaluating extreme responses is not as clear. Perhaps the most obvious source of bias in service industry measurement systems is human bias in the form of measurer subjectivity. Bias can also be introduced by the sampling process or by data collection instruments such as forms that fail to capture the complete data and only record information pertaining to a part of the measurement goal. Now that you are thinking from a process point of view, have operational definitions to measure against, and have identified and eliminated as many sources of measurement error as possible, you can focus on understanding the variation in your process. To examine variation, Six Sigma practitioners in the service industry can make use of a tool that is already widely used in manufacturing, the control chart. For instance, an X-bar and R, or IMR control chart, can help you understand the variation in your service process and indicate whether or not your process is in control. For example, an IMR control chart that plots sales for a department over several months. Data points indicate process behavior, and in a normally behaving process, all the data points fall within the control limits. Noise, the result of common cause variation, is always present and is considered acceptable for a process. Signals, the result of special cause variation, are patterns that indicate that points do or may soon fall outside control limits. Signals indicate that the process is not in control and not behaving normally. In service industries, as in manufacturing, it's very important to look for signals because the aim is to keep process behavior within the normal range. Because not all special cause variation warrant an immediate action, investigating all signals of non-normal process behavior before acting is crucial. Say you investigate a drop in monthly sales and find that your top seller was away that month. This variation wouldn't require your attention. Knowing what is causing the variation helps you determine its importance. A further investigation of the signals often leads you to opportunities to improve your processes. Special cause variations are generally considered undesirable and indicators of a process that is out of control. But they are not always due to negative events. For instance, even though you don't want to have variation in your service process, a sudden increase in sales numbers or customer satisfaction should activate your curiosity about what caused those positive effects. You may even wish to incorporate those causes into your process to improve it, creating a new baseline with a new normal range. Analyzing measurement systems in the service industry requires some special considerations to be made. Establishing clear operational definitions will improve your measurement system's ability to measure performance in an industry where the activities and results of processes can be subjective. Assessing measurements throughout the entire process, not just at its output, is important because service processes have so many interrelated inputs and outputs. Measurement problems in one area will most likely have an impact on measurements in other areas. Finally, you need to investigate signals that the process isn't behaving as it should before you act to eliminate special cause variation. Investigating these signals will help you determine whether the variation is important and needs to be addressed or not. Basic statistics are very useful for summarizing and presenting large amounts of raw data, making it easier to understand. Descriptive statistics summarize or describe the basic features of data collected in a study. Descriptive statistics, also known as enumerative statistics, involve data you can count or measure. Examples include summaries of such things as income, age, populations, and test scores. You can use the various graphical tools associated with descriptive statistics to present the data you've gathered in a readable format. You can also apply descriptive statistics to your data to summarize and describe trends, such as averages and ranges. Because collecting data on every item in a large population is rarely possible, your data is likely to be sample data, taken from a smaller set of the population. You can then go on to make inferences about the population based on your sample data. You can check the validity of your inferences and evaluate, interpret, and make predictions about the population. These activities come under the heading of analytical or inferential statistics, which will be covered later in this course. You can apply two main categories of descriptive statistics to a given data set: measures of central tendency and measures of dispersion. Measures of central tendency are measures of the location of the middle or the center of a data distribution. These include the mean, median, and mode. Dispersion, or spread, is the degree to which the data varies around one of the central tendency points, usually the average or mean of the data. Dispersion is typically measured as range, standard deviation, or variance. If you use only one of the measures of descriptive statistics, you'll only get partial information about your sample data. Using measures of central tendency as well as measures of dispersion provides you with more information. For example, two data sets may have an identical mean, but their respective data points may be spread around that mean in different ways. Or, alternately, you might have two data sets that are spread out in the same way. However, on closer examination, you find they differ on measures of central tendency. You can use measures of central tendency as well as measures of dispersion to analyze both discrete and continuous data. Discrete data, also known as attributes data, typically involves a finite number of values, for example, counting things using whole numbers. In other words, discrete data is not a measurement, but a count. You're using discrete data when you gather population data by counting people and putting them into various categories. Continuous data, or variable data, can be measured on an infinite scale. This means the measurements could conceivably take on any value. Measures of time, height, pressure, and temperature are examples of continuous data. The distinguishing feature of continuous data is that you can measure it on a scale, whether numeric or incremental, and the values can lie anywhere on the scale. You can break a continuous variable down into smaller and smaller units, and the resulting fractions are still meaningful. You should already be familiar with the methods for calculating the mean, median, and mode from your Greenbelt training. You can access the content of Measures of Tendency after this video to review the 3 calculations of central tendency. The mean is the arithmetic average of the values in a distribution. It is a commonly used measurement because it describes normal distributions well, and also because it is useful for generating many other statistics. The median is the distribution's center point after it is originally sorted. An equal number of data points lie on either side of it. The mode is the distribution's most common value. The mode is simple to determine and fairly effective with small samples. Each measure of central tendency offers particular advantages for calculation and assessment, and each measure also has its drawbacks. Advantages of the mean include representing the center of gravity and using all of the available data. It is the most commonly used measure of central tendency. You don't need to sort or arrange the data first to calculate the mean. Some limitations include exceptional and extreme data measures distorting the complete picture because all the data points are used in the calculation of mean. It can be time-consuming to calculate the mean for large or complex data sets. And the mean may not be the actual value of any data points. The mode is the only measure of central tendency that can be used with qualitative or non-numeric data. For example, your statistical analysis might involve non-numeric information about gender or race. Using the mode as a measure of central tendency offers several advantages. No calculations or sorting is necessary, and the mode isn't influenced by extreme values as the mean is. The mode is an actual data value and, unlike the mean and median, is easy to detect visually in distribution plots. Using the mode has limitations as well. Your sample data may not have a mode, or your data set may have multiple modes. This can make the mode difficult to use in analysis. It's possible to have bimodal and trimodal data sets. This refers to 2 or 3 modes when several different measurements occur the same number of times in a given data set. Using the median as a measure of central tendency has several advantages. The median provides you with an idea of where most of your data is located. Like the mode, the median is easy to calculate and is insensitive to extreme values. Using the median as a measure of central tendency has its disadvantages. Finding the median involves sorting and arranging the data, which can be time-consuming. Extreme values may be important in your analysis, but the median will not detect these. Also, 2 medians can't be averaged to obtain a combined distribution median. If you have more than one median, the result is almost useless. Finally, the median typically varies more from sample to sample than the mean does. Therefore, the median isn't as true of an indicator as the mean is. In a skewed distribution, the three measures for the median, mode, and mean are different. In a normal distribution, the median, mode, and mean are identical. Elaine, a math teacher, learned firsthand the relative advantages and limitations of calculating each measure of central tendency as she processed her students' test scores. 10 students took a math test that scored a maximum of 10 points. The mean is the most widely used measure of test performance in the school, and it allows Elaine to easily compare results with other teachers and students. The mean is the arithmetic average of the values in a distribution. One limitation of this measure is that the mean, 6.8, is not one of the actual test scores in the data. Also, one student handed in the test without answering any questions. This significantly affects the class average, making it seem like the class is performing poorer than it really is. The median is the distribution's center point. Elaine needs to first sort and arrange her data. If she had 100 tests to score, this would be very time-consuming. After Elaine sorts her data, calculating the median is easy. The center point of the distribution is between the numbers 7 and 8. The median test score is 7.5. From this, Elaine knows that half of her students' test scores lie on one side of the median and half lie on the other. If the median is a fairly high score, Elaine knows that half of her students performed well on the test. If the median is low, she knows that 50% of her class scored below an unacceptably low value. This might give her an indication of how fair or difficult the test was. The mode is the distribution's most common value. Elaine doesn't need to perform a calculation or sort and arrange the numbers. She determines that the number 9 is the mode, since this score occurs most frequently. It's not always possible for Elaine to use the mode to measure test results. Sometimes the test scores don't have a most common value, or when several students have identical scores, there may be more than one mode. Calculating measures of dispersion is another important way of describing a data set. Dispersion refers to the spread of data around the mean, or the spread of values around the central tendency. Suppose an average test score is 75%. The dispersion is the range of values above and below this number. Measures of dispersion are necessary because measures of central tendency don't tell the whole story about a particular set of data. To avoid making the wrong conclusions, you need to know how data is spread around the mean. Consider the scenario of crossing a river. You happen to know that the river has an average depth of 4 feet, but this doesn't mean you can safely walk across the river. Knowing that the average depth is 4 feet doesn't give you a complete picture of the river's depth. Averages can be misleading if your data contains extreme measures. In this case, the river has an extreme depth of 8 feet, so you won't be able to walk across it. The two common measures of dispersion are the range and the standard deviation. The range is the highest value in a set of data minus the lowest value. An advantage of using the range is that it's very easy to calculate. However, the range can be misleading because you compute it using only the two extreme values of a data set. The range completely ignores all of the other values. Consider this example. Mark is calculating the range for a data set of student test scores. The highest test score is 98. The lowest test score is 65. So the range is 98 minus 65, which equals 33. A disadvantage of this measure is that an outlier value can exaggerate the range. In this example, note how 98 stands apart from the other values. The high value of 98 makes the range much larger than it would be without this outlier. As you should already know from your Greenbelt training, the standard deviation is a more accurate and detailed measure of dispersion. It's useful for helping you measure how much each value actually varies from the mean. The standard deviation of a sample is typically used to estimate the standard deviation of the population. Mark is now calculating the standard deviation for his dataset of student test scores. He uses the standard deviation formula. Standard deviation for a sample is equal to the square root of the summation of the squared differences of all scores from 1 to n from the mean, divided by n minus 1, where s represents the sample standard deviation, square root represents square root, Sigma, or summation of, represents the summation of. X subscript I represents a score in the distribution. X bar represents the sample mean, and N is equal to sample size. This can be evaluated using the following formula. S equals the square root of the outcome of the expression sigma x subscript I minus x bar raised to the power of 2 divided by n minus 1. Mark's dataset is 98, 85, 80, 80, 75, 70, 70, 65. Mark has already calculated some of the formula. He knows the value of the mean is 77.88. He then sets up a table to calculate the value of each test score minus the mean. He squares all of these values and adds them together. He adds the results in the last column and gets a total of 762.88. For the denominator, he subtracts 1 from the sample size of 8, giving him 7. Then, he calculates the variance by dividing 762.88 by 7, which is 108.98. Finally, to find the sample standard deviation, Mark takes the square root of 108.98. The standard deviation for his dataset of test scores is 10.44. He finds the standard deviation useful because he knows how much each value in his dataset actually varies from the calculated mean. He can also use this information to calculate the variance. Variance is simply the formula for standard deviation squared. Because the differences are squared, the units of variance are not the same as the units of data. Therefore, the standard deviation is reported as the square root of the variance, and the units correspond to those of the dataset. The measure of variance is central to Six Sigma projects where the focus is on reducing variance to improve processes and cut costs. Calculating these measures of dispersion is a critical skill for both green belts and black belts as they work with descriptive statistics. You can access the content on measures of dispersion after this video if you wish to further review the 3 measures of dispersion. The coefficient of variation is simply the standard deviation expressed as a percentage of the mean. Because it is a ratio, the coefficient of variation can help you to compare the variability of 2 datasets, even if the means and the standard deviations for the datasets aren't the same. If one sample's dataset has a higher coefficient of variation than another, its standard deviation is larger relative to its mean, which points to greater variability in the sample. In these examples, the means and standard deviations have already been calculated. To calculate the coefficient of variance for each dataset, divide the standard deviation by the mean. A higher coefficient of variance indicates higher variability. For set A, the standard deviation of 2.4 divided by the mean of 7.8 equals 0.3. For set B, the standard deviation of 3.4 divided by the mean of 7.4 equals 0.5. Therefore, set B has the higher variability. Descriptive statistics summarize or describe the basic features of data collected in a study. The 3 measures of central tendency are the mean, median, and mode. Each of these measures have characteristic advantages and limitations. Measures of dispersion refer to the spread of values around the central tendency. The 2 common measures of dispersion are the range and the standard deviation. Variance and the coefficient of variation are other useful measures of dispersion. You can access the job aid Measures of Central Tendency and Dispersion after the video to review the definitions and formulas for these common measures. When you organize raw data in a meaningful order, it's easier for you to recognize patterns in the data. One of the preliminary ways to arrange data for analysis is to use a frequency distribution table. A frequency distribution is a list of the values that a variable takes in a sample. Frequency distribution tables show the values ordered by frequency. For example, you can use a frequency distribution table to show how often a park is visited over a period of time. There are various sources of data and various collection methods and tools for gathering the data that goes into frequency distribution diagrams. Also, there are several graphical presentations that can be prepared using the data in a frequency distribution diagram. Collecting data in a check sheet is one way to compile a frequency distribution table. The frequency distribution table can then be used to create a histogram. First, there are sources of data. A check sheet is a simple form used to keep a tally of data recorded over a period of time. You can customize your check sheet to collect data on specific categories and frequency of events. You can also compile a frequency distribution table by using other techniques, such as observation, surveys, interviews, and other data collection tools. A frequency distribution table can be used as a graphical presentation, such as a histogram. A histogram is a specialized form of bar chart that depicts a frequency distribution. It shows the number of the individual instances that fall into each of several specified categories. Other common visual tools include line charts, pie charts, two-directional bar charts, and trend analysis. You should be familiar with creating frequency distribution tables from your previous Greenbelt training. You can access the content on frequency distribution tables after this video to review the steps for constructing a table. Data is grouped into class intervals if the frequency table becomes too large for organizing, interpreting, and analyzing the data. The frequency of a class interval is the number of data values that fall in the range specified by the interval. It's important to choose class intervals of an appropriate and meaningful size for your frequency distribution diagram. The procedure for determining class intervals involves 3 steps. The first step is to determine the range of the distribution. The second step is to determine the number of class intervals. And finally, the third step is to determine the range of class intervals. Consider the example. Mark, a Six Sigma black belt, is determining the class intervals for customer complaints per day. The first step is to determine the range. He begins by organizing data in an ascending or descending order. Next, he identifies the highest and lowest data points. The highest data point is 32 and the lowest data point is 11. To determine the range of the distribution, he subtracts the lowest value from the highest value. The range of Mark's distribution is 21. He determines the number of class intervals by using the following general rule of thumb. If the number of data points is greater than 100, he will use between 10 and 20 class intervals. If the number of data points is less than 100, he will use between 5 and 10 class intervals. Mark's customer complaint sample has 30 data points, so he will use between 5 and 10 class intervals. He chooses 8 as an appropriate number of intervals for his frequency distribution table. He determines the range of class intervals by dividing the range of the distribution, 21, by the desired number of classes, 8, to get 2.63. Rounded up, this equals a class interval range of 3. It's important to choose an appropriate number for your range of class intervals. The number that you choose for the range, or class width, must accommodate all of your data points. Each class must also be unique, so that data points can belong to only one class. To ensure that the results of your frequency table are accurate, your class values should not overlap. You must be able to divide the lowest class interval's lower limit by the value of the class interval range. If you can't, you need to select the next lowest point that is divisible by the class interval range. This ensures that the lowest class interval does not end up with a smaller range than the other class intervals. In your customer complaint sample, 9 is used as the lowest class interval's lower limit because 10 is not divisible by the class interval of 3 without a remainder. Once you've determined the class intervals for a dataset, you can complete the frequency distribution table. Simply insert your class interval and class frequency data into the respective columns and rows. Cumulative frequency describes how much of an overall distribution is accounted for up to a given threshold. It's common to hear statistics such as 20% of people look forward to traveling, or 30% of people want to be more physically active. These are cumulative percentages because they describe the percentage of items up to and including a certain threshold. You can use a frequency distribution table to calculate cumulative frequency. This involves adding columns to the table for additional information on cumulative frequency and cumulative percentage. In this example, 2 columns have been added to the table for cumulative frequency and cumulative percentage. To find a cumulative frequency, you total all frequencies up to the point in question. To calculate the cumulative percentage of a row, you first take the cumulative frequency of that row and divide it by the total number of values in the dataset, or n, multiplied by 100. You should already be familiar with this material from your Greenbelt training. You can access the content on cumulative frequency tables after this video to review how to create these tables. A stem and leaf plot is another form of check sheet that you can use to show frequency distribution. This type of diagram, unlike most other graphical methods, is used for classifying and organizing the values during data collection rather than after the fact. Both the raw data and the distribution of the data are shown in the stem and leaf plot. You create the basic stem-leaf structure by dividing the numbers in a dataset into stems and leaves. The stems are made up of all digits of the numbers except the last. In a dataset of numbers such as 0.28, 0.39, 0.42, 0.52, and 0.66, the stems are 0.2, 0.3, 0.4, 0.5, and 0.6. The leaves of the diagram are the final digits of each number. So in the case of the previous dataset, 0.28, 0.39, 0.42, 0.52, and 0.66, the leaves are 8, 9, 2, 2, and 6. You can create a stem and leaf plot by making a table with 3 columns labeled stems, leaves, and frequency. Add an appropriate number of rows to accommodate the data in your sample. Stem and leaf plots offer a quick comparison between the distribution of values in different data samples. They also allow a quick overview of the relative density and shape of data distributions. Stem and leaf plots are also useful for highlighting outliers. As with many summary techniques, stem and leaf plots are not useful for very small or very large datasets. Small datasets don't have enough values to present a useful picture, and large datasets are cumbersome to present in this manner. A stem and leaf plot can also be shown in a vertical format. The numbers on the bottom are the stems. The numbers on the top are the leaves. One of the ways you can arrange data is to use a frequency distribution table. A frequency distribution table shows values ordered by quantity and frequency. You can then use this table to present information in a graphical format, such as a histogram. You can use a frequency distribution table to calculate cumulative frequency. Cumulative frequency describes how much of the overall distribution is accounted for up to a given point, or threshold. This frequency can be used to determine a cumulative percentage. Stem and leaf plots are a form of check sheet that are used to show frequency distribution. Actual data values are recorded so that the raw data is maintained and the distribution of the data is also shown. The basic stem-leaf structure is created by dividing the numbers in a dataset into stems and leaves. The stems are all of the digits except the last digit, and the leaves are the last digit. To express how effectively an image can tell a story, it's often said that a picture is worth 1,000 words. This phrase also characterizes the goals of visualization, where large amounts of data must be absorbed quickly. Visual tools such as charts and graphs are an effective way to represent the distribution of data. Graphical tools enable your audience to quickly pick up the trends in complex data. Data trends can often be better understood when the data is presented in a graph rather than in a table. For example, while frequency tables can adequately document and categorize information, graphical methods go a step further to convey the general form of a data distribution. Different graphical methods highlight different types of trends. These methods include histograms, dot plots, probability plots, bar charts, scatter diagrams, run charts, and box and whisker plots, among others. Frequency diagrams are graphical tools used to display raw data in visual form and help teams to focus on the primary causes of problems. Histograms and dot plots are commonly used types of frequency diagrams. A histogram shows you where variations occur within a frequency distribution. Variations may occur grouped together within a narrow interval, or be evenly spread out over a wide range of values. A histogram also shows you how frequently various values occur and provides clues to the sources of variations. You should already be familiar with histograms from your Greenbelt training. You can access the content about histograms after this video if you wish to review the features and patterns of histograms. A histogram lets you identify the shape of a set of data, where its center is, and how far it spreads out on either side. Keep in mind that creating a histogram requires sufficiently large number of data points depending on the nature and requirements of your process. A sufficient number of data points is required to provide an accurate shape to the distribution. The procedure for creating a histogram involves 4 steps. Step 1 is to draw a horizontal line to represent the scale of measure for the data you're graphing. Then, Step 2 requires you to divide the horizontal line into 10 to 20 equal buckets between the maximum and minimum values. Buckets can mirror the class intervals from the frequency diagram. Followed by Step 3, which is to place a dot for each data point in the corresponding bucket along the horizontal line. You may find it useful to group all of the dots that occur within the same bucket in one step. To create a histogram, you simply replace the grouped dots with a bar of the same height. Finally, Step 4 is to repeat the third step until you've placed a dot on the histogram for each data point. You can use a histogram to determine if a frequency distribution has a relatively normal bell-shaped curve. If there are wide variations in frequency distribution values, the histogram will be flatter. You can also use a histogram to determine if a change has taken place in a process, or to compare the output of 2 different processes. A histogram that displays a normal bell-shaped curve is usually associated with a predictable, stable process. When a histogram has a normal curve, the variation around the bell curve represents chance or natural variation. Interpreting a histogram involves examining the mode, mean, range, and outliers for basic patterns. The mode is the tallest peak of the distribution. Examine your histogram to determine if there is one peak or multiple peaks, and where peaks are located. Examine the horizontal axis of your histogram. If you placed a straight line on the graph, which column would appear to act as the pivot point? This point represents the approximate location of the mean. As this example represents a normal distribution curve, the median, mode, and the mean are the same. The range is the distance along the horizontal axis and equals the maximum value minus the minimum value. So in this case, the range is 12 minus 2, or 10. Examine your histogram to determine if the data contains any outliers. Outliers are specific points that don't seem to fit the grouping of the rest. Outliers may either be too far to the right or too far to the left of the rest of the data to be concluded as coming from the same set of circumstances that created all the other points. This example does not have any outliers, and the variations are normal. A non-normal shaped histogram may represent a problem or an unstable process. You should investigate any significant deviation from a bell shape to determine if there is a problem. You can add upper and lower specification limits to your histogram to examine how a process is performing. Upper and lower specification limits highlight data that lies outside of accepted limits. Histograms can deviate from the normal curve in various ways, revealing particular patterns of process behavior. A histogram with special causes, or a process histogram, may differ from a bell-shaped curve due to special causes of variation that may be present in a process. These special causes can have an impact on the shape of the histogram. For example, a process other than the one you are studying may be affecting the shape of your histogram. In a histogram with special causes, some columns are higher or lower than normal, which can indicate a problem. A faulty component in a piece of machinery or low-quality materials are examples of special causes. Special causes should be investigated. Then, a bimodal histogram is a bimodal or two-peak pattern, meaning that while the data may seem to come from the same process, 2 processes are actually at work. This problem can occur if 2 different processes are intermingled in the data. For example, data from 2 shifts, 2 different machines, or 2 different measuring devices. You must separate the data associated with each peak by stratifying the data. You'll then be better able to examine each process separately. A negatively or positively skewed histogram is a strong indicator that a problem exists in the process. In a skewed distribution, your histogram will have one tail longer than the other. The graph appears as an uneven curve, and values taper to one side. In a positively skewed histogram, the tail extends to the right, and the distribution is said to be right-skewed, while in a negatively skewed histogram, as the one shown in the example, the tail extends to the left, and the distribution is said to be left-skewed. A skewed distribution can occur because a natural limit prevents outcomes on one side. For example, there may be sizes or call times that can't be less than 0. Then, pile-up at spec limit histograms are comprised of data points that pile up suspiciously close to one of the upper or lower specification limits, and may indicate that someone is letting out-of-spec items pass as in-spec. For example, a supplier or an employee may be allowing out-of-spec items to be counted as within spec. While many deviations of normality point to problems or instability in the process, several non-normal distributions also represent stability. These are beyond the scope of this course, but you should be aware that where data is found to assume one of these distributions, the data can be transformed mathematically so that it becomes normal, or the presumption of normality can be laid aside and the data can be analyzed according to the properties of that non-normal distribution. Some of the distributions used include exponential distributions, log-normal distributions, gamma and beta distributions, Weibull and Poisson distributions, binomial distributions, and hypergeometric and geometric distributions. A Six Sigma team at a greeting card manufacturing company is preparing a histogram to present to management. The data gathered from the analysis will be used to help establish prices for various product categories. As a first step, the team gathers information from a frequency distribution table. Then, using the data from the frequency table, Six Sigma team members perform the 4-step procedure you learned earlier to create a histogram. They use 7 intervals, expressed in dollars, as the values for the x-axis of their histogram. They record the frequency of each data point in their data set on the y-axis. Six Sigma team members analyze the resulting histogram to determine what kind of distribution shape it has. The distribution shape allows them to obtain certain information quickly. For example, they can quickly identify that the distribution is positively skewed because the tail extends to the right. Why is this? To find out, they observe that more items cost between $1 and $1.49, but items with higher costs have more varying class intervals. The team includes this information in its analysis. A dot plot can reveal substantial information about the nature of a variation. In this cycle time plot example, the distribution appears somewhat bell-shaped. Most of the cycle time measurements are clustered around the middle of the distribution, with the frequency of occurrence trailing off as you move farther out from the middle. The mode and the mean are represented by the tallest peak in the dot plot. They're located in the same bucket and have an approximate value of 8.2. You can check your rough visual estimate by mathematically calculating the mean. To do this, add all of the cycle times and divide by the number of values. You can easily determine the range in the dot plot. The cycle time measurements range from a high value of 12.5 to a low value of 4.6. So the range is 7.9. Are there any outliers in the data? To find out, look for any data points that appear far outside of the normal distribution. In this case, the data does not have any outliers. Many of the inferential statistics you will use to later analyze your data presume a normal distribution. You can use probability plots as a visual check to assess whether or not your dataset has a normal distribution. Normally distributed data will yield a straight line when plotted as a normal probability plot. In a probability plot, the x-axis shows the observations, or data values, and the y-axis represents the cumulative frequency at each point. Because the calculations can be cumbersome, probability plots are typically done using software, but it is possible to manually plot your data to check its normality. Before you can calculate cumulative frequencies, the observations must be put in ascending order. Each observation is plotted against its cumulative frequency. A shortcut in calculating cumulative frequency is to divide the amount of overall distribution accounted for up to that point by the sample size plus 1. In this example, you have a list of data values that you want to visually examine on a probability plot. First, you put the observations in ascending order and plot them on the x-axis. Then you calculate cumulative frequency for each data value. Finally, you plot each observation against its respective cumulative frequency. When it's time to assess the distribution, you judge it to be normal only if the resulting plot forms a straight line. If the plotted points deviate significantly from the straight line, especially at the ends, then the data does not fit the normal distribution, as you may have hypothesized. The fat pencil test is a good rule of thumb. You place a thick pencil or similar straight item over the line created by the dots, and if the pencil obscures almost all of the data points, the distribution is approximately normal. Based on the normal probability plot and the results of the fat pencil test, the distribution in this example is judged to be normal. You can access the content on probability plots after this video to review basic features and use of probability plots. Graphical methods can convey the general form of a frequency distribution more quickly and easily than a frequency distribution table can. Frequency diagrams, which are the graphic representation of a frequency distribution table, can come in the form of histograms or probability plots. A histogram is one of the basic tools of quality control because it gives a simple, quick, and easy visual display of the center, spread, and skewness of a distribution. Probability plots provide quick and effective checks for the normality of a data set or a sample. Normally distributed data will yield a straight line when plotted as a normal probability plot. Using graphical tools is essential for providing a quick and intuitive view of data, allowing you and your audience to easily spot trends. Graphical tools like bar charts, box and whisker plots, and run charts are valuable for translating data into meaningful information. Bar charts are one of the graphical tools you can use to visually represent trends. Bar charts are used for comparing discrete data and are useful for showing segments of information. When creating a bar chart, you place vertical bars over each horizontal axis category. The height of the bar is measured against the vertical axis to show the frequency of different values. You can also use a double bar chart to show multiple sets of data for each category, using bars of different colors to compare sets of data about the same items. For example, suppose you want to create a bar chart comparing visits to a children's educational website, and you want to break it down by gender and by month. A bar of one color can represent the boys, and a bar of a different color can represent the girls. Pareto charts are based on the Pareto Principle, or the 80-20 rule. In the context of process and quality improvement, this rule states that 80% of a process's problems result from 20% of the causes. These are often referred to as the vital few causes. Pareto charts enable you to target the most significant contributors to a problem in a business process. The Pareto chart is a simple bar graph. Each bar represents a factor that contributes to the problem. The height of each bar reflects that factor's relative contribution. You can access the content on Pareto chart patterns after this video to review this graphical tool. Box and whisker plots are another simple and useful way you can summarize data. The box plot represents data based on a 5-number summary of a data set. The median is a line that divides the box. Minimum and maximum data points are drawn as points at the end of whiskers extending from both ends of the box. The whiskers connect all the values outside the box that are not more than 1.5 times the box width away from the box. There are 5 main points used in a box and whisker plot. The first quartile, which cuts off the lowest 25% of the data set, is the median of the lower half of the data. The median is the value exactly in the middle of an ordered data set. The median, or 50th percentile, is a primary element of a box and whisker plot, as it is used as the reference point for the other elements. The third quartile, which cuts off the highest 25% of the data set, is the median of the upper half of the data. For a small data set, the smallest observation is generally the lowest value in the dataset. For more complex and large datasets with potential outliers, The lower whisker is drawn between the lower boundary of the box and the point that is 1.5 times the interquartile range below the 25th percentile. For a small dataset, the largest observation is generally the highest value in the dataset. For more complex and large datasets with potential outliers, the upper whisker is determined by calculating the point that is 1.5 times the interquartile range above the 75th percentile. You draw a line from the boundary of the box to that point. A vertical mark at the endpoint denotes the end of the upper whisker. You should already know how to construct box and whisker plots from your background in Greenbelt techniques. You can access the content about box and whisker plots after this video to review the steps for constructing a basic box and whisker plot. The graphic power of box and whisker plots goes beyond the 5-number summary. You can also use these plots to convey a more detailed summarization of your data. You can create a more complex and informative version of a box and whisker plot by adding outlier dots, notch widths, and variable box widths to your diagram. You can easily identify outlier dots, which are shown as points or asterisks that lie beyond the reach of the whiskers. To determine the presence of outliers, you first need to find the interquartile range. This is the difference between the upper quartile and the lower quartile values. In this example, it's the difference between 5.4 and 4.8, which equals an interquartile range of 0.6. Outliers are defined as any observation more than 1.5 times away from the closest quartile. In this example, multiplying 1.5 by the interquartile range of 0.6 equals 0.9. Notches display the variability of the median between samples. Notch widths are calculated in such a way that if medians from two different samples have notches that don't overlap, then you can be sure that the means of the two are different at a 5% significance level. This notch width feature is like a visual hypothesis test, allowing you to quickly determine whether two means are statistically different. For a single box plot, the width of the box is arbitrary. However, for multiple box plots, you can set variable box widths based on the log of the sample size. A wider box indicates a much larger sample size than a smaller box. Box and whisker plots provide a graphical summary of some of the most important characteristics of a distribution. Like histograms, box and whisker plots reveal useful information about the shape and concentration of data and easily show the differences between two or more samples. In this example, two box and whisker plots represent two samples of data. The red dots at the end of the whiskers represent the outliers. The first plot has outliers at both ends, whereas the second plot has outliers only for the upper range of data, which means the resulting distribution will be skewed toward one side. Outliers are useful for indicating whether a distribution is skewed and whether a dataset has potential unusual observations. Outliers can lead to investigating possibilities of special cause variation in your process. Because the first column's upper box width is different from the other box's width, it indicates a significant difference in the size of the two samples. Since the notches in the box plot don't overlap, you can conclude that the means of the two medians are significantly different. Run charts, or trend charts, are graphical tools that identify changes in data over time. Since important elements of a process can change over time, run charts can help you to pinpoint time-related patterns or variations. For many business activities, run charts can reveal patterns that indicate if a process is running normally or whether positive or negative changes are occurring. You can access the content on run charts after this video to review the graphical tool. Run charts typically show time values increasing along the x-axis and measurement values increasing along the y-axis. What is considered a positive result will differ depending on the process being studied. A good result might be an upward trend where values are increasing. Conversely, a positive result might be reflected in decreasing values or in values that remain steady and close to targets. There are a number of revealing run chart patterns. An upward trend may not necessarily be a good thing. It simply means there's been an increase in the values over time. Your team might consider this a good result if it was a desired increase, customers served per week, for example. But it might be a troubling trend if reflecting an increase in customer wait times. Whether a downward trend is considered good or bad depends on the particular process that's being analyzed. For example, if the goal of a process is to reduce parts defects over time, you'll view the downward trend as a positive thing. If the goal of a process is to increase sales over time, you'll view the downward trend negatively. You should investigate downward trends for their possible causes. A run chart with a process shift shows a sudden upward or downward change in the center of an otherwise stable process. A process shift occurs when the mean value in a stable process jumps suddenly and then stays at its new level permanently. An example of a process shift would be a deviation that occurs in a process because of a defective component. Unusual values in a run chart can signal that a special cause may be at work. You may observe unusual values in other non-random patterns, showing up as unusual clustering, outliers, and cycles. Continuous or extreme trending in either the positive or negative can be considered unusual if it is extraordinary relative to long-term data patterns. As a rule of thumb, if your run chart shows 7 or more consecutive ascending or descending data points, you should investigate for causes. A cycle or repeating pattern is another indicator of a possible special cause, though in some processes, cycles may be typical and readily explained. It's important to interpret a cycle in the context of the process that is producing it. If you understand why a cycle is occurring in a process, you can predict the process results more accurately. For example, a Six Sigma team was working on reducing shipping errors in the mail order dispatch department at an online retailer. The run chart of the error data for 8 weeks showed a cyclical pattern. On further investigation, the team found that the shipping errors were highest at the beginning of a work week because of the increased workload. Customers generally placed more orders online over the weekends and fewer midweek. As a result, a huge backlog on Mondays led to more shipping errors on the part of dispatchers, followed each week by steady improvement until the next Monday, when error rates would rise again. A run chart with increasing variability shows that, over time, the variation in a process is getting larger. The data won't tell you what is causing the variation, but can help guide you as you make changes to the process. For example, the outpatients department at a large hospital was receiving complaints of longer waiting time from its patients. The data processing department was surprised at this, as the average waiting time hadn't changed at all. However, a run chart of sample waiting time data showed that due to a recent change in the registration process, the variation in waiting time had actually increased considerably without affecting the average much. A pattern with periodic peaks means you need to determine what's different in the process during the time periods of the peaks versus the other times. If the chart indicates that defects occur more frequently on Fridays, this information may help you determine that the department you are investigating is often short-staffed on Fridays. If there's no apparent pattern, it means you've chosen the wrong chart for plotting your findings, and that plotting over time isn't yielding useful information. You can try replotting the data using a different type of chart for a better picture of what's going on with the variation. Bar charts, Pareto charts, box and whisker plots, and run charts are valuable graphical tools for quickly conveying trends. Bar charts are useful for comparing discrete data and for showing segments of information. You can use double bar charts to compare multiple sets of data. Pareto charts enable you to target the most significant contributors to a problem in a business process. Box and whisker plots provide an effective way to depict the central tendency and range of data based on a 5-number summary of a data set and allow you to easily compare samples. Run charts are graphical tools that identify changes in data over time. Run charts can reveal patterns in business activities that indicate whether a process is running normally or whether positive or negative changes are occurring. Scatter diagrams are useful tools for depicting the relationship between two variables. When these variables are plotted on the x-axis and the y-axis, the resulting pattern indicates the nature of a relationship, its direction, and its strength. This information can help you to control the effect of a relationship on a process. If one of these variables happens to be the causal or independent variable, it is represented by the x-axis. The other variable, result, or dependent variable, is represented by the y-axis. Outliers are data points that occur far from the general cluster. If your scatter diagram has only a few outliers, they may represent errors or chance exceptions to a general trend. As you'll recall from your Greenbelt training, a scatter diagram cannot establish or prove direct causal relationships. If a scatter diagram suggests that one variable causes an effect in another, this is actually a correlation relationship, not cause and effect. The slope of the best fit line indicates the strength of the correlation. You can access the content about scatter diagrams after this video to review the construction and use of this graphical tool. The independent variable in a scatter diagram is often a process parameter, such as a setting or condition. The dependent variable is often an output characteristic, such as a product or process result. Suppose that you suspect that press temperature is affecting the tensile strength of plastic sheets in a plastic forming process. To test your hypothesis, you can plot the two variables in a scatter diagram to determine if there is a high correlation. By visually fitting a straight line through all of the dots of the scatter pattern, you can draw a correlation line of best fit. The dots fit closely to the line, if approximately 1/2 are above and 1/2 below the line. You can determine the strength and direction of the relationship based on how slant the line is with respect to the x-axis and the direction of the line. You can calculate a numerical value for the correlation, but this is beyond the scope of this course. You may have a scenario where the sample units come from multiple vendors or machines for the process parameter. In this case, there often appears to be no correlation between the variables. But if you identify sample units by their source, you may find a positive correlation between one of the sources and the dependent variable. Creating unique symbols for each source enables you to identify trends more accurately. In this example, temperature and product rigidity have a strong positive correlation, but only for machine 2. As you're aware, scatter patterns are not always going to reveal a strong positive correlation between variables. Different levels of correlation produce different scatter patterns. A high positive correlation produces a line of closely spaced points up from left to right with the variables moving in the same direction. An increase in the process parameter is related to an increase in the output characteristic. If you can control the process parameter, it's likely that you can also control the output characteristic. A high negative correlation results in a line of closely spaced points descending from left to right with the variables moving in opposite directions. An increase in the process parameter is related to a decrease in the output characteristic. If you can control the process parameter, you can likely also control the output characteristic. When there is no correlation between the two variables, the data points are scattered and don't form any particular line. An increase in the process parameter doesn't have an impact on the output characteristic. If there is no correlation, you can't control the output characteristic by controlling the process parameter. A low correlation, positive or negative, between two variables results in widely scattered data points that form a relatively flatter best fit line. A scatter diagram with a low correlation is not very helpful for controlling output characteristics. The linear relationship between the variables is so weak that it's difficult for you to reliably predict how changing one will affect the other. Sometimes the correlation between two variables produces a nonlinear pattern instead of a straight line. For example, a cliff pattern shows that a significant change in the dependent variable takes place at a certain value of the independent variable. A peaked pattern is a scatter diagram that shows the independent variable has topped off. Scatter plots can be very useful in a Six Sigma initiative. If you understand the relationship between two variables, you can often control the output characteristics by changing the process parameters. You can also determine the optimum setting and tolerance for a process parameter once you've identified it as a key variable. It's important to be able to control the process parameter to meet specifications in many processes. For example, suppose the amount of heat applied to metal containers affects their hardness. You could use a scatter diagram to determine the optimum temperature setting and establish control limits for tolerances. You can follow a 5-step process to determine the optimum tolerance zone and optimum target value for the process parameter. Construct a scatter diagram, draw a straight line through the middle, or median, Draw two parallel lines on each side of the median line, identify the upper and lower specification limits for the output characteristic, and identify the tolerance zone and the optimum target value for the process parameter. The first step is to construct a scatter diagram using a collection of at least 30 data points. Your scatter diagram should show both the process parameter values and the associated output characteristics for each value. The next step is to draw a straight line as close as you can through the middle or median of the scatter pattern. This line is called the median because half of the values lie above the line and half the values lie below it. You can use more advanced statistical techniques for drawing this line. The third step is to draw two parallel lines on each side of the median line. All of your data points should be enclosed within these two outer lines. The fourth step is to identify the upper and lower specification limits for the output characteristic. Draw a horizontal line from the upper limit across to the upper line containing the data points. Also, draw a horizontal line from the lower limit across to the lower line containing the data points. Then draw two vertical lines from the intersection of these lines to the process parameter axis. The fifth step is to identify the tolerance zone and the optimum target value for the process parameter. The two vertical lines that extend to the horizontal axis identify the tolerance zone. This will also mean that the process capability index, CP, equals 1.0, as the process limit conforms exactly to the specification limits for the output characteristic. You can then apply pre-control rules and divide the tolerance zone into 4 equal parts. By accepting only the middle half as the tolerance zone, you can ensure a CP of 2.0. This is important because a process with a value of CP 2.0 or greater has achieved Six Sigma quality. You should set the target value of the process parameter at the middle of these two pre-control zones. In this example, for the CP to equal 2.0, you should set the tolerance range between 162.5 and 167.5 and the target value at 165. You can use scatter diagrams to depict the nature of the relationship between suspected causal variables and dependent variables. This information can help you to control the effect of the relationship on a process. Different levels of correlation can produce different scatter patterns. Scatter patterns can be high positive, high negative, no correlation, low correlation, and nonlinear. By following a 5-step process, you can use scatter diagrams to determine the optimum tolerance zone and target value for a process parameter. You can access the job aid about using scatter diagrams after this video to review the steps for determining tolerance zones and target value. If you were conducting a survey to learn how people feel about an important public issue, how would you go about it? It wouldn't be practical to interview every person in the country. Instead, you would probably interview a relatively small number of people and draw inferences about the entire population from their responses. The people you included in your survey would constitute a sample of the larger population. As a Six Sigma practitioner, you too will often use sample data to make inferences about larger populations. You can only be certain about the characteristics of a larger population by analyzing its parameters. And since it's possible to measure the risk of sample-based inferences, you can draw statistically confident conclusions about population data based on sample data. When you're using inferential statistics, the goal is to reach conclusions that extend beyond the presentation and summarization of data. In contrast to inferential statistics, descriptive statistics are primarily concerned with summarizing and presenting sample data. You use descriptive statistics simply to describe what's going on in your sample data. Inferential statistics are concerned with predicting what will be by extrapolating from the sample data to the population. The statistics you use in Six Sigma projects are primarily inferential because, for most processes, you're interested in understanding the characteristics of the total population. The sample data you use to draw conclusions about a population is largely based upon measures of central tendency, mean, median, and mode, and measures of dispersion, range, and standard deviation. Terms and symbols are used to clearly differentiate between population and sample data, and their associated values of central tendency and dispersion. You should be familiar with populations and samples from your Greenbelt training. You can access the content on population parameters and sample statistics after this video to review concepts related to populations and samples. The main problem with inferential statistics is that they involve uncertainty. Outcomes tend to vary when repeated observations are made under identical conditions. However, when certain mathematical conditions are met, theoretical statistics allow you to predict the likelihood of various possible outcomes of observation. The essential concepts in statistics are derived from the theory of probability. The conclusions you make using theoretical statistics are basically statements about the probability of particular kinds of outcomes. You can make statistical inferences about a population from sample data if you can determine its distribution. Regardless of the shape of the parent population, the distribution of the means that you calculate from samples quickly assumes the shape of a normal distribution. To calculate the sampling distribution mean, you average the means of all the samples in the distribution. You should already be familiar with the concept of distribution from your Greenbelt training. You can access the content about normal distribution and sampling distribution after this video to review these concepts. The concept of distribution is a key aspect of the central limit theorem. The central limit theorem states that the sampling distribution of mean of sufficiently large sample will be approximately normal regardless of the shape of the population distribution. Basically, the theory is a mathematical truth that allows you to draw conclusions about a population based on sample data, even when the distribution of the population is unknown or known to be non-normal. Increasing the sample size used to calculate the mean of the sampling distribution increases the probability of achieving a more accurate estimation of the true population mean. The formal definition of the central limit theorem is, given a distribution of a random variable with a mean mu and a variance sigma squared, the sampling distribution of the mean will approach the normal distribution as the sample size, n, increases. This means that with a sufficient sample size, you can determine the mean and standard deviation of the population using the mean and standard deviation of the sample distribution, no matter what the shape of the population's distribution. You should keep the following concepts in mind about the central limit theorem. The letter n represents the sample size for the sample mean. This is the number of scores that go into the computation of each mean, not the number of samples. With a large sample size, the distribution of the sample means will be normally distributed even if the population isn't. For most population distributions, but not all, a sample size of 4 or 5 will provide a near normal sampling distribution. Here is another consideration to keep in mind regarding the central limit theorem and sample sizes. Sample sizes of 30 are usually large enough to make X bar approximately normal, no matter how far the population is from being normal. Understanding the significance and implications of the central limit theorem is important. With the central limit theorem, you can apply statistical inferences and analysis to sample data whether or not the population is normally distributed. Applying statistical inferences based on sample data yields important process and product information that you can confidently assume is representative of the larger population. The central limit theorem is the foundation for many statistical procedures, including control charts. This is due to the fact that the distribution of the phenomenon under study doesn't have to be normal because its average will be. Control charts show whether or not a process is in statistical control. The data calculated from samples can be used in control charts, which assume normality. You can use the sample data from control charts, which plot many small samples, to make inferences about the population. Suppose a production manager monitors the mean weight of machine components. When a point in the control chart exceeds the control limits, it indicates that the process is out of control and action should be taken. Confidence intervals provide probabilistic ranges of values for population parameters from sampled data. For example, you can determine a confidence interval inside of which there is a very large probability that the population mean or population standard deviation falls inside this interval. You'll have more confidence that the sample mean is close to the population mean when the sample size is large, and less confidence when the sample size is small. This inference about population parameters based on sample statistics, regardless of population distribution, is made possible by the central limit theorem. The spread of the X-bar distribution will be less than the spread of the population distribution. Using a formula, you can use the standard deviation of the X-bar distribution to estimate the standard deviation of the population. The key principle of the central limit theorem, or CLT, is that the sampling distribution of the mean will approach the normal distribution as the sample size increases. A hypothesis test allows us to draw conclusions or make decisions regarding population data from sample data. The hypothesis test is applied using two competing hypotheses, the null hypothesis and the alternative hypothesis. The null hypothesis is the idea being tested, and in most instances is a statement leading to no effect or no difference. The null hypothesis is either rejected or failed to be rejected once the sample data has been analyzed. If the p-value derived from the sample data is less than the cutoff value or significance level that you've already defined for the test, then you can reject the null hypothesis. You need a normal distribution for the dataset to be able to apply hypothesis testing techniques correctly. However, there are many instances when the distribution is non-normal. To work with non-normal data, you can use the central limit theorem, or CLT, to test hypotheses with certain limitations. With the CLT, any sample mean data set that is randomly sampled from a population is regarded as normal if the sample size is large enough. This will apply regardless of distribution. To use the CLT, the sampling distribution of means has to be sufficiently large. But what is considered a sufficiently large sample? In practice, many statisticians say that a sample size of 30 or more is considered large enough. While there are exceptions to this rule, it is an important guideline to adhere to. Consider the situation where a team of Six Sigma professionals at a metal fabricator is determining if a machine for cutting metal sheets is producing excessive scrap on account of uneven width of these sheets. They want to conduct a hypothesis test to validate their assumption about the mean width of these sheets. They take random samples of 4 metal sheets every 15 minutes and calculate their mean width. They collect and plot 20 such sample data points. However, they find a distribution that is clearly not a normal distribution. They know that for hypothesis testing to work, they need their data to be normally distributed. The black belt on the project, who's aware of CLT, recommends the team to take more samples, preferably over 30. The team takes 50 sample sets, determine their mean, and plot them again. This time, they see that the distribution is approaching normality. Now the team can safely assume the distribution is approximately normal and can conduct a hypothesis test on this data. Inferential statistics allow you to predict the characteristics of a population from a sample of data. Unlike descriptive statistics, you use inferential statistics to draw conclusions that extend beyond the summarization and presentation of data. Inferential statistics are commonly used in Six Sigma projects because analysts are often required to understand the total population data based on sample data. It's important to understand the central limit theorem and the concept of distribution. Regardless of the shape of the parent population, the distribution of the means that you calculate from samples quickly approaches the normal distribution as the sample size increases. This enables you to draw conclusions about a population based on sample data, even when the characteristics of the population are unknown or known to be non-normal. Whereas an approximately normal population will have an approximately normal distribution of sample means, even for smaller sample sizes, statisticians usually consider a sample size of 30 or more to find an approximately normal distribution for non-normal populations. A normal distribution is required when working with confidence intervals and hypothesis testing. A hypothesis test allows us to draw conclusions or make decisions regarding population data from sample data. The central limit theorem can be used to work with non-normal data. To test for variation in a group, analysis of variance, or ANOVA, can be used. While inferential statistics and descriptive statistics both have their place in Six Sigma practice, they are quite different. Descriptive statistics are typically straightforward and easy to interpret. Inferential statistics are often complex and may have several different interpretations. When using descriptive statistics, your goal is to present and summarize sample data. When using inferential statistics, your goal is to make inferences about a larger population based on sample data. Descriptive and inferential statistics also differ in the use of tools, techniques, and methods. With descriptive statistics, you use scatter diagrams, histograms, and frequency tables to meaningfully present data and squeeze additional information from it. When using inferential statistics, you analyze sample data to infer properties of population using techniques such as probability distribution, hypothesis testing, confidence interval, correlation, and regression. The methods you use in descriptive statistics typically involve counts and statistics, whereas you use process and mathematical models in inferential analysis. When conducting a descriptive analysis, you might ask questions similar to these. Based on the sample data, what is the average processing time? How much variation is there in the process? How is the sample data distributed and what kind of pattern does it reveal? When conducting an inferential analysis, you'll be interested in finding the answers to questions such as these. Based on the sample data, what is the average processing time for the larger population? What do you predict the error rate will be for the process? Based on the sample data, what percentage of the total customer population will buy defective products? You should be familiar with descriptive and inferential statistics, also known as enumerative and analytical statistics, from your Greenbelt training. You can access the content on enumerative and analytical studies after this video for additional information. The concept of applying statistics in order to understand processes is designed to gain information from a limited amount of data. Inferential statistics allow you to draw valid statistical conclusions based on a sample group. You can use 3 tools to help you draw valid statistical conclusions by utilizing correlation testing, confidence interval, and hypothesis testing. You can use correlation testing as a tool for drawing valid statistical conclusions from descriptive data. Rough assessments of correlation are involved when you analyze scatter plots and other graphical representations of descriptive data. There are precise formulas, such as the Pearson correlation coefficient, that you can use to calculate the strength of the relationship between 2 variables, but these are beyond the scope of this course. Drawing general conclusions from specific information can be dangerous. Your inability to be certain about the true situation is one of the central problems with theoretical statistics. You usually can only make a limited number of observations or conduct a study once in order to reach general conclusions. And since you're dependent on the sample evidence, you can never be completely sure of the accuracy of your conclusions. However, the theory of statistics provides ways for you to assess uncertainty and to calculate the probability of being right about a particular situation. Provided that you can make some assumptions about what's true, deductive statistics can tell you how likely particular results should be. Equipped with this information, you're in a better position to decide what actions you should take based on the sample evidence. You can use deductive statistics to help you determine the probabilities of error in a particular decision. You need to consider 2 elements when drawing conclusions about population characteristics based on sample data. The 2 elements comprise of the inference itself and the validity of the inference. In terms of measuring validity, inferential statistics allow you to draw various conclusions, such as determining the probability that sample results occur in the larger population given certain conditions. Other conclusions you can reach include whether you should accept or reject an inference, which will depend on the degree of uncertainty that you can tolerate. When drawing conclusions from the sample data, your goal is to determine the probability that a value is true of the population. However, you also need to determine what degree of risk is acceptable if the inference turns out to be invalid. Confidence intervals are statistical ranges with associated probability values that help you to show how statistics of your sample are representative of the population parameters. The larger the sample size, the more confidence you'll have that the sample mean is close to the population mean. Confidence intervals are written as a range in units of the specific characteristic the statistic and parameter are referring to. Suppose your sample data of 50 measurements gives you a diameter mean of a tool in the range of 6.23 to 17.04 centimeters with a 95% confidence level. This means you are 95% sure that the confidence interval, 6.23 to 17.04 centimeters, contains the true population mean. In most business processes, it's common to choose an alpha of 5% as the value of risk with a confidence level of 95%. Statistical procedures quantify the uncertainty of samples through confidence interval statements. A confidence interval statement can be single-sided or double-sided. A confidence interval statement can also relate to characteristics such as mean values and population variance. Statistical inference typically takes the form of hypothesis testing, which is similar to the confidence interval. Hypothesis testing is the process of using statistical tools to analyze a theory or opinion about the relationship between variables. When using hypothesis testing, the goal is to ultimately reject or fail to reject a theory or opinion based on your analysis. All hypothesis tests involve testing a sample of a larger population. With hypothesis testing, a test value is compared with a critical value that reflects the degree of uncertainty that can be tolerated. From this comparison, you can determine whether or not you should reject the null hypothesis and accept your alternate hypothesis with confidence that your results are not just the product of chance. Hypothesis testing involves 7 steps. The first step is to define the problem precisely. You should identify specifically what you want to know in plain business language or as a question. The second step is to choose a one-tailed or two-tailed test for the problem. You use a one-tailed test when you want to know whether your sample mean is significantly larger or smaller than your population mean. You use a two-tailed test if you want to know whether the sample is significantly different from your null hypothesis. The third step is to formulate the null and alternate hypotheses. The null hypothesis assumes there is no change from the original condition. The alternate hypothesis assumes a change has occurred. The fourth step is to select a test distribution and critical value of the test statistic. This will reflect the degree of uncertainty that can be tolerated. The critical value is usually set at 5%, 0.05. The fifth step is to calculate a test statistic value from the sample data. This calculation is slightly different for each test type. The sixth step is to make an inference about the larger population by comparing the calculated test statistic value to the critical value. By comparing these values, you can make a decision to reject or not reject the null hypothesis. The seventh and final step is to either fail to reject the null hypothesis or reject the null hypothesis and accept the alternate hypothesis. The hypothesis testing process prevents you from making decisions by intuition or gut feeling, and enables you to use data to back up your decisions with confidence. Let's consider the example: a Six Sigma team at a large retail bank is working to reduce the loan processing time from 8 days or more to less than 8 days. The team thinks that process improvement efforts have reduced the cycle time to less than 8 days. Team members know that if they apply inferential statistics to the sample data, they'll be able to make assumptions about the population within a certain confidence level. They decide to conduct a hypothesis test to determine whether process improvement efforts have reduced the cycle time. First, the Six Sigma team needs to define the problem, which involves finding the answer to the question, has loan processing time been improved to less than 8 days? Because the hypothesis is directional, whereby the team wants to determine if the loan processing time is less than 8 days, they choose to use a one-tailed test to find out whether the sample mean is significantly larger or smaller than the population mean. Next, the Six Sigma team establishes a hypothesis. Since the alternate hypothesis assumes a change has occurred, the team members set up their hypothesis to assert that the loan processing time is less than 8 days. The team members then select a test distribution and critical value of the test statistic. They also establish that the degree of uncertainty that can be tolerated is 5%. Now the team members can calculate a test statistic value from the sample data. After team members compare the calculated value to the critical value, they are able to make an inference about the larger population. Based on this comparison, the Six Sigma team determines that it can reject the null hypothesis and accept the alternate hypothesis with a 95% degree of confidence. The team, by accepting the alternate hypothesis, assumes the loan processing time has been cut to less than 8 days with 95% certainty. Descriptive and inferential statistics differ in their goals, focus, tools and techniques, methods, and approaches. Whereas descriptive statistics simply summarize your data, Inferential statistics allow you to draw valid statistical conclusions based on a sample group. You can use 3 tools to draw valid statistical conclusions from inferential statistics: correlation testing, confidence interval, and hypothesis testing. Correlation testing is a tool you can use to draw valid statistical conclusions from descriptive data. You can make assessments of the correlation between variables by analyzing graphical representations of descriptive data. Confidence intervals provide probabilistic ranges of values for population characteristics from sampled data. Hypothesis testing involves comparing a test value with a critical value that reflects the degree of uncertainty that can be tolerated. A coin is tossed in the air. How will it land? You can never know for sure if it will be heads or tails, but using probability, you can try to predict the likelihood of the outcome. In the probability formula, probability is represented by the letter P. Events are the desired outcomes in an experiment, with the first event assigned the letter A, the second event given the letter B, and so on. The term sample space refers to a set of all possible outcomes from a random experiment. An event is a subset of the sample space. To determine the probability of an event, you take the number of ways event A could occur and divide it by all possible outcomes. This can be illustrated by considering the relatively simple probability of getting heads in a coin toss. Since there's only one way to get heads, the numerator is 1. There are 2 possible outcomes, heads or tails, so the denominator is 2. Probability is typically expressed as a decimal or percentage, so the probability of event A tossing a head is 0.5, or 50%. You might also want to know how likely you are not to get a specific outcome. The probability that a simple event won't occur is represented by the probability of the event and the relationship to its complement. The probability that event A won't happen is represented by P-A complement. P-A complement and P-A are called complements because they always combine to equal 1. So if you are 50% likely to get heads in a coin toss, then you are 50% likely to get tails. If you're 40% likely to get the flu virus, you're 60% likely not to get it. You can access the Calculating Probability resource after the video to review basic probability concepts and terminology. Whether a coin will land heads up or tails up is a probability question about a simple event, an event that has an outcome that can only be achieved in one way. Each coin flip is an independent event, and the outcome of one toss has no effect on subsequent ones. But many events you'll encounter aren't simple and have multiple components. This course assumes that you have knowledge of the basic concepts and terminology associated with probability from your background in Six Sigma methodology. To understand compound events, you must ask questions about the relationships among events. For example, do the events contain sample points in common, or is the compound event mutually exclusive? Does event B contain all the points of the sample set that are not in event A? If yes, then they are complementary. If no, then they cannot be complementary. Does the occurrence of one event have an effect on the occurrence of other events? If yes, then they have a dependent relationship of some kind. If no, then they are independent. Let's consider an example now. The quality improvement team at an industrial chemicals manufacturer is analyzing the customer complaints about defects in its leading formulation. The defects involve violation of density, event A, and boiling point, event B targets in different batches of formulation supplied to customers. Out of many customer complaints, 8 are attributed to the defects being studied. Based on the data, the team wants to determine if the 2 defect events are mutually exclusive, complementary, dependent, or independent. So what is the outcome? Customer complaint C5 is common to both the events, so the events are not mutually exclusive. The events are not complementary because defect event B does not contain all the complaints that are not in defect event A. That is, there are more complaints than those included in A or B. The last characteristic of compound events for the quality improvement team to investigate is independence. By definition, if PAB is equal to PA, the events are independent. In this case, the probability of A is 1/2, and the probability of B is also 1/2. The probability of A and B is 1/8, since there is 1 out of 8 complaints in common to both events. So the probability of AB is 1/8 divided by 1/2, or 1/4. Therefore, PAB is not equal to PA, and events A and B are dependent. Understanding the probability of events can help you solve problems, improve processes, and reduce variation. This knowledge is critical when you want to analyze process data without bias. When teams can determine that one event is reliably associated with another, they will be in a better position to control the dependent event by controlling the events it is dependent upon. This course assumes that you have some prior knowledge of event relationships. You can access the resource Independent, Dependent, and Mutually Exclusive Events after the video to review how to determine the probability of variously related events. If you're planning a camping trip, it would be nice to know if it might rain so you can pack accordingly. The chance of rain is affected by different circumstances. For instance, precipitation is more likely in early April than late August, and your location also affects the probability of rain. You can analyze many different event circumstances when determining probability. For example, before you leave to go camping, you might try to predict different conditions such as complementary, dependent, independent, mutually exclusive, or not conditional. Different formulas are used to calculate the probability of events under different circumstances. 2 rules can be used to find combined probabilities: the multiplication rule and the addition rule. The multiplication rule is used to find out how likely it is for multiple dependent or independent events to happen simultaneously. You use the multiplication rule when finding the probability of both A and B. Usually, these events are the result of more than one task, such as rolling one die and then another, or drawing 2 cards from a deck. There are 2 different calculations, one formula applicable to independent events and one applicable to dependent events. The addition rule finds the probability of occurrence of one or more events. For example, if A and B are 2 events, the addition rule will find the probability that either or both of the 2 events occur. For the addition rule, one formula is applicable to non-mutually exclusive events, and one is applicable to mutually exclusive events. You can access the Multiplication and Addition Rules resource after the video to refresh your knowledge on the application of these rules. Suppose you're investigating the probability of both cards being aces if you draw 2 cards from a deck. The 2 events are dependent, since you're not replacing the first ace into the deck after you draw it. So, what rule and what formula should be used to calculate this probability? To find out the probability of drawing both aces, you use the multiplication rule for dependent events. This rule says that for both of the events to occur, the first one must occur, and then, given the first event has occurred, the second event occurs. The probability of drawing one ace is 4/52, but the very act of drawing the first ace changes the number of cards remaining to 51. These cards now contain 3 aces, so the probability of drawing an ace on the second draw is 3/51. To find the chance of both A and B occurring, that is, drawing 2 aces, multiply 4/52 by 3/51. To get a winning lottery ticket, you need the right numbers. But to open a locked safe, you need the right numbers in the right order. In the language of probability, the lottery numbers constitute a combination, and the combination to a safe is actually a permutation. In Six Sigma data analysis, permutations and combinations offer practical help in identifying the optimum configuration of products or processes. The biggest difference between permutations and combinations involves order or arrangement. Combinations are used when order doesn't matter, as for groups. Examples of combinations include choosing flowers for a bouquet, dealing a hand of 5-card poker, and selecting managers for a special task force project when all of them are similarly qualified. Permutations are used when order matters, as in lists. Since permutations take the order or position of elements into account, examples include mathematical formulas, since the order of the steps of the formula is critical, and determining how many access codes for a security system can be created from a certain number of digits. In probability, you often have to figure out the number of outcomes of an event and divide by the total number of possible outcomes. For some problems, you can easily count outcomes, but for other, more complex problems, manual counting becomes laborious. That's where combinations and permutations come in. The permutation and combination formulas have a number of elements in common. In both, the N stands for the size of the larger group, and the R represents the size of the smaller subgroups. The exclamation points in the formulas are factorials. A factorial is calculated by multiplying the number shown before the exclamation point by all whole numbers leading up to and including it. A factorial of 4, which is represented by 4 exclamation point, equals 4 times 3 times 2 times 1 equals 24. Let's discuss each formula in a bit more detail. The permutations formula tells you the number of possibilities that result if the subgroup items can be placed in different orders. The number of permutations, represented by NPR, is equal to the factorial of n divided by the factorial of the result of n minus r. The combinations formula tells you how many ways you can select n objects, taking them in groups of r objects at a time. The combinations formula is the permutations formula, but divided by r factorial, and n minus r refers to the size of subgroups. Suppose you need to solve a probability problem. There are 2 steps to follow. Decide whether the scenario is a combination or permutation situation, and then perform the calculations using the correct formula. Consider this combination situation. After work, you need to exercise, E, cook dinner, C, and phone a friend, P. But you know you'll only have time to do 2 things. In this case, N is equal to the 3 activities, and R is equal to the 2 possible. Notice that with combinations, you don't count the different order of activities as separate possibilities. EC and CE are considered the same. If you instead wanted to know how many different ways you could arrange your schedule, the order of activities would then be important, and you'd need to calculate a permutation. Consider this probability problem. How many different programming project teams of 5 members can be created from 20 computer engineers? Finding the solution will take 2 steps. First, determine whether this is a combinations or permutations situation. In this case, the project teams are being formed without any consideration of members' order or rank within them, so this is a combination problem. For step 2, you would use the combinations formula to calculate the answer. In this case, n equals 20 and r equals 5. So the formula takes the factorial of 20 and divides it by the product of the factorial of 5 and the factorial of 15. The end result is that there are 15,504 combinations of 5 engineers for the programming project teams. You need to understand the relationship between events when calculating probability using the multiplication and addition rules. The number of ways a larger group can be broken down into smaller groups also provides vital information. For combinations, order isn't important, but it is for permutations. Once you know that, you can select the right formula. A probability distribution displays all possible outcomes of an experiment with their respective probabilities. It's a way to link each result of an experiment with how likely it is to occur. Not every experiment has a numerical outcome. For instance, a coin toss can result in heads or tails. But random variables are functions that associate unique numerical values with every outcome. A random variable represents the probable values a variable can take in an experiment. A random variable can take discrete values, such as 0, 1, or 2, or continuous values, such as 1.5 or 3.7. The value of the random variable will vary from trial to trial as the experiment is repeated. A probability distribution of a random variable describes how probabilities are distributed over the entire range of values of the random variable. A probability distribution shows the distribution of x a random variable with a real value. Six Sigma practitioners use random variables for statistical tests, generating probability distributions that allow them to predict the probability of events occurring. Inferences can be made about sample data even if it's not abundant, based on the properties of known distributions. For Six Sigma, probability distributions of all kinds are used to answer questions like, what is the probability that a specific product will be defective? Or how likely is it that there will be so many defects per million parts? It's important to be familiar with the assumptions made about these distributions. You should have a basic understanding of this information from your background in Greenbelt concepts. You can access the Probability Distributions resource after the video to review characteristics of probability distributions. There are two broad types of random variables based on two types of data, continuous and discrete. Continuous data is also known as variable data and can be measured on an infinite scale. It can be broken down into smaller and smaller fractions and still have meaning. Some common examples of continuous data are measures of time, height, sound levels, and temperature, along with such industry examples as cycle time, cost, length, or width. Discrete or attribute data is counted data and isn't measured on an infinitely divisible scale. It includes information on occurrences, proportions, or characteristics, and is often binary, with measurements such as pass or fail, leak or no leak, go or no go. Things such as people, customers, cars, defects, or defectives are countable and are discrete. Three of the most commonly used discrete probability distributions are the binomial, hypergeometric, and Poisson distributions. The binomial distribution is one of the most important and frequently used statistical distributions in Six Sigma. Binomial data is based on the existence of only two outcomes or categories, either A or not A, pass or fail, defective or non-defective, heads or tails, and so forth. Binomial data is inherently mutually exclusive. Either an event happens or it does not. The binomial distribution is used when you're interested in the occurrence of an event, not in its magnitude. For instance, in a manufacturing experiment, a prototype may work or not. If you're interested in the number of units that work, and not how long the unit continues to function, the binomial distribution is the right choice. You should have an understanding of binomial distributions from your previous Six Sigma experience. You can access the Binomial Distributions resource after this video to review the characteristics of binomial distributions. In industry applications, the binomial distribution is commonly used to determine process yield by counting the number of defective items. There are many other uses as well. For example, estimating the probabilities of an outcome in success or failure trials, or sampling for attributes as in acceptance sampling. It can also be used for estimating the number of defective items in a batch, estimating the number of items in a batch, or for estimating the number of items that will be needed from inventory. Where there are exactly two mutually exclusive outcomes, such as success or failure, the binomial distribution is used to find the X success in N trials, with P as the probability of success on a single trial. The binomial curve will shift depending on the probability of the event occurring. The binomial distribution assumes the conditions for repetition are identical. But what if they're not? Suppose you have a jar with 10 marbles in it, 5 green and 5 blue. You randomly pull out one marble at a time, placing it on the table next to the jar until you have 3 marbles. Now, count the number of green marbles on the table. Congratulations, you've conducted a simple hypergeometric experiment. The hypergeometric distribution gives the probability of obtaining elements if those elements are chosen at random without replacement. A complex combination calculation is involved and applies when you know or can calculate the defined occurrences. The hypergeometric distribution is appropriate under similar conditions as the binomial distribution. But the hypergeometric is used when the sample size is more than 10% of a finite population. In other words, it's used when the tested sample is a large part of the total. For example, in the hypothetical marble experiment, the marbles are being pulled out of the jar and no more marbles are going in, so the sampling is occurring without replacement. Although the hypergeometric distribution is closely related to the binomial distribution, there are differences. The binomial distribution requires the probability of success to be the same for all trials, while the hypergeometric distribution doesn't. Because you're sampling without replacement, in a hypergeometric distribution, the trials are not independent, and the probability of success changes slightly from trial to trial. In the marble experiment, even though there are only 2 colors of marbles, it's not a binomial experiment. The probability of success is changing every time you pull out a marble from the jar. The probability changes from 5/10 to 4/9. In the hypergeometric distribution, the relatively large sample size without replacement changes the probability slightly with each observation. Hence, the formula is different from the binomial formula. The hypergeometric distribution is used to determine the probability of a specified number of successes or failures when a sample is selected from a finite population without replacement, and when the sample size is large in proportion to the population size. This makes the hypergeometric distribution useful in a wide range of organizational situations, including human resources and quality inspection. Let's see how the hypergeometric distribution applies to human resources and quality inspections using some examples. HR has been tasked with going through a pool of applicants to find engineers who can be matched in pairs to provide strengths in both programming and debugging. The entire applicant pool, population, is divided in 5 processing batches, samples. As the organization goes ahead with the recruitment process, 20% of the candidates from each batch are picked randomly from the pool, assessed, interviewed, selected, or rejected. These candidates' resumes are not replaced back into the pool, and a fresh set of candidates are considered for interview. As the applicants are randomly matched, the hypergeometric distribution is used to find the probability that engineers with excellent strengths are selected. A batch of chicken feed contains 200 pounds of corn from a local supplier and 400 pounds from an overseas supplier. When concerns arise about the possibility of fungal contamination in the offshore corn, the feed manufacturer ramps up its testing process. During the sampling, 20 pounds of corn are selected randomly and without replacement. The hypergeometric distribution is used to find the probability that all samples are from the offshore supplier. Remember, the conditions that govern the binomial also govern the hypergeometric, except that independence is not assumed, and the conditions for repetition are not identical. The Poisson distribution is vital to Six Sigma practitioners. It's most often used to model the number of random occurrences of some phenomenon in a unit of space or time. This makes it ideal for modeling defect counts per unit, or failures over time, and provides the basis for the control limit formulas for the C and U control charts. The Poisson distribution describes situations where you can count the number of times that events, such as defects, occur, but you can't count their non-occurrence. You can use it to study probabilities of rare events that occur randomly in time or over distances, areas, and volumes. Rarity here implies the low probability of occurrence compared to the sample size. The Poisson distribution can be used in situations where P, the probability of occurrence, is small, and N, the sample size, is large. The Poisson distribution depends only on the average number of occurrences per unit of time or space. The Poisson distribution is associated with rates, flows, or counts, so it's commonly used to study arrival rates of customers, whether at banks, call centers, restaurants, theme parks, or traffic lights. For example, using this distribution, you can estimate the number of cars passing a fixed point in a 10-minute interval and improve traffic flow dramatically. If the average transaction volume in a call center system can be estimated, the Poisson distribution can determine the most likely minimum and maximum number of transactions you will deal with within a given time period. Insurance companies typically model accident rates and mortality statistics with Poisson distributions, since accidents and deaths usually occur at random in populations. The Poisson distribution describes discrete data that includes multiple possibilities for repeated values, but with a low probability of occurring. Starting from a few simple equations that describe random events, The Poisson formula generates predictions for large-scale patterns. These resulting distributions take different shapes depending on the type of process being modeled. The Poisson distribution is used when counting the number of occurrences of a rare event in a long series of trials. You should already have a basic understanding of this distribution from your Greenbelt studies. Some other unique characteristics of the Poisson distribution include that the length of the observation period is fixed in advance, and the events occur at a constant average rate. Additionally, the events are independent of prior occurrences within the sampling unit. You can access the Poisson distributions resource after the video to further review the characteristics of Poisson distributions. There's a simple way to decide which distribution to use. A flowchart can help you choose the correct discrete distribution for your study. Just 3 questions will enable you to make a choice from the 3 distributions covered in this video: Poisson, binomial, or hypergeometric. Let's consider the 3 questions. The first question, are you studying rate with no upper limit on occurrences? Concerns rate and boundaries. Ask yourself if rate is being studied and if there's no upper limit on how many occurrences can happen. If rate is being modeled and there's no upper boundary on occurrences, the Poisson distribution is a good choice. If the answer or answers are no, you should go on to the next question. The second question, do you have a set number of trials? Involves the number of trials. If your study has a fixed number of events, so the answer is yes, go on to question 3. If there's no fixed number of successes, in other words, the number of trials is the random variable, and the answer is no, you use either the geometric or negative binomial distributions. While these distributions may be used, they are beyond the scope of this course. The third and final question, do you have the same chance of success each time and is the sample size small? Concerns the probability of success and the sample size. Is the probability the same on all trials and is the sample size less than 10% of the population? If the answer is yes to both of these, use the binomial distribution, and if no to one or both, use the hypergeometric distribution. Let's review an example now. In an insurance company, the number of accident claims submitted in a week averages 50. What distribution should you use to find the probability that no accidents will occur in a given week? Well, the first question to ask is if this study concerns rate or counts with no upper limit on occurrences. Since this study is about accident rates and uses discrete data, and there's no upper limit on the amount of claims that can be filed, the answer is yes. The Poisson model should provide you with an accurate representation of these probabilities. Let's consider another example. For an Internet Service Provider, ISP, there are 5 errors out of 20 client modem installations. If the ISP can only check on 3 of these installations, what distribution should be used to find the probability that none or all of the 3 checked installations will have errors? To identify the correct distribution to use, start by asking the questions in order. First, are you studying rate with no upper limit on occurrences? The answer to the first question is no, since rates are not being studied, and 20 is the upper boundary for occurrences. Then the next question, do you have a set number of trials? The answer to the second question is yes, since there are a total of 3 trials. And finally ask, do you have the same chance of success each time and is the sample size small? The answer to the third question is no. The probability of success is not the same on all trials, since once the installation is checked, it's taken out of the sample set and not replaced with another, and the sample size is greater than 10% of the population. Now, you need to take the theory of the flowchart and translate it into a practical choice of probability distribution when you're on the job. Using the correct probability distribution will help you make predictions about the probability of occurrences. For instance, you'll be able to determine how a process output falls above, below, or between targets, such as quality specifications. You can then use such information for effective decision-making. In some quality control situations, you may have trouble organizing data in a particular distribution. That's the time to use equivalencies and approximations. They allow you to approximate one probability distribution with another and may make it easier to work with your data. For example, the binomial curve begins to approach the normal curve as probability, p, increases, So in that situation, you can use the normal to approximate the binomial. The term approximates implies that for data under specified conditions, there are equivalencies among the three distribution types. Let's examine each distribution type for the conditions suitable for using approximations, starting with binomial. The binomial approximates to normal when NP is greater than or equal to 5 and n times 1 minus p is greater than or equal to 5. Next is hypergeometric. The hypergeometric approximates to binomial when the population size is 20 times larger than the sample size. The third one is Poisson. The binomial distribution approximates to the Poisson when n is large and p is small. When p is less than 0.1, n is greater than or equal to 16, and mu, or np, is less than 7, you use np as the mean of the Poisson to get a binomial equivalent. Discrete distribution functions are used to model experiments for counted or attribute data. The binomial is used when an experiment results in one of two outcomes. The hypergeometric is used when there is sampling without replacement. The Poisson distribution is unbounded and used for rates over time or space, for events with low probability of occurrence, and for large sample size. Being able to choose the appropriate discrete distribution for a given study and identify the equivalent approximations and conditions under which it holds true will help you use discrete data more effectively. Small, medium, or large. Group 1, 2, or 3. Data that fits into these kinds of categories is discrete and non-continuous. But continuous data, also known as variables data, can be measured on an infinite scale. For instance, if you select one part from a production run, there may be small variations from temperature fluctuations, operator differences, calibrations, tool wear, or raw materials. These measurements each have a real number value, giving you continuous data. The probability distribution of every continuous random variable is represented by an equation called the probability density function, or PDF. This is plotted on a graph. PDF of a continuous random variable is a function which describes the probability that the random variable takes a value in the sample space. PDFs can be used to determine the likelihood of a continuous variable, x, being found on the distribution curve. For example, you can use a PDF to determine the probability that a particular random variable falls between defined upper and lower specification limits. A continuous probability distribution differs from a discrete probability distribution in several ways. In a discrete probability distribution, the probability of a random variable is a non-zero value, so a discrete distribution can be presented as a table of values. In a continuous probability distribution, the probability of any one point is 0. Since the number of data points is infinitely large, dividing 1 by this infinitely large number results in an insignificantly low value, effectively 0. And because the individual probabilities are 0, you can't present the values in a table. You have to use a formula or an equation to summarize the random variables in a continuous probability distribution. For a continuous probability distribution, the density function has several properties. First, since the PDF is defined over a continuous range of values, otherwise known as the domain, the graph is also continuous. Then, when computed over the domain of the variable, the total area bounded by the curve and the x-axis is equal to 1. The PDF is represented by a curve, and the area under the curve between two numbers is the probability that the random variable will be between those two numbers. And the probability that x is less than or equal to a is equal to the area under the C. From your previous Six Sigma experience, you should already be familiar with the common continuous probability distributions, such as chi-square, F and T distributions, and the normal distribution. This video will cover the less common continuous probability distributions, including the log normal, exponential, Weibull, and bivariate normal. There are times when the normal distribution just won't fit. What do you do when your data is modeling extreme events? Sometimes using the logarithm of a variable can give an improved fit to your observations. The log normal distribution, the first of the four that will be discussed, is flexible and fits many kinds of failure data. The log-normal distribution is used for general reliability analysis, cycles to failure, and loading variables. It's often used to model modes of fatigue stress. Since this includes most, perhaps all, mechanical systems, the log-normal distribution has broad and useful applications in Six Sigma. Industrial applications include measures of strength, such as the tensile strength of fibers and the breaking strength of concrete. The log-normal is also used for environmental data, such as random quantities of pollutants in water or air, and economic variables such as per capita income. The log-normal distribution is scaled on a base number, and the scale of the distribution is based on a power. If data values in a distribution have many outliers, unusual characteristics, or unknown shapes, the data distribution can be subjected to a mathematical transformation so that they assume a more manageable distribution. Log-normal transformation is useful when the data follows a logarithmic scale, and if the data is transformed with a natural log, the resultant data will be following the normal distribution. There are several ways of transforming the data, including taking the square root, taking the inverse of the value, and taking the inverse of the square root of the value. When log-normal data is subjected to the log transformation, a normal distribution results. This relationship to the normal makes the log-normal easy to work with mathematically. In the log-normal distribution, a variable y is equal to e to the z exponent when z is a normally distributed variable. You can obtain the mean and variance using formulas unique to the log-normal distribution. The details of these formulas are beyond the scope of this video. The mean of the transformed data sets, the location parameter, and the standard deviation of the transformed data set will correspond to the shape of the curve. The log-normal distribution is skewed right, and the skewness increases as the value of sigma increases. The PDF starts at 0, increases to its mode, and then decreases. What would you do to estimate the approximate length of time between check-ins at a reception desk, calls at a call center, or customers at a cashier? If the events occur continuously and independently at a constant average rate, you can use the exponential distribution to determine the time between events. The exponential distribution is used in modeling the rate of change that will occur in a given amount of time. It can help you determine how long equipment will keep working with proper maintenance and part replacement. The exponential distribution is used to model the behavior of independent variables that have a constant rate. The occurrences of the variables are described by a Poisson distribution, but the times between occurrences are described by the exponential distribution. Naturally, the exponential and Poisson distributions are closely related. In fact, if x is Poisson distributed, then y equals 1 over x will be exponentially distributed. The exponential distribution occurs naturally when describing the time between arrivals in a homogeneous Poisson process. For example, if the rate of events over time, such as the number of arrivals at a checkout counter or the number of product failures over time, follows a Poisson distribution, then the length of time between events, that is, between one arrival or failure and the next, will follow an exponential distribution. In this manner, the exponential distribution can model the interval between random events. In the exponential distribution formula, the failure rate is represented by the Greek letter lambda, and the mean is represented by theta. The exponential distribution transforms data so it has a common distribution with the same range and identical maximum and minimum values. The transformation is performed by ranking the scores in each domain and transforming these with the help of a formula that involves the natural logarithm and an exponential transformation. The exponential distribution is usually used to model the mean time between occurrences. In an exponential population, 37% of observations are below the mean and 63% are above. This is because you plot the inverse of the data, or 1 over x. Formulas are available for calculating the mean and variance of exponentially distributed data, but they won't be covered in detail in this course. The exponential distribution uses a constant failure rate, but what do you do when the rate isn't constant? Whether a system or item ages and the failure rate increases, or becomes younger with time, decreasing the rate of failure, the Weibull distribution is the best at modeling time to fail. The Weibull distribution is a versatile distribution due to its flexibility. It can simulate the behavior of other statistical distributions. It can take on many different shapes due to having parameters of shape, scale, and location. Based on these parameter settings, the Weibull can mimic distributions such as the log normal, exponential, and more. The Weibull PDF can be used to derive reliability metrics such as the reliability function, mean, and median. It's one of the most widely used distributions in reliability and statistical applications, and is used to model time to failure, time to repair, and material strength. The Weibull and log normal distributions are quite similar and are from the same family. Either one can be used to assess a data set that contains close to average values that are not too high and not too low. But the Weibull is a better fit for data sets where a majority of data falls to the higher side of the range. And log normal can better fit data sets where a majority of the data falls to the lower side of the range. The Weibull distribution uses estimates based on parameters to form a linear distribution. Distribution characteristics are affected by three parameters: shape, scale, and location. The Weibull shape parameter, represented by beta, determines the shape of the distribution. Beta is also known as the slope. Different values of beta can have marked effects on the behavior of the distribution. In fact, some values of the shape parameter cause the Weibull to emulate other distributions. The Weibull scale parameter, represented by eta, determines the spread or width of the distribution. A change in eta has the same effect on the distribution as a change of the x-axis or y-axis. The non-zero location parameter, or gamma, is the point below which there are no failures. This is the parameter that locates the distribution along the x-axis. Changing the value of gamma has the effect of sliding the distribution to the right or left. The shape parameter, beta, gives the Weibull distribution its flexibility in modeling. For example, when beta equals 1, the shape of the Weibull is identical to the exponential distribution. When beta is between 3 and 4, the shape is identical to the normal distribution. Several values of beta can approximate the log normal distribution. Increasing the scale parameter eta while maintaining a constant beta and gamma will stretch out the PDF. This decreases height while maintaining the shape and location. Since the area under a PDF curve is a constant value of 1, the peak of the PDF curve will also decrease with the increase of eta. Decreasing eta in the same situation will push the distribution in, increasing its height. The location parameter shows the probability of failures at different times. When gamma is more than 0, there is a period when no failures can occur. When gamma is less than 0, failures have occurred before the time equals 0. At first, this seems counterintuitive, but a negative location parameter can be caused by defective raw materials or failures during transportation. Generally, the location parameter is assumed to be 0. When the location parameter is 0, the scale parameter is known as the characteristic life. This is also the mean of the distribution when beta is 1. Using the Weibull distribution will help you understand failure rates and get insights into why failures occur. Regardless of the specific value of beta in a Weibull distribution, 63.2% of all values fall below the characteristic life, and the variance decreases as the value of beta increases. When a Weibull distribution shows a decreasing failure rate, it suggests that defective items fail early and the failure rate decreases over time as the early defectives leave the population. A constant failure rate suggests failure from random events. An increasing failure rate suggests aging, or parts wearing out and becoming more likely to fail as time goes on. Leaving failure rates for a moment, what can you use when you're interested in two variables, such as height and weight, or water temperature and hurricane strength? When you have two variables that are normally distributed and may be totally independent or may be correlated to some degree, you need the bivariate normal distribution. As the name implies, the bivariate normal distribution is a generalization of the normal distribution. The bivariate normal is the joint distribution of two independent variables that simultaneously and jointly cross-classifies the data. Bivariate normal distributions may be discrete or continuous. To graph the bivariate normal distribution, you need a three-dimensional plot that appears somewhat like mountainous terrain. The x and y axes represent the independent variables, while the z-axis shows either the frequency for discrete data or the probability for continuous data. The bivariate normal distribution of x and y displays how they behave together, and the probability density is registered on z. The maximum or peak occurs when x1 is equal to mu1 and x2 is equal to mu2. You can take a slice anywhere along the distribution by fixing one of the variables. This is known as a conditional distribution. The formula is complex and won't be covered in detail. Computer software is usually needed to handle problems involving these distributions. The bivariate normal distribution is used extensively in manufacturing or service industries for joint probability distributions involving two continuous variables. The bivariate normal distribution can help determine items of critical importance beginning with causality by examining the joint frequencies to investigate if the second variable changes in a systematic way when the first variable changes. Next are predictions, by reviewing outcomes from one variable as the other changes. And finally, importance, since if two variables are causally related, they should have a statistically significant impact. The key to using probability distributions effectively lies in understanding what type of data you have. You also need to know the characteristics and assumptions that apply to each distribution. There are no clear and widely accepted rules for choosing one continuous distribution over another. However, depending on some broad parameters and the demands of the situation, you can choose a few distributions and test them to determine if they really fit the data. Choosing the appropriate distribution for your data is a process involving trial and error and verifications. Let's consider this example. The Six Sigma team at a heavy machine tools manufacturer is measuring the industrial bearing data for further analysis. The team collects key input data from a pair of variables, material density and material temperature in the bearing manufacturing process. Both the variables are known to be normally distributed and varying jointly. The black belt in the team wants to calculate probabilities involving both these correlated normal random variables and presents their distribution as a three-dimensional joint probability distribution. The black belt chooses the bivariate normal distribution for analysis of probability that tools manufactured using this process satisfy both temperature and density specifications. She uses a statistical software package to plot the material temperature on the x-axis, material density on the y, and probability on the z-axis. Using formulas unique to the bivariate normal distribution, the black belt is then able to analyze the probabilities and relationships of the two normally distributed variables. Different situations require different distributions. Let's take a look at a few examples of process and distribution choice. First up is the water pump process. The process improvement team at an auto manufacturer is working with the supplier of the water pumps to improve their overall reliability. To determine how to focus the improvement effort, engineering has collected data on how and when water pumps fail on sustained use. The average failure life of water pumps is estimated at 1,200 hours, with a range of 1,050 to 1,500 hours. Out of 100 observations, the majority are in the 1,050 to 1,100 hour group. Next is the water pump choice. The team is modeling lifespans of a product with a variable failure mode due to fatigue stress, and the majority of the data is on the lower side of the range. With these facts in mind, the team decides to use the log normal distribution to fit this data set. If the majority of the data fell on the higher side of the range, the Weibull might have been a better fit. Let's consider some other situations, for example, an electric motor process. The quality and design team at a small electric motor manufacturer wants to validate a motor's capability to sustain high voltage fluctuations. The team conducts a number of destructive tests and collects samples. All motors are connected to current at varying voltage levels, 120, 130, 140, 150, and 160, for 10 minutes, and the failing response is recorded. A total of 100 samples were tested at each voltage level, and the majority of the data falls to the higher side of the range. And the last one is the electric motor choice. The data obtained is successfully fitted in a Weibull distribution. The Weibull and log normal distributions are quite similar and are from the same family, and both can be used in reliability, survival, and life data analysis of equipment. But the Weibull is a better fit when the majority of the data falls to the higher side of the range. When choosing the most appropriate distribution, keep the following in mind, starting with use what you know about the data, such as the historical shape the data has assumed. Then use a goodness of fit statistic, probability plot, or correlation coefficient to compare competing distributions and test different distributions to find out how they affect your conclusions. When testing different distributions to determine how they affect your conclusions, keep in mind that if there's little or no difference between them, you can choose any distribution. However, if you find significant differences, it's safest to choose the distribution that yields the most conservative conclusion. To choose the most appropriate distribution for your continuous data, you need to know the characteristics and applications of the various distributions. The log normal, exponential, Weibull, and bivariate normal distributions all have certain strengths that can help you in your work. The log normal distribution is used when there's a random variable data set, the log of which follows a normal distribution, and the exponential is used when you're analyzing the distribution of time between occurrences. The Weibull is versatile and can take on the characteristics of other distributions, and the bivariate normal is for the joint probability of two continuous process variables. Being able to choose the most suitable continuous probability distribution can help you estimate lifespans and reliability and adjust policies or procedures as needed. The normal distribution, or Gaussian probability curve, often referred to as the bell curve, is called that because of its shape. A bell curve is shaped because the largest results are clustered around a central value with decreases in frequency as the distance from the mean increases. It's normally symmetrical, with 50% above the average and 50% below. A significant number of natural and man-made systems can be modeled by this distribution. Normal distributions are described by both the mean, mu, where the peak of the density occurs, and the standard deviation, sigma, or the spread. Most of the data is concentrated around the mean. Using the normal distribution, you can calculate the cumulative probability that a value will fall below a given variable, above a given variable, or between two variables, represented as part of the area under the normal curve within the interval. Although there are many normal curves, they all share what is known as the empirical rule, or the 68-95-99 rule. Let's review what each component of the empirical rule means. The 68 indicates that whatever the mean and the spread, the area within one standard deviation from the mean is always the same, comprising 68.3% of the data. In other words, 68.3% of the observations fall within one standard deviation of the mean, that is, between mu minus 1 sigma and mu plus 1 sigma. Next is the 95. The rule reflects that 95.5% of the observations fall within two standard deviations of the population mean, that is, between mu minus 2 sigma and mu plus 2 sigma. And then 99. The final rule component states that 99.7% of the observations fall within three standard deviations of the mean, that is, between mu minus 3 sigma and mu plus 3 sigma. Another important concept in understanding normal distributions is the central limit theorem, which you should be familiar with from your Greenbelt experience. This theorem states that sample data will approach a normal distribution as the sample size n increases. This basic tenet allows Six Sigma practitioners to assume that the sample mean and variance approximate to the population mean and variance, given a sufficiently large sample. You can access the normal distribution resource after the video to review explanations and terminology. The standard normal distribution is a perfect shape that can be used to model other normal distributions. There are known facts about the perfect curve that can be used to describe empirical data. The z-distribution, also called the standard normal distribution, has a standard deviation of 1 and a mean of 0, and the distribution is perfectly symmetrical around the mean. Any normal distribution can be converted into the standard distribution. The z-score formula tells you the number of standard deviations that an observation is from the population mean. Using the assumption of a standard normal curve, you can calculate z-scores for your sample data. This will allow you to assess the probability of any value based on its distance from its own mean, expressed as number of standard deviations. Cumulative probability with regard to a randomly selected value refers to the sum of probabilities between negative infinity and the specified value. To find the cumulative probability with regard to a specified value, you determine its z-score and look it up in a cumulative probability table. To determine the probability of getting a random variable value above a certain value, you look at 1 minus the cumulative probability value from the table for your z-score, since the total of all probabilities always adds up to 1. For example, the probability of getting values for z is greater than 2 is 0.02275, or 2.28%. Similarly, you also subtract the cumulative probability value from 1 to determine the probability for a negative z-score. For example, the probability of getting values for z is less than negative 1.5 is 0.06681, or 6.68%. Finding the probability of data falling between an interval under the curve is simply a matter of finding the z-scores for each value, determining the cumulative probabilities using a table, and subtracting. You can access the job aid Standard Normal Cumulative Probability table after the video to access a table to transform z-scores to probabilities. Z-score shows how many standard deviations above or below a population mean a raw score is. There are 3 steps for determining the probability of a value falling between 2 random values using z-scores. Transform raw data into z-scores, find the probabilities, and subtract one from the other. Consider this situation. A computer chip manufacturer is analyzing the time it takes to produce a certain chip. The mean time for manufacture is 150 seconds, and the standard deviation is 30. The manufacturer wants to know if the time it takes to produce a chip will fall between 140 and 170 seconds. To determine the probability of a value falling between 2 specified values, the chipmaker follows 3 steps. Transform raw data into z-scores, find the probabilities, and subtract one from the other. Let's continue with the chipmaker's example. The raw data needs to be transformed into z-scores using a transformation equation. To determine if the time it takes to produce the chip will fall between 140 and 170 seconds, the manufacturer first calculates each z-score. After the data has been transformed into z-scores, standard normal cumulative probability tables can be used to find the probabilities. While z-scores can be negative, probability scores cannot, so you use the positive equivalent of the z-score when using a distribution table. However, you subtract this value, 0.62930 in this example, from 1 to account for the negative z-score of negative 0.33. The final step to give the probability of a value falling between 2 other values is to subtract the lower cumulative probability value from the higher. If you sample one chip from that population, the chances it took between 140 and 170 seconds to produce is 0.3779, or 37.79%. If the chip manufacturer only wanted to determine the likelihood of a chip taking longer than 165 seconds to produce, only one z-score is needed. Unlike the normal distribution, the Poisson distribution is associated with rates, flows, or counts, and is particularly well suited to situations where you can count a number of occurrences, but you can't count the number of non-occurrences. The Poisson distribution expresses the probability of a number of events occurring within an interval in space or time, if those events occur with a known average rate. You should recall from your previous Greenbelt studies that Poisson distributions describe discrete variables, and they allow you to find the probability of a given number of events, often defects, occurring in a given interval. You can access the Poisson distributions resource after the video to review explanations and terminology. The Poisson distribution is a special case of the binomial distribution, used when probability, p is small. It's important because many of the cases needing statistical support aren't necessarily concerned with small probabilities. That is, they're relatively rare events. The formula for the Poisson distribution includes two important components, the mean and the standard deviation. Let's continue by examining each Poisson distribution parameter. First is the mean. The mean and variance, standard deviation squared, both are equal to lambda for Poisson distributions. This is the only parameter needed to determine the probability of an event in a Poisson distribution. Then, the standard deviation of a Poisson distribution can be approximated by taking the square root of the mean, giving you an idea of the dispersion in the values. For the Poisson, if you know the standard deviation, you can identify the mean and vice versa. Then, if any situations that use counts and rates, unbounded, can be approximated by the Poisson distribution. Follow along as a black belt in a glass manufacturing plant makes calculations. First, the black belt calculates that the annual probability of rate of defect is 0.01. If the production population is 10,000 sheets of glass and is randomly sampled, she can expect a mean of 100 sheets to be defective. Knowing the mean, she can now calculate the standard deviation by taking the square root of 100. Unlike z-scores, which require you to calculate z, then consult the table, the probability of a given number of events can be found in two ways using the Poisson distribution. Six Sigma practitioners can either calculate the Poisson probability using the Poisson distribution formula, or find the probability using a Poisson distribution table. As with the normal distribution, there's a table that can be used for calculating cumulative Poisson probabilities. The rows show the actual rates of the data, and the columns show the mean. Finding the intersection gives the cumulative Poisson probability. For example, say a black belt at an auto parts company wants to find the cumulative probability of getting up to 6 defective injectors on a given day in the factory, rather than exactly 6. If the mean is 3.5, she can use the table to locate the probability of 0.935. So how do you know when to use the normal or Poisson distribution? Well, populations display characteristics of one or the other, and Six Sigma practitioners need to know how to use each one. Many populations display normal or near-normal distributions. Normal distribution has no skew, and therefore offers a high level of confidence that data reflects actual conditions. In a normal distribution, two parameters are needed, namely the mean and the standard deviation. You can use the normal distribution to know your population, that is, the probabilities of obtaining different random samples from within it, which is the basis for statistical testing. For example, the shipping times at a parts manufacturing facility depend on the transport company used. The average time for transport over the past 2 years is 12 days with a standard deviation of 1.5 days. A test shipment with a new shipping company took 15 days. The manufacturer wants to compare this shipping time to the average time. The company uses the normal distribution because there is a large data set and the mean and standard deviation are known. The Poisson distribution is ideal for modeling defect counts or rates, especially for small sample sizes or infrequent events. You need only one parameter, the mean or standard deviation, since the other can be calculated from the one you know. A computer hardware company might use the Poisson distribution to determine the probability of a backup system failure. With few sample events, but a known mean, this distribution is a good choice, especially because rate is the parameter being studied. The normal and Poisson probability distributions each have specific formulas and uses. Six Sigma practitioners can model collected data with these distributions to assess and predict process capability and performance. The normal distribution is used to model approximately normal data, while the Poisson distribution is an unbounded distribution suitable for modeling rare events. Both the normal and Poisson distributions can be calculated through a formula or through the use of distribution tables. It's important for Six Sigma practitioners to be able to choose the appropriate distribution formula and use it to find probability. You can access the job aid probability distribution formulas after the video for a reference to probability distribution. If you have a prototype part that has a 50% probability of being defective and submit it to 4 tests, you will more than likely have 2 defectives. However, there is also the chance that you could have 0, 1, 2, 3, or 4 defectives, or conversely, similar results for non-defectives. This type of situation is referred to as a binomial distribution, which is used with discrete data with mutually exclusive outcomes, typically success or failure. Six Sigma practitioners often use the binomial distribution to count the number of defective or non-defective items in a sample. They can then investigate process yield by determining the probability of finding that number of defectives in a sample taken from a population with a known percent defective. So if you find a large number of defectives in your sample, and the probability of finding this is low given the known percent defective in the population, it could indicate that something has changed in the process. In Six Sigma, the binomial distribution might be used in many different situations. You can model the number of defective units in a lot, the number of units that fail under warranty, items that fail outside of specifications, or even the number of people that respond to a survey. When using the binomial distribution, you need to identify the number of trials, n, the probability of a success on any one trial, p, and the number of successes desired, x. You may have an understanding of binomial distributions from previous Six Sigma experience. You can access the resource Binomial Distributions and Formula after the video to refresh your knowledge of binomial distributions. Binomial distributions are used to calculate the probability of an event occurring in a given number of trials in order to determine process yield. That is, you can calculate the probability that an experiment results in a certain number of successes or failures. For example, if a product has a 0.05 defect rate, the binomial distribution can determine the probability that testing will yield 3 defectives out of 100 samples checked. You can calculate binomial probabilities using the binomial formula or binomial distribution tables. Let's examine each method for calculating binomial probability in a bit more detail. The binomial formula allows you to estimate the probability of events based on a sample. In the formula, p is the overall binomial probability, x is the event, lowercase p is the probability that x will occur on any particular occasion, and n is the number of opportunities for x to occur. For the 2 distinct outcomes of binomial experiments, success is designated p for probability of success, and failure, which is all outcomes except those defined as success, is designated 1 minus p for probability of failure. The other method is to use binomial probability distribution tables when samples are relatively small. Binomial probability distribution tables contain pre-solved probabilities for different values of the binomial formula for sample sizes less than 25. Every value shown in the table represents the probability of x occurrences in n trials for a given probability of success, p. A cumulative binomial distribution table can be used to determine cumulative probability of x or fewer occurrences. Using the binomial tables is straightforward. Suppose you work for a solar panel manufacturer. Your company's records show that about 10% of the panels have serious scratches. If you inspect 15 panels, what's the probability that you will find no scratched panels? Since the sample size is less than 25, you can use a binomial table to determine the answer. All you need to do is look at the table for n equals 15 and find the intersection of p equals 0.1 and x equals 0, which is 0.206. Sometimes you'll have binomially distributed data, but you'll be interested in the number of defects or the location and spread of your data. The mean, standard deviation, and variance of a sample allow you to estimate if your data has certain characteristics, namely centered, within control, capable, and meets customer specifications. The mean formula for binomial data will give you an estimate of the count of occurrences. You need to know the sample size, n, and the probability of success, p. The standard deviation formula for binomial data deals with dispersion, which is location and spread. You need to know the sample size, n, and both the probability of success, p, and the probability of failure, 1 minus p. You can access the job aid probability distribution formulas for a reference to probability distribution formulas. Let's consider an example. You're a Six Sigma black belt at an electronics equipment manufacturer, where the DVD player molding process is being studied. Historically, this process is known to yield about a 4% defectives. By analyzing the QA data for all DVD players produced in a given shift, you want to find out if the mean and standard deviation exceed the defective limits of 3 and 1.5, respectively, for each shift producing exactly 50 items. This example represents a binomial distribution, since there are only two outcomes, defective or no defective, a fixed number of trials, 50, and independence. Plugging the numbers into the formula, you determine the mean to be 2. Let's continue with the example. As a Six Sigma black belt at an electronics manufacturer, you need to find out the standard deviation of the DVD player molding process. Plugging in the numbers you previously found into the formula, you determine the standard deviation to be 1.39 and conclude that the defect limits of 3 and 1.5, respectively, for each shift producing 50 items are not exceeded. Like the binomial distribution, a hypergeometric experiment focuses on the number of successes in a given number of consecutive trials. The biggest difference is that with the hypergeometric distribution, sampling from a finite population is done without replacement. As a result, unlike binomial distribution, probability of occurrence does not remain constant for all trials. The hypergeometric distribution is used for calculating probabilities for samples drawn from relatively small populations, when n is greater than 10% of the population n, and when samples are drawn without replacement. Two conditions distinguish the hypergeometric from the binomial distribution. The consecutive trials are not independent, and the probability of success changes from one trial to the next. This is because the item sampled is not returned to the population, and therefore the probability of success in the next trial is changed. An item's chance of being selected increases in each trial, so the change can sometimes be dramatic, especially if the population size is small. The hypergeometric distribution is the basic distribution underlying many sampling plans used in connection with acceptance sampling and quality control. Many software spreadsheet functions have the built-in capability to analyze hypergeometric probabilities. You simply enter in population and sample values. Suppose you receive a lot of 12 parts from a vendor. You need the parts badly and are willing to accept the lot if it has fewer than 3 defective parts. You decide to inspect only 4 parts since you don't have time to check every one. Checking the sample, you find one defective part that doesn't meet your acceptance criteria. Should you reject the remainder of the lot? What is the probability that exactly one defective part would be in your sample? Before you can answer this important question, you need to be able to use the hypergeometric formula to calculate the probability of this situation occurring. Let's discuss the components of the formula: Px, the numerator, and the denominator. First is Px. In the equation, n is the lot size, r is the total number of successes in the entire population, lowercase n is the sample size, x equals the specified number of successes in the entire sample, and Px is the probability of getting exactly x defectives in the sample. Note that the numerator term subscript r c subscript x gives the number of combinations of non-defectives, while subscript r c subscript x multiplied by subscript n minus r c subscript n minus x is the number of combinations of defectives. Thus, the numerator gives the total number of arrangements of samples from lots of size n with r defectives, where the sample n contains exactly x defectives. The term subscript n c subscript n in the denominator is the total number of combinations of samples of size n from lots of size n, regardless of the number of defectives. Thus, the probability is a ratio of the likelihood of getting the result under the assumed conditions. Think back to the situation of inspecting parts delivered from the vendor. You sample without replacement, the lot is small, and the sample is 25% of the lot. The hypergeometric is a good fit for this situation. N is the lot size, 12. R is the number of acceptable defectives in the lot, 3. N is the sample size, 4. X is 1, the number of defectives in your sample, and you're looking for the probability of getting exactly one defective in the sample. Plugging the numbers into the equation gives a probability of 0.509, or 50.9%. Before you can decide on accepting or rejecting the remainder of the lot, you need to solve the formula for x equals 0 as well as for x equals 1, since you would accept the lot if there were no defective parts as well. Adding the two probabilities tells you the probability that your current sampling plan will accept lots of 12 with 3 non-conforming units. The plan of inspecting 4 parts and accepting a lot with 0 or 1 defective parts has a probability of 0.255 plus 0.509 equals 0.764, or 76.4% of accepting a lot with poor quality. Such a high sampling risk is unacceptable in most situations. There are 2 formulas for finding the hypergeometric mean and standard deviation. As you may have observed, each distribution has a unique formula for calculating mean and standard deviation, which should be used accordingly. The mean is used when you are interested in the count of occurrences, that is, the number of defectives. The standard deviation, or sigma, is used when you're interested in the dispersion. Remember, the normal distribution can be used to approximate the hypergeometric distribution if both the mean, NP, and the probability of failure, n times 1 minus p, are greater than or equal to 5. The binomial distribution is used to model binomial data where there is one of 2 outcomes, while the hypergeometric distribution is used for calculating probabilities for samples drawn from relatively small populations and without replacement. The mean and standard deviation of a binomial data sample are used to estimate the location and spread of the population data. With hypergeometric data, the trials are not independent, and the probability of success changes as the items are sampled. It's not only important to be able to recognize when and why to use this distribution, but also to be able to calculate probability using the hypergeometric distribution form. In statistics, a sampling distribution is the probability distribution of a given statistic under repeated sampling. A statistic is a numerical value that characterizes the sample, so a sampling distribution can be used to help you make stronger inferences about the entire population. You consider all possible samples of size n that can be drawn randomly from the same population and compute the desired statistic for each one. This results in the sampling distribution. In Six Sigma, it's important to know what kind of distribution a pattern of observed data fits into. For example, is it a normal, Poisson, binomial, chi-square, students t, f, or other type of distribution? Since sampling distributions are formed from combinations of random variables, they aren't typically used to model physical phenomena, but are used to make decisions, test hypotheses, and construct confidence intervals. Distributions such as the chi-square, f, and students t address a sample and find the cumulative probability of the observed data. The chi-square statistic is used to investigate whether distributions differ from one another. Sample data can then be generalized to more complex situations, as when desired information from one production line can apply to the whole factory. You're probably familiar with chi-square distributions from your previous Six Sigma experience. You can access the Confidence Intervals resource after the video to review sampling distribution concepts. The chi-square distribution is formed by summing the squares of standard normal random variables. Since it's based on squared random variables, it's similar to the distribution you get when you plot sample variances, squared standard deviations, from a normal distribution. This is why it takes the shape it does. The chi-square distribution begins at 0 and continues to positive infinity, so there can be no negative results. The chi-square probability distribution has many uses in business statistics, including goodness of fit testing and hypothesis testing. Let's cover each type of testing using the chi-square distribution in a bit more detail. Have you ever had to make a decision where everything depended on whether your sample results would match the real-world situation? A goodness of fit test can help you determine the probability that a computed test statistic could occur randomly. Chi-square tests are used in Six Sigma for testing the goodness of fit of an observed distribution to a theoretical one. It allows you to test your assumptions about data. The second type of testing is hypothesis testing. Six Sigma black belts constantly evaluate claims such as, "We're running at an average of 80% efficiency," or "Variable X causes variable Y to change by 20%. Hypothesis testing can help substantiate such claims. Chi-square tests are popular, in part, because they involve reasonable assumptions and relatively easy calculations to prove or disprove a hypothesis. You can test theories about population variances, since the distribution of sample variances drawn from a normal distribution is similar to the chi-square distribution. You can also evaluate the independence of differences between groups within a data set. For example, you might use the chi-square distribution to determine if a focus group sample differs significantly from a known national distribution based on census data. Whether your assumptions are based on a theory or based on some other known distribution, the chi-square distribution compares actual values to expected values to determine whether the differences exist to a degree that is unlikely due to chance alone. Chi-square is used with categorical data with either one or two variables, at least one of which can take on more than two values. In the formula, the chi-square symbol represents the test statistic. N is the sample size, S is the sample standard deviation of the new population, and sigma subscript 0 represents the standard deviation of the original population. You can access the chi-square distributions resource after the video if you wish to review concepts about using the chi-square formula. A black belt reviewing an online insurance company's claims processes believes, with 95% confidence, that the improved process should reflect a standard deviation of 15 minutes. To test this theory, she samples 10 claims, calculating a standard deviation of 9 minutes. She then wants to determine the chi-square statistic for the sample data to test her theory. The sample size is 10, the sample standard deviation is 9, and the standard deviation of the population is 15. Using the formula, she calculates that chi-square is 3.24. The next step is to consult the chi-square distribution table to find the level of confidence associated with this chi-square statistic. You can do this simply because the chi-square distribution is constructed so that the total area under the curve is equal to 1. The area under the curve between 0 and a particular value of a chi-square statistic is the cumulative probability associated with that value. You can look this value up on a chi-square distribution table that is also used to derive the level of confidence for the chi-square statistic. These tables are readily available online and in statistical publications. To determine cumulative probability using the table, you find the relevant degrees of freedom in the first column, continue along that row until you locate the approximate chi-square value, and follow that column to the top where you will find the cumulative probability of the chi-square value. In the previous example of the black belt reviewing the online insurance company's claims processes, the sample size is 10, making the degrees of freedom 9 and the chi-square statistic 3.24. Using the table, the black belt determines the cumulative probability is approximately 0.05. This tells her that the probability that a standard deviation would be less than or equal to 9 minutes is 0.05 or 5%. Sometimes you need to test the equality of variances from two populations. In this case, you use the F distribution. The F distribution is similar to the chi-square distribution, as both involve statistic of variance to characterize sampling. The F distribution is related to the chi-square distribution since it's basically a plot of the ratios of two independent chi-square variables. The mean and variance for the F distribution depend on the degrees of freedom for each variable. In an F-density curve, the peak is near 1. Values that are far from 1 in either direction provide evidence against the hypothesis of equal standard deviations. The F distribution is often used in hypothesis tests, especially to test for equality of variances from two populations that are normally distributed, and in designed experiments using ANOVA. The F distribution is formed by dividing one randomly obtained sample variance by another. To calculate the F statistic, you use the formula and begin by squaring the standard deviations for each sample under consideration. The ratio of these variances is then calculated to produce the F statistic. Just as with chi-square, Every F statistic can be associated with a unique cumulative probability. You probably have some prior knowledge of F statistics from your Six Sigma experience. You can access the F distribution resource after the video to review concepts about using the formula. The student's t-distribution is also related to the chi-square distribution. Unlike the F distribution, the student's t-distribution is formed by dividing a standard normal random variable by a chi-square random variable, accounting for the degrees of freedom. A specific t-distribution is defined by its degrees of freedom. The bigger the sample size, the more the t-distribution resembles a normal distribution. The student's t-distribution, or t-statistic, is often used for hypothesis testing and constructing confidence intervals for means. When random variables are averaged, the distribution of the average tends to be normal, no matter what the distribution of the individuals. The t-distribution formula shows that the distribution is equivalent to the F distribution with 1 and k degrees of freedom. There are still certain situations when you would use the t-statistic instead of chi-square. For example, when sample sizes are small but populations are thought to be normal. Also, when the standard deviation of the population is unknown, or when dealing with inferential problems involving the mean of a normal population. The test statistic value for t-distribution can be calculated using the t-statistic formula and the t-critical value by using a t-distribution table. The formula for finding the t-value allows you to determine a cumulative probability that represents the likelihood of finding a sample mean less than or equal to x, given a random sample of size n. There are 4 steps to using the t-distribution table to find the t-critical value. First, you determine the value of degrees of freedom and find it in the first column. Next, you determine if the test is one-tailed or two-tailed. Then, determine the desired significance level for the test, and finally, you find the t-critical value at the intersection of the DF row and significance columns for your tail test. As with the chi-square statistics, you take the student's t and f statistics to the appropriate tables to determine the probability of those values. You can access the student's t-distribution resource after the video to review concepts about using this test statistic. The chi-square statistic is important for goodness of fit tests in statistical analysis, and it allows you to test theories about populations based on sample data. The F distribution is often used in hypothesis tests, especially to test for equality of variances from 2 populations that are normally distributed, and in designed experiments using ANOVA. When sample sizes are small, and the standard deviation of the population may not be known and has to be estimated from the data, the student's t-distribution applies. It's used to test hypotheses regarding confidence intervals and is applicable when dealing with inferential problems involving the mean of a normal population. Natural variation occurs within a process. It comes from the voice of the process. Using statistical data from the process itself, process limits and natural process spread can be determined. Let's look at current process performance. The current performance of a process is measured in terms of its process spread or natural process limits. The natural process limits, more popularly referred to as control limits, are positioned at plus and minus 3 standard deviations from a central value, such as mean. These limits are identified as lower and upper process limits, or LPL and UPL, or lower and upper control limits, or LCL and UCL. They represent all variations, common as well as special cause, inherent in a process. Now, let's consider process limits versus specification limits. As previously mentioned, process limits are based on the inherent variation in a process. These are determined by the statistical data from the process and are used to calculate process spread. Specification limits, or allowable process limits, on the other hand, are determined by customer needs and organizational priorities as the minimum or lower, or LSL, and maximum or upper, or USL, values. A central value between these limits, the ideal value for the process, is called the target. The specification limits are external to the process and come from the voice of customer, or VOC, or from the voice of business, or VOB. That is, specification limits are externally imposed on the process by the organization. most often based on customer preferences or requirements, and sometimes also reflect organizational choices and any regulatory requirements. As a result, process limits don't necessarily match the upper and lower specification limits. For example, consider a customer call center where process spread is based on the number of calls customer representatives currently take in an hour. The lower and upper specification limits, however, are set by the organization based on the number of calls representatives should take to meet the call flow and customer wait time requirements. What about defects? Defects, or nonconformances, are the area on both sides of the bell curve bounded by the curve, specification limits, and process limits. The core goal in Six Sigma is to bring the entire process spread, or as much of it as possible, within the specification limits. This minimizes the area representing defects, which is made possible by minimizing the process variation. Let's discuss process capability. This involves comparing specification limits to the process limits. In other words, comparing specification width to process width to determine how capable a process is in meeting its specifications. This comparison is the cornerstone of many improvement initiatives in Six Sigma. There are 4 possible states of being for a process. First, on target within spec. In this situation, the process limits are within the specification limits and the process is centered around the specification target. The products meet customer specifications. You also get on target out of spec. Here, the process is centered around the target, but the process limits are outside both specifications. This indicates that the process is centered, but some products won't meet specifications. When the process limits are within the specification limits, but the process mean is not centered around the specification target, you get off-target within spec. Here, the process is off-target, but the products still meet specifications. Finally, you have off-target out of spec. In this specific situation, the lower process limit is outside of the lower specification limit, and the process is not centered on the specification target. This indicates that the process is both off-target and not within specifications. Improving process performance is central to a Six Sigma initiative, and measuring is central to performance improvement. Measuring your processes before, during, and after an improvement effort provides objective data for evaluating whether your efforts have improved the process. The measure phase of the Six Sigma DMAIC methodology provides a vast array of measurement tools, metrics, for just this purpose. The core of Six Sigma quality control is the percent defective and its countermeasures. Shipping defective products creates quality problems, but not shipping them causes loss to the manufacturer. To avoid damaging the company's reputation, it's imperative to determine quality and percent defectives before products are shipped. You can use 4 basic metrics to help measure defects and the probability of defects in your products. First, defects per unit, or DPU, allows you to determine the average number of defects that exist when observing a sample population. It is calculated by dividing the number of defects by the total number of items. Defects per million opportunities, or DPMO, provides information on the mathematical possibility that an organization will produce defective products or services. DPMO is also known as parts per million, ppm. The Six Sigma DPMO is 3.4. To assess the yield of an entire operation on a cumulative basis, you can use the rolled throughout yield, or RTY. It measures the capability of a multi-part operation to produce products that are free from defects. Finally, first-time yield, or FTY, measures a single process's capability of producing products that are free from defects. It's also referred to as first-pass yield, or FPY. First-time yield provides a measure of capability for a single step or process. But what about operations with multiple steps or processes? This is where rolled throughput yield, or RTY, comes in. As you know from your studies, RTY is a cumulative calculation of yield or defects through multiple process steps. Rolled throughput yield reflects the yield for an entire operation on a cumulative basis by rolling over the yield from one process into the next. And RTY is a useful tool for identifying problematic steps in a process or problematic processes in an operation. For instance, each step in this 3-step process has a first-time yield above 90%. Looking solely at these numbers may lead you to think that the overall process is meeting your specifications. However, rolling the yield from one process to the next reveals a very different picture. The rolled throughput yield is only 84.9%, rounded to 85%. Let's consider another example. A company that does rhodium plating on jewelry wants to calculate the rolled throughput yield for a sub-process in its plating operation. This involves 3 steps. In the first step, the first-time yield in the plating operation is 0.945, or 94.5%. We'll call this RTY1. The first-time yield for the second step, say RTY2, in the operation is 0.913, or 91.3%. And third time round, the first-time yield is 0.954, or 95.4%. This is RTY3. To calculate rolled throughput yield, you multiply the 3 first-time yield values together and round the final answer to 3 decimal places. Yield and defect rate are the Six Sigma metrics that communicate how often things go right and how often things go wrong. You need to be able to calculate and translate between the different yield and defect rate measurements. You can do this mathematically using some handy conversion formulas. If you have a relatively low defect rate, for instance a DPU of less than 10%, you can mathematically link the defect rate to the yield such that, if you know the DPU, you can simply calculate the FTY. In the equation, E is a mathematical constant equal to 2.718. If a process has a DPU of 0.3, for example, you can calculate that the FTY is 0.741, or about 74%. The same conversion formula applies to RTY and total DPU. So, given that FTY is equal to E raised to the negative power of DPU, it follows mathematically that DPU is equal to the negative natural logarithm, ln, of FTY. This means that, given the value of FTY, you can find DPU. This is easily done with a scientific calculator. For example, if a process has an FTY of 0.9911, you can determine that the DPU is negative ln times 0.9911, or 0.00894. Again, the same equivalency holds true for RTY and total DPU. There is a mathematical relationship between yield and process sigma such that once you know the yield for a process, first-time yield or rolled throughput yield, you can find the sigma value. Here's how it works. Yield is the percentage of product that requires no rework. When you subtract the yield from 1.0, you get the reciprocal, which is called the probability of a defect, P paren D. Probability of a defect represents the proportion of product that is defective. Once you know P paren D, you can take the value to a z-distribution table and find the corresponding process sigma value. Suppose you have a yield of 90.49%. By subtracting 0.9049 from 1.0, you get a probability of defect of 0.0951. Finding this value on a z-distribution table and following it over to the z-column gives you a z-value of 1.3, which is equal to the process sigma value. Process sigma value tells you how many standard deviations you should be able to fit in the specification limits for the process. For example, for a 3 sigma process, 3 standard deviations will be able to fit between the lower and upper specification limits. Many Six Sigma practitioners believe that a negative sigma is just a mathematical possibility, and they are very unlikely occurrences in the practical Six Sigma world. However, a large number of Six Sigma experts believe that a negative sigma value signals the presence of a very poor process. For normally distributed data, then, a negative sigma value would mean that over 50% of the process output is defective, which is not a very plausible or common scenario in the business world. For the purposes of this course, you will ignore the negative symbol and focus on the absolute value of sigma. A sigma value is a metric that communicates the ability of a process to perform defect-free work. The higher the sigma value, the better the process is performing, and the lower the probability that a defect will occur. As the sigma value of a process increases, depending on situations at hand, its costs, defects, and cycle time may decrease too. The term 6 sigma means that with 6 standard deviations on each side of the mean, nearly all products will meet the specifications. Ideally, a centered 6 sigma process has a mean that is equal to the target specification, and specification limits placed 6 standard deviations to either side of the mean. Portions of the distribution that are outside of the specification limits are 0.002 parts per million ppm of the data, with a mere 0.001 on each side. Suppose you work for a manufacturer that produces bearings. The outside diameters of your bearings must be between 0.9780 and 1.1310 to be acceptable to your customers. To test your process, you sample 200 bearings. You find that outside diameters range from 0.6890 to 1.450, and you determine the mean to be 1.070 with a standard deviation of 0.05. These numbers fit a normal distribution. The area of the distribution under the curve and between the vertical lines shows the percentage of yield that is within specifications. The shaded areas are the percentages of diameters that are out of specification. These areas represent the probability of a defect, P parent D. To find the sigma value for the process, you need to know either the yield or probability of a defect. In this example, you'll use P parent D. First, you calculate the z-score for the upper specification limit. Subtract the mean from the USL and divide that result by the standard deviation. The z-score is 1.22. Looking for this value in the standard normal distribution table, you find this area equal to 11.12% of the distribution. Next, you do the same calculation for the lower specification limit. Subtract the mean from the LSL and divide by the standard deviation, giving a z-score of 1.84, disregarding the negative sign. Looking for this value in the standard normal distribution table, you find this area equal to 3.29% of the distribution. Now, you add the two percentages together for determining the sigma level of the process. Combining the calculated percentages out of specification, 11.12 plus 3.29, yields a result of 14.41%. Since you know the probability of a defect of this process to be 14.41%, or 0.1441, you look that value up on the z-distribution table to find sigma. The closest value of sigma is 1.06. The P parent D value you found is also 1 minus the yield, meaning that yield for the process is 1 minus 0.1441 equals 0.8559 or 85.59%. Six Sigma process performance must be weighed against the process specification. Certain process limits are naturally present. They are determined as the upper or UPL and lower or LPL process limits. However, these inherent process limits are separate from what the customer has specified. The voice of customer, or the voice of business, is used to determine the upper and lower specification limits, the USL and LSL. Process capability is assessed by comparing the current process performance to the specification limits. There can be one of four results: on target within spec, on target out of spec, off target within spec, and off target out of spec. Process improvement, the heart of the Six Sigma initiative, depends heavily on measurements. Key metrics that you'll use in the measure phase of DMAIC include defects per unit, or DPU, defects per million opportunities, or DPMO, first-time yield, also known as first pass yield, FTY or FPY for short, and rolled throughput yield, or RTY. Rolled throughput yield is especially helpful because it provides an accurate picture of a group of related processes. Whereas examining each FTY in a process can be misleading, the RTY shows the amount of defect that is likely to occur throughout the combined processes. It can help you identify processes that need improvement. Because these metrics are related mathematically, you can use the values of yield to calculate defects per unit and vice versa. There is also a mathematical relationship between yield and sigma level. Once you know the yield for a process, the FTY or RTY, you can find the sigma level. For a normally distributed process, the sigma level is equal to the z-score of the proportion of products that are out of specification. To determine how well your processes meet customer requirements, you perform a process capability study. Before undertaking the study, however, you have to make sure of two things. Your process must be stable over time, and your data must fit a normal distribution. If both conditions are met, you can calculate process capability indices. These indices enable you to assess and compare conformance to process limits with conformance to specification limits. There are two main types of process indices. CP is a ratio of the allowable process spread, the specification spread, to the actual process spread. And CPK is a ratio of the same elements, but unlike CP, CPK makes an adjustment for a non-centered distribution of data. To calculate CP, you subtract the lower specification limit, or LSL, from the upper specification limit, or USL. Then divide the difference by 6 times sigma, or the standard deviation. For sigma, you'll often use an estimate of the population's standard deviation calculated from a sample of process data, since you likely won't have enough data to describe the entire output of a process. A CP equal to 1 or more means that the natural limits of the process fit within specification limits, and the process is capable. There are some handy rules of thumb for interpreting CP values. While there's no standard for a good CP value, many organizations require a CP of 1.33 or above. This value signifies that the process comfortably meets specification limits. It corresponds to 0.0064% or 64 ppm out of specification. A CP between 1.0 and 1.33 is capable with tight control. When a process has a spread that's about equal to the specification width, any slight movement of the mean off-center means that a significant portion of products will be outside a specification limit. Such a process must be closely monitored. A process with a CP less than 1 is not capable of producing a product or service that meets customer specifications. When using CP to assess process capability, you need to be aware that although CP may indicate a process is capable, CP doesn't consider the process center. An uncentered process can have a favorable CP and yet not meet customer specifications. The second metric, CPK, does the same thing as CP, except it does consider centering and spread. To calculate CPK, you calculate two different values and then compare them. First, subtract the mean, x bar, from the upper specification limit and divide the result by 3 times the estimated standard deviation, 3 sigma. Then subtract the lower specification limit from the mean and divide that result by 3 times the estimated standard deviation. The lower result in the two calculations is CPK. Why do you use the lower result? Because CPK focuses on the point at which the specification is closest to the process mean. Measuring the distance from the mean to the closest specification limit and calculating it as a proportion of the spread produces a more accurate picture of process capability. Dividing by 3 times sigma accounts for half of the total of 6 standard deviations that were used previously in determining CP. Traditionally, a CPK of 1.0 or greater has been considered capable, signifying that the process limits lie within specification limits. However, quality requirements have tightened up in recent years, and many organizations require CPK values of 1.33, 1.67, or even 2.0 based on customer requirements. These values are equivalent to 4, 5, and 6 sigma, respectively. Capability and sigma are linked. If your process is stable and normally distributed, you can use a z-distribution table to convert CPK, or CP for a centered process, into a sigma metric for both short-term and long-term values. For instance, you can determine sigma values for a CPK of 1.33, 1.67, or 2.0. You can use the job aid Process Capability Conversion table after this video as a reference for converting process performance values to sigma metrics. CP will always be greater than or equal to CPK. Based on experience in the real Six Sigma world, a process must have a CP of at least 2.0, a CPK of at least 1.5, and defects per million opportunities, or DPMP, of 3.4 or less to reach Six Sigma quality. You can access the content Process Capability after this video to review the meaning and interpretation of CP and CPK. Another way to express process capability is with the capability ratio, or CR. The capability ratio is the reciprocal of the capability index CP. It's calculated by dividing 1 by the CP value. The capability ratio offers the same information as CP does, only from a different perspective. As with the other capability indices, there are some rules of thumb for interpreting CR. Lower values of the capability ratio are better. A capability ratio less than 0.75 signifies the process is capable. Note that if you divide 1 by 0.75 to calculate CP, the result is 1.33, the traditionally accepted good CP value. On the other hand, a capability ratio of 0.75 through 1.0 is capable with tight control, meaning that the process bears watching, since small shifts could render the process not capable. A capability ratio greater than 1.0 is not capable of consistently meeting customer specifications. Suppose you work for a manufacturing company. Specifications for a machine slot are 0.5 inches plus or minus 0.003 inches. You need to determine the capability of the process to produce slots of this dimension, and you decide to use the capability ratio. The process mean is estimated to be 0.501, and the standard deviation is 0.001. You calculate CP as 0.55 by subtracting the upper specification from the lower specification limit and dividing the difference by 6 times sigma. Then you calculate CR by dividing 1.0 by 0.55 for a value of 1.818. With a CR greater than 1, you conclude that your process is not capable. Note that you could find CR without finding CP first by simply inverting the CP formula to calculate CR. In some cases, CP and CPK may not adequately address process centering. For instance, a customer may want to have data clustered more closely around a target specification rather than around the process average. To measure this, you use the CPM index, which was devised by Genichi Taguchi. The CPM index, also called the Taguchi loss function, measures the amount of loss resulting from variation when processes are within specification but not centered adequately around the target. The function demonstrates how the amount of loss increases the farther you go from the target, even though the process is within specifications. The Taguchi loss function demonstrates why you should strive to continually improve conformance to target, as opposed to conformance to specification. Because it is more sensitive to target, when the process is not on target and the target is not in the middle of the specification limits, CPM will be less than CPK, which itself is less than CP. The Six Sigma team at a smoke detector manufacturer determines that the sensor manufacturing process is very capable with a high CP value. Shari, the process owner, wants a highly sensitive product with a quicker response time, so she wants to determine the capability of the process around the target 0.16 as opposed to the process average of 0.18. She needs to use the CPM index. Now, the USL and LSL of the product are 0.25 and 0.05 respectively. The process average is 0.18 with a standard deviation of 0.02. Shari wants to adhere to the best-in-class target of 0.16. First, she substitutes values into the formula and subtracts the LSL from the USL. Next, she subtracts the target value from the process average and squares the result. She squares the standard deviation and adds the result to the previous result for a total of 0.0008. Last, she divides the specification spread, 0.20, by 0.168 for a CPM value of 1.19. The ideal CPM value depends on the industry and the nature of the business the organization is in. A CPM of more than 1 is preferred, and many manufacturing companies like the CPM to be in the range of 1.5. With a CPM of 1.19, Shari considers her process to be roughly within her manufacturing organization's guidelines. Capability indices CR and CPM are related metrics that lie next to CP and CPK in the Process Analyst's toolkit. The capability ratio, or CR, is another way of looking at process capability. It's the reciprocal of the capability index and provides the same information as CP. That is, it will tell you whether the process is capable, but not whether it's centered. You'll use the CPM index to assess the ability of a process to center around a target rather than around the process average. Capability indices are useful for forecasting potential short-term capability for stable processes that remain within control limits. But what if you need to find out how capable your processes actually are right now? For this, you use Process Performance Indices, PP and PPK. These indices measure the actual performance of a process in meeting customer specifications. Both indices are calculated based on extensive sampling that includes special cause as well as common cause variation. Unlike process capability indices, a state of statistical control is not a requirement for process performance indices. Since PP and PPK include all kinds of variation, they are more reliable indices for assessing long-term as well as actual process performance. The relationship between PP and PPK is similar to that of CP and CPK. PP determines the range of a process's variation with respect to customer specifications. It doesn't take centering into account. PPK, like CPK, determines performance in relation to customer specifications and accounts for process centering and spread. Capability and performance measures, like sigma, are ratios. They have no units. This makes them useful when you want to compare different processes. Suppose you want to compare 3 processes to find out which one is the most capable. Sales, shipping, and manufacturing are measured in dollars, time, and yield, respectively, so you can't compare them that way. However, you can calculate their sigma values and compare them to find that shipping is the most capable process, with manufacturing and sales following. The Process Performance Index, or PP, is calculated the same way as CP, except for the value of standard deviation, which reflects long-term sigma rather than short-term sigma. To calculate PP, subtract the lower specification limit from the upper specification limit and divide the difference by 6 times the sigma long-term, which is the standard deviation in the long term. This value is called sigma long-term because it represents both common and special cause variation, indicating that the sigma value will hold true over the long term. To determine sigma long-term, you calculate population standard deviation using the usual formula. Take the square root of the sum of the squared differences of the observed values from the mean, divided by the number of samples minus 1. This value is then multiplied by 6 to produce the denominator of the PP calculation. Like CP, PP does not take centering or spread into account. However, the Process Performance Capability Index, or PPK, does. The formula for calculating PPK is USL minus X bar divided by 3 sigma, or X bar minus LSL divided by 3 sigma. Let's see how a calculation is done. The first step is to find the differences between the specification limits and the mean by subtracting the mean from the USL and subtracting the LSL from the mean. Then you divide each of the results by 3 times the estimated standard deviation. The lower of the 2 numbers is the performance index. The higher the PP and PPK values, the more stable and capable the process. To interpret the results in relation to PP, you compare the PPK value with the PP value. If PPK and PP are virtually the same, the process is considered centered. If PPK is less than PP, the process average is off the specification target and closer to the specification limit. Most organizations require a PP of at least 1.33. Six Sigma performance requires a PPK of at least 1.5. Another way of looking at process performance is with the performance ratio, or PR. The performance ratio is the reciprocal of PP and is calculated by dividing 1 by PP. The performance ratio provides the same information as PP, only in a different format. The lower the performance ratio, the more capable the process. A PR of 0.75 is equivalent to a PP of 1.33 and means the process is capable. A PR of 0.75 to 1.0 means the process is capable with tight control. A PR greater than 1.0 means the process is not capable. You can access the content Process Capability after this video to review information about PP and PPK. An important objective of the measure phase of the DMAIC process is assessment. Six Sigma provides an array of indices for this purpose. Capability indices, CP, CPK, CR, and CPM, enable you to calculate how potentially capable your processes are over the short term. These indices are used with stable processes whose data fits a normal distribution. Capability indices can be converted to sigma values using a z-distribution table. Process performance indices, PP, PPK, and PR, are calculated using both common cause and special cause variation. As such, these indices reveal the actual performance of a process that is not necessarily in the state of statistical control over time. Most organizations require a PP of at least 1.33. Six Sigma performance requires a PPK of at least 1.5. In order for you to truly know if a process needs improvement, you need to know how capable it is. A process capability study measures the extent to which processes can create end products that meet customers' requirements. It has a number of different steps you can follow. However, their order may vary based on your organization's guidelines. Often, the first step in a study is to identify the characteristics you'll measure and their appropriate specifications or tolerances. The capability testing process assumes that your data is stable and normal, and you must test your process to verify these conditions. This is the second step. The third step is to develop a good sampling plan to ensure that you and your team gather a representative sample of data to use for calculations. Then, with the data you've gathered, calculate capability and performance indices and sigma levels. Finally, based on your calculations, decide what to do. If the process is capable, no further action is needed. If the process is not capable, you must investigate the cause and take corrective action. At the beginning of your process capability study, you'll identify key characteristics, specifications, or tolerances. Let's look at some guidelines to help you choose the right characteristics. You should choose characteristics that have a direct impact on quality. These are also known as the critical to quality or CTQ characteristics. The vital few key process output variables, or KPOVs, or key process input variables, or KPIVs. Also, choose characteristics whose measured value can be adjusted within the given specification range. In theory, every characteristic should be included in a capability study. In practice, you can't study everything. Pare down your selections to the vital few. In other words, select a manageable number of characteristics. Often, these will be the ones that have a history of difficulty meeting the specification. Also, if a process or part has many dimensions, select a small number of them to study. Lastly, bring all general operating conditions that affect process capability under control. These include heat, light, noise, and parameter settings. Your customers also have a voice in determining which characteristics are most important, and industry standards often mandate them. As you identify characteristics, you must also identify specifications or tolerances. These are usually established by customer requirements, industry standards, or by your own engineering department or organizational strategy. A specification consists of the ideal measure for the product plus the tolerance. These values are normally determined during development as ways to ensure that products are assembled with required fitness to perform their functions with minimal adjustment. Specifications are important to customers. If specifications are too tight and unrealistic, however, many potentially acceptable outputs can be rejected. While process improvement teams have little or no control over specifications, the concerned department may be able to negotiate relaxing the specifications with the customer. In any case, a close monitoring of the process is recommended until you find out what might be causing problems and work to make the process more capable. In addition to identifying key characteristics, you must also verify your process's normality. If your process isn't normal, a capability study can produce undesirable results. For instance, misinterpretation of special cause patterns on control charts, or misleading assessment of process capability due to incorrect statistical results for yields, CP, CPK, and sigma levels. Other undesirable results include incorrect assessments of alpha and beta risks associated with confidence intervals, acceptance sampling plans, and hypothesis tests, and misidentification of process parameters as important or unimportant for desired results. You can use a number of methods to assess normality, including a histogram and a comparison of data statistics with the properties of the normal distribution. Goodness of fit tests like the Kolmogorov-Smirnov and Anderson-Darling tests are also useful. A simple test for normality is a histogram. This is a visual representation of the frequency distribution of your data. You can use this as a quick visual check on whether your data is normally distributed. Another simple normality test involves comparing your data with properties of the normal curve. There are 3 simple tests you can conduct. 1. Compare the mean, median, and mode of your data. If these are equal to each other, your data is likely to be normal. You can also calculate the interquartile range, IQR, for your data and divide it by the population standard deviation, or the sample standard deviation if the sample is large. The IQR is the distance between the 25th and 75th percentile. If the result is approximately 1.33, your data is likely normal. Finally, compare the range of your data to the normal distribution. Approximately 68.27% of your data values should fall within plus or minus 1 standard deviation from the mean. 95.45% should fall within plus or minus 2 standard deviations from the mean, and 99.73% should fall within plus or minus 3 standard deviations from the mean. Goodness of fit tests are commonly used in normality testing. A number of tests are available to you, but 2 of them are the most common. With the Kolmogorov-Smirnov test, the distribution of the test statistic is independent of the underlying cumulative distribution function being tested. However, the test applies only to continuous distributions, and the distribution must be fully specified. It can't be estimated from the data. The Anderson-Darling test is a powerful modification on the Kolmogorov-Smirnov test. Anderson-Darling is especially effective in detecting departures from normality that occur in the tails of the distribution. The test for normality involves hypothesis testing, which is done with statistical software. The software returns a p-value statistic that represents the probability that you might be wrong to reject the assumption of normality about the dataset. You compare the p-value with a predetermined risk level, alpha, to determine whether to reject or not reject the assumption of normality. Whereas histograms, probability plots, and goodness of fit tests are examples of how to verify normality, measures of skewness and kurtosis are examples of how to verify non-normality in the data distribution. Normal data is symmetrical around the mean. When data is not distributed symmetrically, it is said to be skewed. Data distribution curves showing any of these characteristics will not be considered normal distribution. If the distribution has a long tail to the right and a concentration of the mass on the left side, the distribution is skewed to the right or positively skewed. On the other hand, if the distribution has a long tail to the left and a concentration of the mass on the right, the distribution is skewed to the left or negatively skewed. Kurtosis means the concentration of data values in the center of a distribution as compared to the tails. Kurtosis is sometimes referred to as an index of flatness or as a measure of tail heaviness. Distributions with high kurtosis relative to normal distribution tend to have a thin peak near the mean, decline rather rapidly, and have heavy tails. Distributions with relatively low kurtosis relative to normal distribution tend to have a flat top near the mean rather than a sharp peak, decline rather slowly, and have light tails. The kurtosis formula is complex, involving the differences around the mean raised to the 4th power. Tests for kurtosis and for skewness are done with statistical software. A useful rule of thumb is that data distribution is normal if the skewness and kurtosis measures are between -2 and +2. Another element in the capability study involves verifying the stability of the process. The common way to assess process stability is with control charts. To interpret a control chart, you must know its components. The upper control limit, or UCL, is typically 3 standard deviations above the center line. Similarly, the lower control limit, or LCL, is 3 standard deviations below the center line. The target, or center line, represents the mean value for the process when it's in control. This is the value around which you want the data points to cluster. Control limits are determined by the process itself in a way that if the process is in control, nearly all of your data points will cluster around the center line and fall between the UCL and LCL. Data points falling between the limits and the center line represent common cause variation inherent in all data samples. Data points falling outside the control limits indicate special cause variation, and also that the process is unstable. Both of these control charts show stable processes. Can you tell why the processes are considered stable? Variation centers around the target, and all of the data points are well within the control limits. You can access the content Understanding Variation after this video to review the types of variation inherent in data. In control charts, certain non-random sequences of data points indicate the presence of out-of-control conditions. These conditions include trends, spikes, cycles, and shifts. Let's take a look. 6 or more consecutive data points in a row in either direction indicate a trend. A spike occurs when a data point goes above the UCL or below the LCL. It's also defined by 2 data points that fall just within either control limit. Spikes indicate the presence of special cause variation. A cycle occurs when 14 or more consecutive data points show alternating higher and lower values in a sawtooth pattern. Finally, a shift is indicated by 8 or more data points that fall consecutively on one or the other side, not both, of the center line. A shift has a ragged, sawtoothed appearance and can result from changes in the equipment, methods, or materials, or a shift in the measurement system. For a control chart to be a useful diagnostic tool, you must capture any out-of-control conditions that are in your process. You do this by plotting a sufficient number of data points. A good rule of thumb is to plot between 20 and 30 data points. As noted earlier, control charts are used to determine process stability over time. The X-bar and R control chart is one of the most frequently used control chart types for continuous data. It shows variation from the mean and the range of your data. Observe the X-bar and R control charts for the process. If the data points are clustered around the center line, the process is said to be in control. On the other hand, if there are data points outside the limits, then the process is said to be out of control. Early in a process capability study, usually after verifying the stability and normality of the process, you and your team start developing a sample plan and gathering data. Since this data will serve as a basis for your statistics, it's essential that you gather a good representative sample. Often, teams stop data collection too soon and produce misleading calculations. To help you avoid this, it's good practice to take at least 50 samples. When in doubt, take a cumulative average of your samples. When the average begins to flatten out, you've probably got enough data. For processes that are currently running and in control, you can use your original control chart data to estimate standard deviation and calculate process capability indices. For processes that contain special cause or long-term variation, though, you'll need to collect additional sample data. The point of any sampling plan is to ensure that your sample accurately represents the larger population. If your process is stable and normally distributed, you can use the original control data from currently running processes as your sample. However, you must be sure to capture seasonal variations as well as any problems and special cause variation. And you may need to plan for collecting data over a long period of time to capture long-term variation. After calculating and analyzing capability and performance indices, you need to decide what to do. Your recommendations can take several forms. For instance, you could do nothing. You could also change the specifications if the customer allows it. Or you could center the process and even reduce variability. Alternatively, simply accept the losses and prepare for handling scrap and rework. Is do nothing really a legitimate option? Sure it is. If you find that your indices are within optimum ranges and the process limits are within specification limits, the process is capable. Unless your customer requires a higher sigma level, your decision to do nothing is appropriate. Another possible recommendation is to change the specifications. Specifications that are too tight create excess scrap and rework. Whether you can change specifications really depends on the customer. If the customer allows it, You may be able to negotiate more relaxed specification limits. Otherwise, you'll need to do a full inspection of the process to determine how to make it capable. Another possible recommendation is to center the process. Here's an example. Suppose a manufacturer is conducting a capability study on glass used for welders' goggles. The glass must have the right amount of tint to protect the welder's eyes. Too much tint and welders can't see what they're doing and may burn themselves. Too little tint and the welder's eyes could be damaged. In this case, centering on the target, the right amount of tint, is critical. Using data you gathered from 100 samples, you calculate the indices. A CP of 1.5 would indicate the process is adequate as long as it's centered on the target. However, this manufacturer's CPK of 1.17 and CPM of 0.883 reveal the process is not centered on the target. The manufacturer is producing glass within specifications, but consistently below target. The glass allows a little more light in rather than being a bit darker. In this situation, you recommend centering the process to bring the process back in line with the target and the specification limits. Another recommendation you might make is to reduce variability. This option is the most difficult and costly to implement as it may involve experimental designs and long-term studies. Another recommendation that you could make as a result of a process capability study is to accept the losses. This option is similar to do nothing, but doing nothing usually applies to a capable process that is performing at specification levels. An organization might choose to accept the losses when it would be more expensive to fix the problems than it is to live with them. You make this recommendation based on a careful cost-benefit analysis. A process capability study measures the capability of your processes to create end products that meet customer requirements. You often begin by identifying the critical to quality characteristics and their specifications and tolerances. These are the characteristics that you'll study. A capability study assumes data is stable and normal, so it's important for you to verify your process's stability and normality. You can verify stability with control charts. Plotting 20 to 30 data points gives you a good basis for finding special cause variation, as well as anomalies such as trends, spikes, cycles, and shifts. You can verify data normality with the following methods: a histogram, which is a comparison of your data statistics to properties of the normal curve, and goodness of fit tests, such as the Kolmogorov-Smirnov test and the Anderson-Darling test. Measures of skewness and kurtosis verify the non-normality of data. Early in the process capability study, you create a sampling plan and gather data. You must have enough data to obtain a representative sample of all special cause variation, seasonal fluctuations, and intermittent problems. Once you know how capable your process is, how well it's centered, and its level of variation, you make your recommendations. Recommendations can take 5 forms: do nothing, reduce variation, center the process, change the specifications, or accept the losses and prepare to handle scrap and rework. Short and long-term capability need clear explanations. A process that is Six Sigma capable in the short term won't remain so over the long term. Over time, variation increases as machines wear down, operators leave, materials vary in quality, and environmental changes occur. The phenomenon is known as drift, and it explains why control limits based on short-term processes are closer together than control limits based on a long-term process. Process drift degrades performance over time. A process that is capable today won't remain so over the long term. To account for drift, an adjustment factor of 1.5 is used. The commonly accepted definition of a Six Sigma process as one that produces no more than 3.4 defects per million opportunities, or DPMO, actually corresponds to 4.5 sigma in the long term. Every process will exhibit variations in its output. A distinction can be made between elements that cause short-term variation and those which cause long-term variation. There are conflicting definitions of short and long-term capability. In some cases, opinions about what constitutes capability are in direct conflict with each other. There is a lot of confusion surrounding the distinctions between these terms, and 2 sets of opinions have emerged to describe them. It's useful to be aware of both sides. The first opinion is that process capability is a measure of the highest expectations for the results of a process. However, it doesn't directly describe whether or not the process satisfies the needs of the customer. Generally speaking, it deals with short-term variability. The input for analyzing process performance and capability can be drawn from short-term or long-term data. The standard deviation from the X and R control charts describes the short-term variability, whereas the standard deviation of the total data set describes the long-term variability. During a business process, short-term variability may omit day-to-day variability or department-to-department variability. During an average manufacturing process, short-term variability does not typically include raw material lot-to-lot variability and operator-to-operator variability. The process capability indices CP and CPK are usually used to evaluate the potential short-term capability with a short-term standard deviation estimate. On the other hand, PP and PPK usually evaluates the total long-term capability with a long-term standard deviation estimate. The second opinion is that process capability is a direct measure of how well a process performs in relation to the needs of the customer. Here, the standard deviation describes total process variability. Even when referencing the R control chart data, only a total standard deviation value is determined. The protocol for determining the standard deviation is not fixed. Each analyst will therefore employ their own technique, ranging from a variance components model to simply grouping all the data together. During a business process, short-term variability takes day-to-day variability or department-to-department variability as likely causes. During the manufacturing process, short-term variability might typically include raw material lot-to-lot variability and operator-to-operator variability as likely causes. This is due to the second opinion adopting a more long-term view of the entire process. PP and PPK are seldom used to quantify the standard deviation for process capability measures, as this describes the total process variability. Let's consider the long-term shifted model of Six Sigma capability. The 1.5 sigma, ST, represents a design margin, M or M, of 25%. When this compensatory correction is applied to a short-term, ST distribution, it expects a long-term, LT performance of 4.5 sigma, LT, which is the remaining 75% of the total 6 sigma, STM, and is the equivalent figure of merit. The 25% safety margin is big enough to handle a sizable shock to process centering. In a 6 sigma process, the 4.5 sigma LT level of capability sets a DPMO of 3.4 parts per million, ppm. This means that any deliverable defined as 6 sigma has a critical to quality CTQ attribute that will adhere to a short-term capability of approximately 6 sigma ST. Over the long term, after many process iterations, it will not rise above 3.4 DPMO. The shift factor is, typically, added to the estimate of long-term capability. This strips away the long-term influences and approximates the short-term capability. The reverse is done to estimate the long-term capability. The shift factor is subtracted from the approximation of short-term capability. There are several key terms in the measure phase of a Six Sigma process. Process capability is a measure of how well a process and its output conform to the initial specifications. Specification limits define the amount of acceptable variation that can occur within a process while still meeting customer requirements. Process variability must be distributed so that all products fall within 6 standard deviations on each side, and must also fit between the upper and lower specification limits. Drift means that a 6 sigma capable process won't remain so over the long term. The exact definitions of short and long-term capability can be confusing. However, there's a distinction between elements which cause short-term variation and those which cause long-term variation. Capability studies require that data is normally distributed. But what is normal? Most people, things, and processes are different, and the same is true for data. There are no characteristics that define a perfect normal distribution. Some data falls within a normal range, but most data doesn't. For instance, suppose you own a television shopping channel and you guarantee delivery of products within 72 hours of purchase. To keep on top of your delivery process, you decide to test it. After collecting 50 samples of delivery time data, you create a probability plot and can see that the data isn't normally distributed. A histogram of the data shows that it's skewed. Most data points fall between 52 and 72 hours. This kind of skewness is typical of delivery processes. Since the capability indices CP and CPK hold true only for normally distributed data, how do you deal with non-normal data? Can you still test your delivery process for capability? Yes, you can. Two strategies are often used for dealing with non-normal data. You can transform the data to make it appear more normal, or you can find a known distribution model that fits your data and use its parameters for your calculations. Let's look at transforming data. You can often achieve a normal distribution by first subjecting each data point to a mathematical transformation. The transformation does not change the meaning of the results or the data points, it simply changes the way the data is expressed. What about distribution models? If your data follows a distribution for which capability can be calculated, such as a Poisson, Weibull, or log-normal distribution, you can calculate your capability based on parameters of the particular distribution. If you opt to transform the data, you can apply several common transformation options. For example, you could use square root or power, log, or reciprocal values. Data transformation is typically done with software, which performs the same mathematical operation on each data point. For example, the data set before transformation is not normally distributed. To transform the data, the square root of each data value was taken. The transformed data is more easily understood, more manageable, and better fits a normal distribution. In another example, a probability plot indicates that a particular set of time data is non-normal. Transforming the data by plotting the reciprocal for each data point gives a straight-line probability plot, indicating that the transformed data is normally distributed and can be treated as such. Don't forget that in order to work with transformed data, you must also transform the specification limits using the same mathematical operation. Choosing the appropriate transformation is a matter of trial and error, but you can use software to quickly test how data looks after being transformed in a variety of ways. The software produces a test of normality in the form of a probability plot for each transformation strategy, and you then choose the strategy that produces the most normal-looking distribution. Two commonly used transformation strategies are the Box-Cox power transformation and the Johnson transformation. Box-Cox is the simpler of the two. The Box-Cox power transformation uses exponents to transform data. This transformation raises data values to the power of lambda, where lambda equals a number between -5 and +5. The goal of the Box-Cox transformation is to find the value of lambda that will produce a data set whose variability is as small as possible. Lambda is simply the power to which your data points will be raised. If lambda is 2, each data value will be squared. If lambda is 0.5, then you take the square root of your data. If lambda is -2, then 1 over x squared is used. The Box-Cox power transformation formula for a lambda value not equal to 0 is x raised to the lambda power -1 divided by lambda. Basically, x raised to the lambda power. If lambda is 0, you don't use the same formula. Instead, you find the natural log of each data value. If you transform your data using the Box-Cox equation for successive lambda values, and then plot each lambda value against the standard deviation of your transformed data, you can identify the lambda that yields the lowest variability. This is the lambda value that is the lowest on the resulting Box-Cox curve. Since it's easier to work with whole numbers as exponents, it is customary to round decimal lambda values to the nearest number that is easier to work with. This will generally be the nearest whole number, with the exception of 0.5 or -0.5. These also make convenient values for powers. For this example, the lambda power that you'd use for your final transformation is 0.00. Many software packages will give you the precise value of lambda as well as the rounded value. Consider this situation. Your process improvement team at a health insurance company is measuring and evaluating the current and expected premium for a client company. You're using average employee age as one of the key inputs. The team collects sample data for 25 employees and normality tests the data with a probability plot and histogram. Both tests show that the data isn't normally distributed. You decide to transform the data using a Box-Cox transformation. Next, using software, you perform the transformation. The resulting Box-Cox plot provides a lambda value of -1.66, which you round to -2.00. A lambda value of -2.00 means that each data value will be transformed with the operation 1 over x squared. The probability plot created from transformed data and lambda values shows your data clustered more closely around the center diagonal, or the 95% confidence level. In addition, the test returns a p-value of 0.53, which exceeds the alpha level of 0.05. Both of these indicators signify that the data is normally distributed. Once you have transformed your data and obtained a data set that appears normally distributed, you need to verify its normality using a normality test, such as a new probability plot or an Anderson-Darling test. Then, before you can use the transformed data to calculate capability, you must also transform your specifications with the rounded lambda value used in the Box-Cox transformation. The Box-Cox power transformation test is simple, but it doesn't always work. The test focuses on finding the smallest variations among data values, not necessarily on achieving a normal distribution. If Box-Cox fails to give you a lambda value that will produce a normal distribution from your non-normal data, you may want to try the Johnson transformation. The Johnson transformation selects one optimal distribution function to transform non-normal data into normal data. The Johnson transformation is very complex, involves a number of complicated conversions, and is always done with statistical software. It returns a p-value that you can compare to alpha. If the p-value is larger than your alpha level, the distribution is normal. Another technique for handling non-normal data is to find a known distribution model and use it to model your data. For instance, if the data from your process follows a Poisson, Weibull, or log-normal distribution, you can calculate performance indices based on the parameters of that particular non-normal distribution. For cases in which data falls into other distributions, software is typically used to calculate process performance, but you must know the correct distribution to choose. Performing the calculations with software requires that you enter all of the data as well as the specification limits and choose the distribution that fits best. You need to be aware of some restrictions when calculating performance based on well-known non-normal distributions. For instance, you can't calculate CP and CPK for non-normal distributions. CP and CPK are based on z-scores, which are exclusive to normal distributions. And PP and PPK will be found based on the mean and standard deviation of the particular parameters of the known distribution, not the parameters of your data. For example, for the Weibull distribution, the shape and scale are used to estimate the probability of occurrence for the event being considered. The shape parameter beta and scale parameter eta are used in the capability calculation, generally done using software. If you can't determine which distribution to use, you can use software that will generate goodness of fit and probability plots for some of the commonly used distributions. Then you can visually determine which distribution seems to be the best fit. A chi-square goodness of fit test can also be used for this purpose. As you can conclude here, the data doesn't fit a normal distribution, but it does appear to fit a Weibull distribution. What if you've tried with no success to use data transformation methods and you can't find a well-known distribution that fits your data? Is there anything else you can do? Yes, but you need to do some detective work to determine the source of your data's non-normality. Check for outliers in the data. Should these be removed to restore the data to a normal distribution? Also, verify that your data represents only one population, and split the data if you discover that two or more populations have been mixed. Normal populations can produce a non-normal sample when they are combined. For instance, at your organization, one production line is slower than a second production line. You find that 40% of your products come from the slower line and 60% come from the faster line. When data from the lines is combined, data from the slower line pulls down the mean of the combined process. What you can do is subdivide the data into two sets, one for each individual process. Then calculate the defects per million opportunities, or DPMO, for each process, and combine the DPMOs into a single capability assessment. If you have exhausted all possibilities and you're sure that your distribution is correct, you can still assess capability for non-normal data by using more simple measures, such as parts per million, ppm, or percentage out of specification. Capability tests require data stability and normality. If your data is non-normal, you can first transform your data so it appears to be normal, then calculate capability. Or you can use parameters from well-known non-normal distributions to calculate your process's performance. The Box-Cox power transformation and the Johnson transformation are two strategies for transforming non-normal data to normal data prior to calculating capability. Box-Cox returns a lambda value that is used to transform data and specifications by raising them to the power of lambda. The Johnson transformation uses software to select the optimal transformation. In the event that transformation fails to deliver normal data, probability plots and goodness of fit tests can help to identify alternate distributions for modeling your data. From these distributions, PP and PPK, but not CP or CPK, can be calculated. If these methods fail, you should check your data to determine whether you have mixed populations that should be separated or outliers that can be eliminated. Finally, you can always assess capability with a simpler method such as parts per million, ppm, or percentage out of specification. Many customer requirements can't be defined through continuous physical characteristics such as weight, time, pressure, or temperature. Instead, performance must be measured through occurrences, such as how many complaints are received or defective products returned. Different types of characteristics are measured with different types of data. When working with Six Sigma, you deal with two types of data. First, continuous data is measured on a scale and can be infinitely divided and presented in fractions or decimal numbers. Temperature and time are examples of continuous data. Second, discrete data is binary or categorical data. It includes information on occurrences, proportions, or characteristics, such as pass versus fail, go versus no-go, or number of defective items versus number of customers. Discrete data cannot be presented in fractions or as decimal numbers. Delivery deadlines met, warranty claims made, products returned, and units scrapped or reworked are examples of discrete data. Up to this point, you've been accustomed to the terms continuous and discrete as applied to data. But as you move into the analyze phase and begin discussing statistical tools, you'll find the terms variable and attribute used more often than continuous and discrete. For this reason, those terms will be used for the remainder of this course. Continuous is interchangeable with variable, and discrete is interchangeable with attribute. Of the two types of data, variable data gives more information and is more precise. You should use it whenever possible. Having said that, however, Six Sigma is measured by defects, and there's a natural orientation toward attribute data. Six Sigma teams often start with variable data, then apply it to an attribute threshold to find the sigma level. Capability is calculated differently for variable and attribute data. For variable data, capability accounts for the total inherent variation of the stable process, with or without adjustments for process centering to specification targets. Assuming a normal data distribution, you can assess process capability with the indices CP, CPK, and CPM. CPK can be translated to a z-score, which corresponds to a sigma level. So, knowing CPK, you can use a conversion table to find sigma. Attribute data, however, is not continuously distributed over the entire range, so you can't use the familiar capability indices to express capability. Instead, capability for attribute data is expressed as a proportion of non-conforming product or number of defects, typically in parts per million opportunities or DPMO. Knowing your data's DPMO, for example, you can use the conversion table to find the correct sigma level. However, you can't go backwards in the table to find CP through the z-score. You can determine sigma level by calculating defects per million opportunities or DPMO. It's helpful to note that when you are determining sigma level for attribute data, DPMO and PPM are typically assumed to be the same. This is because, for academic purposes, most Six Sigma practitioners assume that there is only one defect opportunity per unit. DPMO is simply defects per million made into a more stringent metric by dividing it by the number of opportunities per unit. When this denominator is set at 1, DPMO and PPM are identical values. You can access the content control charts for attribute data after this video for more information. The primary way to monitor and determine capability for attribute data is with control charts. Unlike for variable data, where control charts indicate a response irrespective of specification needs, each data point on an attribute control chart is related to a proportion or percentage of nonconformance relative to customer requirements. If you're plotting new data, the control chart should contain at least 25 points showing statistical control. You can use historical data so long as you remove points known to be due to special cause variation. You can access the content control charts for attribute data after the video to review the basics of attributes control charts. Choosing the right control chart for attribute data is extremely important. A flowchart can help you make the right choices. One question that can help is, are you measuring defects per unit or defective parts? Let's look at the difference between defects and defectives. A defect is a measurable failure to meet a customer's requirement or performance standard. Because defects are defined through customer requirements, anything that customers find unacceptable is a defect. C and U charts are used to plot defects per sample or per unit. A defective is a unit of output, a part, for example, that doesn't meet specifications because it contains more than the allowable number of defects. A part may contain multiple defects, up to the specification limit, before the part itself is considered defective. NP and N control charts are used to plot defective parts. The number of defectives is often reported as a proportion or percentage of the total parts or units. The C and U charts, count charts, reflect the Poisson distribution, which describes count data. You'd use C and U charts when you want to plot numbers of defects in a sample or on a unit instead of categorizing the whole unit as defective or non-defective. C charts plot defects per sample, while U charts plot defects per unit. One way to easily remember the difference is to associate U with unit. You would use NP and P charts as a general measurement of the total process. NP and P charts are used with binomial data, and you use them when you're plotting the number or proportion of defective versus non-defective parts, satisfied versus dissatisfied customers, or defects per unit. NP charts help you determine the average number of defectives per sample, while P charts help you determine the average proportion of defectives per sample. One way to remember the difference between P and NP charts is to associate P with proportion and NP with number. Let's learn more about the individual characteristics of each control chart type. The C chart, or count chart, plots the actual number of defects per subgroup or sample, and can only be used when the sample or subgroup size is constant. The center line of the C chart, the C bar, shows the average number of defects per subgroup or sample. The U chart plots defects per unit and is used when the sample or subgroup size is either constant or variable. The center line of the U chart, U bar, represents the average number of defects per unit. An NP chart plots the number of defectives per sample and is used only when the sample or subgroup size is constant. The center line of the NP chart, NP bar, represents the average number of defectives. The P chart plots the proportion of what you're measuring, defective parts or satisfied customers. Use a P chart when the sample or subgroup size is either variable or constant. The center line of the P chart, P bar, represents the average proportion of defectives. Multiplying P bar by 1 million yields the DPMO. You can find process capability for attribute data using a method called the mean rate of nonconformity. After you've selected the right control chart and verified that the process is in control, the average value as expressed by the center line, C bar, U bar, NP bar, or P bar, defines process capability. Suppose you work for a manufacturer of coffee makers, and you're monitoring a timer improvement project. You decide to randomly collect subgroups of equal size, 200, from a single production line over a period of 15 weeks. You're interested in the number of defects in the samples. What kind of a control chart would you choose? Well, you're essentially counting defects, and you have a constant subgroup size. So you should use the C control chart. The U chart is used for variable sample size. The NP and P charts are used for defectives to include all coffee makers not meeting all specifications, which does not fit the situation. To calculate the center line for the chart, you determine the average number of subgroup defects per sample, the C bar. You calculate the mean by dividing the total number of defects, 406, by the number of subgroups, 15, which gives you a C bar of 27.07. This number represents the capability of the attribute data by revealing the number of defects in each subgroup. Customer requirements can't always be defined through variable data, such as weight, time, pressure, or temperature. Sometimes attribute data, such as how many complaints are received or how many defective products are returned, is used. Attribute data is not normally distributed as variable data is, so you can't use measures like CP, CPK, PP, and PPK. Instead, you can measure capability of attribute data with parts per million, or DPMO. Control charts are typically used to assess attribute data capability. Choosing the correct control chart is essential because the particular chart's center line, as calculated with a specific formula, represents your process capability. You can choose to use C, U, NP, or P control charts based on whether you are measuring defects per unit or defectives per sample, and whether your subgroup or sample size is constant or variable.